Good morning, and perhaps I should say good afternoon and good evening as well for the international audience. I am Jae-woo Jung, acting UTM project manager. I'll be moderating this event and also give two presentations. I'm grateful for this opportunity to welcome you and kick off the UTM Technical Interchange meeting. Before we dive into the event, I first would like to thank NASA and the FAA leadership and UAS community for their support of the UTM project, and also NASA Aeronautics Research Institute, NARI for short staff, and UTM team members' effort for preparing and running this event. Let's take a look at the agenda and meeting logistics and technology topics before we move on. Here are the UTM sessions before the meal break, which is about half of the team. We have welcomes from NASA leadership. After that, a project overview and history will be provided. The remaining sessions before the Q&A are about FAA, NASA, UTM collaboration work. That's one slide before, please. Also known as research transition team topics, such as concept use cases, and then system architecture, data transfer, sense and avoid, and communications and navigation. And then we'll also have a FAA welcome. The next slide. The UTM project had 4 phases, also known as technical capability levels, and as each phase concluded, in-flight demonstration took place. We will start the latter half of the team talking about this demonstration, followed by NASA's own flight test effort. Human factors and UTM modeling and simulations work will be discussed afterward, and the FAA will provide their UPP 2.0 summary. After the Q&A, we prepared an exciting panel for global impact of UTM, and I am looking forward to that myself. And as we end, we invited AOSP leadership and the UTM project manager until his retirement last year, Mr. Ron Johnson, to help me close the meeting. Next slide. So let me touch on the video collaboration platform. And as you know, this is done through YouTube live stream. And there's a link, and then that link is also on the webpage, but if you're watching it, you're already here. And for closed caption, there's a CC icon at the bottom, and you can turn that on. And the quality can be controlled there as well. And if you want to make sure that it's live, then hover over the bottom left of the menu, and it'll say live. Next slide. Now, we do have a question and answer platform, and since YouTube live stream isn't interactive, we're using conference.io, and there you can ask your questions, and then we will do our best to provide the answers within the time permit. And that link should be, let me double check on the meeting location as well. Okay, next slide. So nowadays, time to time, we run into internet connectivity issues. And if you are experiencing slow or delayed or poor connection of the video feed, then sometimes it helps to move close to your Wi-Fi router. And if possible, disconnect any devices you're not actively using from the Wi-Fi. Also, close any application or internet browser in the device that you're using so that you can dedicate the internet connectivity for the live stream and, if possible, the direct connection using wire works good too. And the video feed, YouTube live stream, can sometimes be improved when VPN is not in use. So that is one other thing to consider. If there's no internet connection, a suggestion could be restarting your modem and the router. And that can be done if one were to disconnect and reconnect to the power source. And sometimes there's a general outage of service in the area. Then that one will need to contact the internet service provider directly to sort it out. Next slide, please. So if you need logistical or technological assistance throughout the meeting, you can reach out to the NARI staff, NARI host, through the following two platforms. The one that we talked about, which is conferences.io, you can ask questions, but also check on logistical or technological issues as well. And you can also use the email arg-cal-nari@mail.nasa.gov, and we will promptly reply back to see if we can help. So that would be the end of the sort of kickoff / the logistics and technology. And let me use this opportunity to introduce Mr. Robert Pierce, who is the Associate Administrator for NASA ARMD. He manages the agency's aeronautics research portfolio and guides its strategic direction, including research in quiet supersonic flight over land, urban air mobility, autonomy, highly efficient advanced air vehicle concept, electrified aircraft propulsion, advanced materials, airspace operations and safety, integration and flight demonstrations of aviation systems, and the nurturing and development of transformative concepts for aviation. Administrator Pierce, thank you for joining us. Floor is yours now.
Okay, thank you. Thank you so much, Jae-woo. It's a pleasure to be here today to provide a few opening comments. So first, let me just say good morning to everybody, or as Jae-woo indicated, good afternoon or good evening, depending on where you are in the world. I'd certainly like to add my welcome to today's participants at the UTM Technical Interchange meeting. My remarks today will be brief. You all have important topics to attend to today, and my message is relatively simple and direct. But first, let me thank Jae-woo and also PK, Ron Johnson, Joey Rios, Marcus Johnson, and the entire NASA UTM team that led the way leading into today. Without your leadership and willingness to think differently about how we innovate and partner, we wouldn't be here today. But even more, UTM has been a community achievement, and it's a work in progress. NASA was a catalyst for innovation, but it took a community of innovators to make it happen. And I also want to thank everyone in the FAA and industry that collaborated with NASA to drive UTM forward. As I said, it's been a community, and it's a set of remarkable achievements that really set the baseline for the future of small UAS operations at low altitude. And while UTM itself is a critical innovation for the operation of low altitude small UAS, it's also an inspiration for a larger airspace innovation effort, including upper airspace and advanced air mobility that is yet to come. And therefore, NASA will continue to push the envelope on advanced architectures and automation for the future of airspace. And so while today is a culminating technical interchange for NASA's UTM effort, it is even more importantly an opportunity to take stock of the progress that has been made so that we can collectively, again, build the next chapter of innovation in airspace operations. NASA is committed to leading the way through research, innovation, and partnership, and I look forward to our continuing journey together. So with that, again, I thank everybody for your attendance today. I thank everybody for the partnership that you have given to us at NASA so that we together can see the fruits of those labors in the UAS traffic management system. So with that, let me thank you again, and I'll turn it back to Jaywu to get the Tim rolling, or over to Akbar, depending on how we're running this for the next section of discussion. Thank you so much.
Thank you, Bob. As we transition to the next, I'll introduce our director, Mr. Akbar Sultan, who is the Director of Airspace Operations and Safety Program, AOSP. He is responsible for NASA's aviation operations and safety research portfolio across 4 research centers. AOSP works with the FAA, industry, and academic partners to conceive and develop next-gen technologies to further improve the safety of current and future aircraft moving through the national airspace system. Director Sultan, thank you for joining us. Floor is yours now.
Thank you, Jaywu, and also want to sort of echo what Associate Administrator Pierce indicated just a moment ago. It's a big congratulations to the NASA UTM leadership team, the NASA UTM researchers, all of our, on-site contractors that developed all the great software and the systems, as well as all of our industry and FAA partners, without whom we would not be able to have this gathering today to sort of celebrate the great achievement we have made. So just want to congratulate the team. Next slide, please. Next slide. Thank you. Just wanted to sort of showcase the amount of progress that I think you all have made, because sometimes, when we're so ingrained into the daily work, the basic things can perhaps be lost. Yes, we're in 2021 right now. However, in 2015, if you all remember, probably a great majority of you were at the UTM convention that was held at NASA Ames, if you remember, in the big hangar and the surrounding areas around it. At that point, the UTM concept did not really exist. There was a high demand for operations of these small vehicles in the low altitude airspace. We knew what the community and industry wanted to do, but we were at that point trying to figure out, like, okay, how do we get there? It seems like it was a long time ago, but it was not. It was only a short 6 years ago. And if you look at the amount of progress that I think the whole community has made over such a short interval, remember, in aviation, 6 years is a short interval. So in such a short time, the amount of progress to be able to essentially culminate in the 2019 flight trials over downtown Reno and downtown Corpus Christi, Texas, to have the system maturity and reliability to get the appropriate COAs established, it sort of like speaks to the great achievement that I think you all have made. And I think just want to be sure that as we go through today's proceedings, we remain cognizant that the work was done over sort of like a high tempo progression and impact over a very short interval of amount of time. Next slide, please. However, one thing I do want to point out that is, as we embarked on the UTM concept design, that is not going to be ending. Because what the small UASs and the large UASs established as sort of the initial emergent operations about 5-6 years ago, that progression of emergent operations in the future has been speeding along pretty well. And if we look at the future of the airspace, it's going to be changing quite a bit. Not only will we have the standard, commercial transports in the Class A airspace, but even in the commercial transports, that ecosystem is changing. As Jay Wu pointed out earlier in the introductory remarks, within NASA Aeronautics, spearheading quite a bit of new vehicle technologies, such as low boom supersonic aircraft, subsonic fixed wing aircraft with different configurations, highly electrified aircraft. All of them will have different performance characteristics, different requirements. If you look at the upper E, you have HALE UASs operating. Even in the lower altitudes, you have urban air mobility, coming along quite well. You have the thin and short haul markets is getting established, as well as the small and large UASs operating for a myriad of operations. So essentially, this future construct is establishing, primary drivers for the future in terms of the diversity of the operations and its inherent complexity, as well as the density and the volume. So essentially, that sets us up for being able to build upon what we've done in UTM to be able to address the future needs of the future airspace users in emergent operations. Next chart, please. So what we're really doing is essentially building up on the UTM construct and trying to go to these various epochs. So if you look at the evolution of airspace operations safety, we're currently at epoch 3, which is, we do the trajectory management and we're trying to do the efficiency and proactive planning. But what we have learned through the airspace portfolio for all the development projects we've done for next gen, such as the various ATDs, the various safety projects, such as the loss of control prevention and also UTM, to essentially build towards the FAA's 2035 concept, where you do a lot of service-oriented architecture for tailored mission-oriented services, trying to move to a very collaborative, connected environment. And of course, we're setting up the NASA's 2045 NAS transformation vision to be able to do this highly complex, scalable, and dynamic adaptation of the airspace in order pretty much to address what you saw in the previous OV1. How do we safely manage all the different users while providing tailored services to be able to optimize their individual performance and sort of move to a very mission-oriented architecture. And of course, this future will set us up for it to be essentially a very highly automated, MLAI-based, dynamic, robust, and for performance and safety. Next chart, please. So what you'll see going into the future is that UTM architecture that I think you all know pretty well being expanded, where together with our FAA partners, as well as all of our industry partners, you all, and as well as our international partners, we would like to be able to essentially move towards enabling a safe, scalable airspace access for diverse mobility solutions. And this sets us up so sort of being able to establish these traffic management systems for that sort of live outside the traditional NAS. They're still owned, the NAS is still owned, operated, and regulated by the FAA. However, some third-party services can be established just like we have done through UTM. So essentially, we are using the UTM construct to be able to, as a first scenario, to address the urban air mobility and advanced air mobility solutions and requirements through the NASA's AAM project and the various national campaigns that are beginning to take shape and will be flying very shortly. And we want to extend that to be able to provide, very digitized commercial transport solutions, being able to move that to address of supersonic transports, highly electrified systems, and you name it. So essentially the UTM construct to be able to move to those sort of federated service-oriented architecture for the future NAS is what we will be using the UTM construct. And I think UTM's laid this foundation to be able to enable us to move towards this future construct. And of course, in-time system-wide safety assurance will be baked in from the get-go. So we are very excited, not only for celebrating today's achievements in terms of what we all collectively have done in UTM for the last 5 years or 6 years. However, we are looking forward to partnering with you all as we move towards the transformation and as towards all the future demands of air mobility. So with that said, look forward to continue an interaction with you and continued engagement. Back to you, Jay-Woo.
Great, thank you, Akbar. We certainly look forward working with you and with the community for the next iteration and then advancement of the UTM and its inspired systems. So next, we have project overview and history. And this will be given by two presenters. I will start going through a few charts, and then the UTM chief engineer, Josep Rios, will address a few slides, and then I'll take it back. So let me move ahead to the next slide. So this is just a reminder of where we came from. As we started, we had this vision of defining and safely enabling future airspace operations in roughly 2025 or around so time frame for small unmanned aircraft systems, small UAS or SUAS or sometimes drone in the national airspace system. Now, so that was the vision. And then we had specific goals. We wanted to have diverse small UAS to integrate and use airspace together, even not just the vehicle types but also missions as well. And we would want to do this in a scaled manner, but safety comes first. And as we do this, we want to grow efficient system. And for US, we would like to maintain global competitiveness and then support the domestic areas. And the objectives were roughly two. We wanted to develop, validate, and airspace operations and integration requirements to enable safe, large-scale US operations. And then we wanted to come up with a prototype UTM system, which we did for future NASA FAA testing and development. Next chart. So this isn't new to you, but let me just briefly touch on what UTM is. And UTM is air traffic management ecosystem for uncontrolled airspace. For now, 400 feet AGL in Class G airspace. And we utilize the industry's ability to supply services, as Akbar mentioned, under FAA regulatory authority, where those services do not exist. So in this sense, you can say UTM is complementary to FAA's ANSP. And we want to do the first 400 feet AGL and below, but it's not really limited there, but we first start from there. And as we do that, we were to identify roles and responsibilities of the UTM participants and FAA's role there. And we prepare information architecture, data exchange protocol, software functions, and then come up with system performance requirements. So all that is UTM, and then there's a picture of what it is from the FAA on the right side. Next chart. So we support agencies' strategic goals and critical commitment. So that would be the NASA-wide. So it really starts from the NASA strategic plan that came out in 2018. And from there, NASA Aeronautics, or ARMD, developed strategic implementation plan, and it got updated in 2019. And there are several areas, and one of them is assured autonomy for aviation transformation, and that's where UTM fit in. So that would be the strategic trust, number 6. And there, the commitment is to demonstrate the feasibility of highly automated, low altitude UAS traffic management and deliver validated requirements to FAA and the industry. And we will have a chart to talk about how we met the critical commitment a little bit down the road. Next slide. So we have multiple activities taking place in UTM, and one of them would be system development and demonstrations. So under that umbrella, we develop UTM system, and we do that to meet the operational concept and requirements of service-based architecture. And what that is, we will briefly touch on in this presentation, but we will dive into the details about it in a separate presentation. And we're also to test UTM functionality in field, such as a flight demonstration and then working with the FAA UAS test sites with many newcomers to small UAS operations, as this was nascent field back in 2015. And we are there to accelerate industry development. Another area is focused flight test. And here we actually characterize the performance of specific challenge areas. And these challenge areas would include beyond visual line of sight, urban area operation, and so on. And finally, there's accompanying simulations and analysis where we evaluate the scalability and robustness of the concept in simulation setting. Next slide. Now, here I will hand off to UTM Chief Engineer Joseph Rios to talk about UTM in more detail.
Yeah, thanks, Jaewoo. That was a great overview of kind of the programmatics and overall project goals that we had with UTM. I'm going to talk a little bit now about how we went about trying to solve the basic problem of enabling large-scale, safe, efficient access to the low-altitude airspace for small UAS. It was kind of a greenfield problem for us, within the confines of the existing NAS. How are we going to do this? And one of the things we noticed very quickly was that it meant a lot of things to a lot of different people. So there's this theory of non-one-sidedness where everyone's view kind of matters, and you need to take them all into account when you're trying to figure out what the truth or the solution might be. And that brings us to this, this age-old tale of, a bunch of people locked in a dark room trying to figure out what this thing is that they're with, and it happens to be an elephant. Depending on where you're touching the elephant, you may have a different sense of what it might be, right? If you're touching the tail, you might think it's just some rope. If you're touching the ear, you might think it's a big fan. If you're touching the leg, you think it's some kind of tree. So you've got to place all of these things together to figure out what they might be. So if we can click ahead once more, that elephant for us was UTM. And all of these perspectives were the folks that had some contact with what UTM was going to be. And understanding what their use cases were, what their requirements were, what they thought it should be, what it needed to enable, was really where we were at the beginning, trying to build a coalition of folks who were going to help us on this journey to figure out what UTM was. And if we go to the next chart, what we started with was a small meeting of folks from industry and from government to think about, all right, if we want to enable small UAS access to the low altitude airspace at scale, safely and efficiently, what are some of the things we have to worry about? What are some of the things that it should do or should enable? And we came up with these 5 core operating principles at that time. This has expanded since then, right? There's further things that we think UTM should do, but this is what we started with when beginning to evolve the system. And going from left to right here, what we're talking about is, the first thing UTM should do is hopefully enable drones to not hit each other, right? So let's keep those things safely separated as much as we can with UTM. Secondly, let's make sure that the drones don't interact negatively with existing traditional operations, right? So let's keep those things separated as much as we can. And as folks are flying these drones in the airspace, we want to make sure that they're all identifiable. All the components are identifiable in the system. So we want to make sure that you can identify what that drone is, who that operator is, and that they're lawfully operating in that airspace. The fourth principle going across the line here is to make sure that we think that this is going to be a highly automated system. And being highly automated, we need to focus on data exchanges, and we need to make sure that the understanding of the airspace through those data exchanges is the same for everybody. We can't have misinterpretations or misunderstandings in terms of what those data are or what they're representing. And finally, we need to make sure that there was access to public safety use cases, right? So if we have a future airspace where there are small drones delivering hot dogs to people, we need to make sure that a police drone or a fire drone that's off to a critical mission has access to the airspace to complete its job. So making sure that these 5 principles were covered, we thought we would have a good start to figuring out what UTM should do. We'll go to the next slide. I think folks that joined this this stream today probably have a good idea of what this architecture is, but I'll cover it briefly here. We have a whole session later on the system architecture and data exchanges, which I would definitely welcome you all to attend. But at a whole, the fundamental concept that we evolved to with the FAA and industry was that there should be certain functions that the FAA performs as the regulator and service provider in the airspace, but there are certain things that industry can also do to help manage that airspace. So you see that line down the middle here in the architecture, where on the left side we have the FAA development and deployment of systems, and on the right side we have industry deployment and development of systems. In the middle, there's some stuff that's either shared or is TBD in terms of where it would land. And it's this architecture that drove us forward ultimately to test it out in the field with partners and work out these concepts. Again, we'll have a deeper dive on this architecture later on, and I would welcome you to attend that. Some of the key pieces are these UAS service suppliers. These are the providers of services to the small drone operators that would enable them to have a common awareness of each other in the airspace. And they would also enable the sending of messages, time-critical messages to those operators as needed, right? So this would allow the operators to begin to collaborate in managing their operations in the airspace without overburdening the FAA systems, right? We don't want to have to put a bunch of human controllers in control of, small drone operations. Nobody wants that. So how do we make sure that these drone operators have a way to know about each other, especially when doing beyond visual line of sight operations, for commercial purposes, for example. Supplying other services to those would be supplementary data service providers. These could be a wide swath of things. They could be mapping and terrain data, could be surveillance data, could be certain navigation data or communication data, or safety data, whatever the services might be to enable missions for small UAS. And always a role for public safety and the public to have access to the system as appropriate. So this architecture evolved, and we were able to test it out over the years with UTM. So we'll click ahead one more slide. So how did we go about testing this? Did we click ahead one more slide? There we go. Okay. How did we go about testing this? Well, we decided to do it in terms of risks. So we, separated this into 4 separate, increasingly more involved risk environments. We call these TCL 1, 2, and 3 in terms of testing them. So we started in the lowest risk environment we could think of, right? This was line of sight operations in a rural environment, not much people or things on the ground for us to worry about, not much stuff happening in the air for us to worry about. How do we begin to think about sharing information in an environment like this? That then propelled us into TCL2, where we stayed in the same kind of environment, but we began to allow beyond visual line of sight operations. So now that exchange of data and situational awareness and intent exchange becomes more and more important. Moving into TCL3, we're doing those same kind of operations, but now in more of a suburban environment. So there is likely more activity in the air. There's definitely more activity on the ground in terms of people and structures. So what does the UTM system have to do to make sure everything stays safe in this environment? Finally, TCL4, which we tested in August 2019, looked at beyond visual line of sight operations for small drones in an urban environment. So as we go into that environment, we get more and more operations. What does UTM need to do? And this is the progression of testing that we did in the project. Next slide. This gives you a historical perspective of how we did that testing with TCLs. Again, in 2013, UTM was an internal seedling project at NASA Ames. We built kind of a following behind that, and folks got behind the idea and began some workshopping with partners, some initial prototyping, behind our walls, some initial testing with partners as early as November 2014. You can see we were testing there with 3DR at the time, and getting some data exchanges with an industry partner and our system. We had our first live flight under the NASA UTM system in May of 2015. We did multiple operations in July of 2015, and then the TCL progressions began. We flew TCL-1 at Crow's Landing in California in August of 2015. We had a national campaign at all the test sites in 2016. That led us into our TCL-2 demo in Reno. We've been working with the FAA continuously through that time, but we formalized our research transition team plan around January 2017. We had another national campaign, TCL-3. You'll see our friends in North Dakota there on a frozen lake. We tested at all 6 FAA test sites in May of 2018. And then summer of 2019, we concluded our flight testing with partners in TCL-4 in Nevada and Texas. And with that, I'm going to hand it on back to Jaewoo.
Great, Joey. Thank you for walking us through the, in a way, memory lane. It's always good to see what we did on the timeline, and oh my, we did a lot. Okay, let's move on to the next slide. So as it was mentioned a few times earlier, the UTM project, it wasn't just NASA's thing. We did it together with the FAA and then the community, extensive community out there. And we had a partnership strategy there. And we wanted to lead where we can, and then leverage where the industry or academia already advanced into, and then collaborate to really make the whole thing move forward. And as you can see at the center, there's a NASA UTM project. And to the right, there's a purple area. I mentioned the research transition team, which is a NASA FAA collaboration and the mechanism to transfer the research outcome to FAA for consideration for implementation or further development. And then also industries there to work things out with us technology-wise and integration-wise. And a part of the industry, you may see the dotted line there. We did have what's called a Space Act agreement, where they bring something to the table, and we bring something to the table, and then we work out the data exchanges and such. And those Space Act agreements worked out really great throughout the UTM project. And there's also FAA UAS test sites. There are 6 test sites we worked throughout the life of the UTM project, and they're wonderful organizations to work with. They're always eager to jump on and fly and help. So that has been great. And we also have kept in touch with DOD and then DHS so that we are aware of the security need, and then also other government agencies as well. And to the upper left side, we have a standards and research group engagement, and the ASTM we will discuss a bit further, but we have a working group developing what's called the inter-USS standard. And then we engage with the ANSI and then CTIA and Science and Research Panel as well. To the lower left corner, that's the international organizations, and we worked with JAXA, did great things under their DNet effort and connecting that to our UTM system, and there will be opportunity to talk about that a little more. And we also engage with the JARAS and ICAO as well. Next slide. So the UTM really wouldn't haven't gone to anywhere if the community didn't accept the concept and also associated technical capability level. And the way at least we see the FAA and the community acceptance is following. First of all, the FAA UTM pilot program, it used the NASA UTM federated architecture and commercial services providers partner with NASA. And what this federated architecture is, our chief engineer, Josep Rios, is going to discuss this further in a couple presentations down. And you may know that the FAA already has stood up low altitude authorization and notification capability, or LANS in short. And that's where it used to be cumbersome process of flying Part 107 operation. With this LANS capability, it became really streamlined. And you should see the number of application that was going through the FAA system for Part 107 operation before and after LANS, number of operations, I should say. And then that has been a big improvement. And FAA published UTM concept of operations. First two versions are out. We're working on the third version. And then there are several rulemaking that came out, most recently remote ID being one. And there's a national implementation plan informed by NASA UTM. And there's growing market of U.S. service supplier. We call them UTM graduate because that UAS service supplier, the term itself and what it should do really came out of the UTM effort. And one of the few of the names, it's not endorsement or anything, but just they are the AirMap and Aerox and Amazons and others. They really got going with the USS concept. And we also have a domestic and international standards group. They are adopting NASA UTM and adding further definitions of it. And there's a chart to dive into this further. And previously mentioned DHS and DoD, they're adopting NASA UTM construct to support their missions. And all this acceptance of TCLs and UTM is really well summarized by this quote from Mr. Steve Bradford, Chief Scientist for Architecture in NextGen FAA. And he says the FAA is already deploying a preliminary version of UTM. It is the wave of the future, and we are using UTM to lead that way. So this is a great way to capture the community acceptance, and I really appreciate Steve allowing us to use this quote. Next slide. So earlier I touched upon programmatic side of the NASA. So this is perhaps a little bit dry for many of you, but it's important as a project to talk about this. And this is how the UTM project met the critical commitment, which is demonstrate the feasibility of highly automated, low altitude UAS traffic management and deliver validated requirements to the FAA and industry. So it's two-part. So how did we demonstrate the feasibility of highly automated, low altitude UTM? We did it in four ways, broadly speaking. We held workshops and working groups to develop use cases and scenarios. And together, we developed the data interfaces and protocols to support the use cases. You can consider those as APIs as well. And also together, we demonstrated use cases via collaborative simulations and flight tests. And finally, we incorporated industry leaders in flight tests to nurture their development and show state of the art. So this is how we demonstrate the feasibility of highly automated low altitude UTM. The second part is how did we deliver validated requirements to the FAA and industry? It's got multiple parts as well. throughout the UTM project, we produced technical memos and documentations to really transfer the technology to FAA and the public as well. A few examples are here, not exhaustive list, but here's a USS specification would be one. That's a NASA tech memo. And there's a USS framework for authentication and authorization. And Joey will elaborate this further, but if one is relying on service, whether that service is what it should be, really need to be going through the authentication and authorization process. So this was a critical part of the UTM ecosystem. And we have a notion of the strategic deconfliction. And in order to do that, what kind of system requirements are necessary, we published on that. And strategic deconfliction is really a key part of sharing the airspace without running into each other. And there will be a discussion of that as well later today. And we published the USS checkout process and also automated management of small UAS communications and navigations contingency. So those are part of the documentation we produced. And then we field tested application programming interfaces, or API, published via GitHub. And we also had a supporting analysis of test result published via technical memo and conferences. So those are how we delivered and validated requirements to the FAA and industry. Next slide. This is a little bit busy, but let me use this chart to really talk about the influence UTM has made. So I'll start from the clockwise left top. That's there's a ASTM working group for ground surveillance, and earlier UTM project produced UTM surveillance API, and we also provided TCL detect and avoid results, and how we do conflict management in terms of modeling. So that's really handed over to the ASTM working group to develop further. And there's another working group for UTM services. There's a USS specification and authorization authentication technical memo provided to them. And there's ongoing discussion about so-called inter-USS standards in development. And we also engaged with the CTIA UAS working group. We provided communications and navigation results, and then modeling and requirements. And there's an unmanned aircraft safety team, and how we handle off-nominal reporting and UTM hazard analysis went there. And we also work with the ASRS, and now there is a UAS operation specific form being made available. And the ASTM, another working group on detect and avoid, we provided a DAN result and also conflict management and model. And now it's 6 o'clock. We have a IEEE V2V or UAS working on the how to do V2V, and we produced earlier V2V results in our TCLs, and we provided that to them. And the remote ID working group, this was before the rule was finalized. We tried several different concepts, and provided our understanding to that group, and then the standards of that is available now. And we're working with DoD and DHS so that the federated USS prototype is developed, and they have a separate requirements, if you will, compared to the civilian operation. So that's the part that we worked on together. And finally, there's a UTM RTT. Through that mechanism, we provided flight information management system prototype. along with the USS checkout process and T-cells 1 to 4 ConOps and use cases. And we also had international engagement and influence with JARUS and ICAO and others. And we actually have another slide to talk about international impact, which is the next one. So we did have a international impact of UTM. And if you look at the upper right corner, there's a ICAO, and there's a common framework with core principles in development. And we provided JARUS input, and it really became an annex of SORA version 2.0 discussing UTM services. And lower right, ASTM, as you know, there's a new specification for service provided under UTMs being developed. And we work with the ISO about requirements for UTM services and service providers. And lower left, there's a GUTMA, that's a Global UTM Association, and map of global UTM implementation from that organization is shown, and their worldwide implementation is shown there. And upper left corner, there's a FAA UTM ConOps 2, version 2, and then EASA on high-level regulatory framework for the use space. So in summary, UTM has directly influenced the regulation and policy, concepts and architectures, and standards across the world for implementing UAS traffic management. So that would be the summary of our impact at international level. Next chart, please. It's always hard to say goodbye, but UTM project ending doesn't mean UTM construct is ending. In fact, UTM construct is continuing strong, and as UTM project ends, there are several places in NASA and FAA and that UTM construct is being used. There is a ATM X project at NASA. There, we're adopting the UTM construct and apply lessons learned to mature the concept of operations for applications such as urban air mobility and then upper class E traffic management. And there's another NASA project, AAM, and there we expand the UTM architecture for testing national campaign associated with the urban air mobility, and then performing high density UAM operations R&D. We continue to work with DoD and DHS to extend the UTM code base for managing government agency operations with an emphasis on security. And finally, FAA has been using the FIMS part of code bases to support the UPP effort. And in summary, the UTM concept has been very successful in evolving to new applications and springboarding other projects within and internal and external to NASA, really. And next slide. So this is the final overview and history slides, and captures the UTM project journey from 2015 to 2020. And Joey mentioned, in 2015, the small UAS industry was just beginning to accelerate and was wondering about, if everybody flies at the same time, how can we manage that safely? So the NASA UTM team and then other members partner with FAA, industry, and academia, and we created a concept and really developed it to meet the stakeholders' needs. And we eventually built a prototype UTM system, including federated services, and we tested that through a series of increasingly complex events, which you will see later today. And industry created business models around providing UTM services, and they're really taking leadership in standards development. And the FAA, as you know, is embarking on the UTM implementation program that will unleash, in a very disciplined way, a multi-billion-dollar industry. And now, in 2020 and 2021, the UTM concept is the springboard for managing UAS in all airspace domains, and this will influence the future of NAS transformation. So with this, let me end the UTM overview and history presentation and move on to the next presentation. And in this presentation, Jeff Homola, who has been NASA FAA UTM RTT Concepts and Use Cases Working Group Co-Coordinator. And I'd like to invite Jeff to talk about UTM concept and use cases. Jeff?
All right. Thank you, Jay. Thanks to you and Joey for providing a nice overview for us here and a trip down memory lane, like you said. So I'll get into the UTM Concepts and Use Cases Working Group. Like you mentioned, I've had the pleasure and honor of serving as the core coordinator of the NASA FAA UTM RTT Concepts and Use Cases Working Group, along with my co-lead, Sherry Majaritz, on the FAA side. It's been a really great experience so far. And I'll provide you an overview of our activities if we go to the next slide. Okay, so I'll spend some time going over kind of the overview of the RTT itself, and then kind of how the CWG, which is the acronym for the Concepts and Use Cases Working Group that I'll use from now on, give kind of an overview of the internal workings of that group, and then kind of the activities that led to the publications that came out from our engagements, as well as some of the more focused test involvement that we were engaged with as part of the TCL testing regime, and touch on a few areas of future work and summarize with kind of the overall overview and the impact that this group had on the overall UTM work that's been ongoing. So if we go to the next slide. Okay, so it's been touched on a little bit so far already within the previous presentation. The RTT, or Research Transition Team, is basically a mechanism for the FAA and NASA to really work very closely together, hand in hand, on a particular area, and it allows NASA to kind of formally transfer the fruits of its labor, or the kind of final products of the research that's been going on, kind of be able to formally transfer that over to the FAA through this mechanism here. Like was mentioned, it's really been a joint undertaking for UTM. This is really the key area for us to be able to interact with very closely in developing the UTM concept, as well as the other areas that feed into kind of the overall UTM umbrella in here. And so for this RTT, it was initiated around 2016. There were 4 key groups that were defined to basically comprise the RTT. And you can see it here in the graphics. Concepts and Use Cases was one of the groups. Data Exchange and Information Architecture is the other group. Communications and Navigation, as well as Sense and Avoid. And each of those other groups will have presentations that will follow this one as well, to get a little bit more details on what went on into each of those working groups and the products that came out of there. And basically the document that was kind of guiding the work and the deliverables that were formulated for this RTT was captured within the Joint Management Plan. And that really kind of formulated the research transition products, the deliverables, and the schedules that really went into basically what each of these working groups would deliver at the end of the kind of the formal working period of the RTT. And that the Joint Management Plan was signed in 2017, but of course a lot of the work had already been underway prior to that, and that's what I will get into here, at least for the Concepts and Use Cases Working Group as part of that RTT. If you go to the next slide, please. Okay, so the CWG was chartered with collaboratively defining the UTM concept. So, working between NASA, the FAA very closely, as well as with industry, to be able to define this concept through the development of use cases that really capture the essence of the concept and touches on really important elements for the concept to be able to address. And these use cases and the concept itself needed to ultimately span the range of UTM operations and environments that we were envisioning from the early days. So we already saw kind of the TCL levels 1 through 4 and kind of developing use cases that really capture that range. And so through the process of the RTT and the development of the concepts and use cases working group worked to identify the important information flows and exchanges that are needed to enable these types of use cases, the supporting architectures, the roles and responsibilities of basically all the stakeholders that are interacting within the UTM system, and this is really taking it from a number of different perspectives, which is really important for us as we kind of move forward through UTM, is understanding kind of the needs and requirements for all the different stakeholders and individuals and entities that would be interacting with the overall UTM ecosystem. And we worked really closely with the other working groups as well. So as part of this process, we were engaging with the other working groups, and we basically kind of fed into each other's work and made sure that we had kind of a cohesive message coming out, and that it was incorporating all the different insights that we were gaining from all the other groups and their interactions with industry as well. If we go to the next slide, please. Okay, so for the CWG itself, it was a pretty small group. We were a little bit different from the other working groups. We had kind of a small core team between NASA and the FAA. We had a number of regular meetings and, of course, plenty of ad hoc meetings throughout our time together. And that was to kind of help build the use cases as we were kind of moving through each of the deliverables. And as we were kind of holding these meetings to help build out the concept, we would invite different people from different areas to provide input and have a good discussion on particular topics. And so the number of attendees and the backgrounds of the people that were in attendance fluctuated and were pretty diverse over time. And like was mentioned, really the discussions were centered around the development of the use cases and really trying to get that insight and perspective from the different people that we were pulling into the conversations. And the idea was to really highlight particular concept elements that would help us kind of clarify and refine particular assumptions and these roles and responsibilities and the processes that were part of what we were envisioning for the UTM environment, and really intending to be captured by these use cases that we were developing and publishing. And like I mentioned before, really participation and coordination amongst all the RTT leads and all of their members in the CWG efforts was really a key and important part of the development process for the concept in general. Okay, if we go to the next slide. Okay, like I mentioned, as part of the joint management plan, we had a number of research transition products that were basically due out from each of the working groups. And for the concepts and use cases working group, we had a number of publications that were kind of our deliverables that were captured either through a use case package or an overarching concept of operations that were published. There were 2 that were published so far. And this is just the graphics below, kind of give an example of what was coming out of some of the use cases. And we'll get into some more details of those use case packages and ConUps here in a moment. If we go to the next slide. So here's basically a graphic of all the publications that came out of the CWG as part of that the research transition products within the JMP. So on the left-hand side were the use case packages that we came out with, And on the right-hand side are the formal overarching concept of operations that were delivered over the past few years. And so if we go to the next slide, we'll get into a little bit of the use case packages. And so as part of our deliverables, there were 3 use case packages that were developed by the Concepts and Use Cases Working Group. Each package was intended to be kind of encompass the type of environment and the concept elements that were related to a particular UTM environment that we had defined as part of these technical capability levels. And so spanning from TCL 1 through 4, increasing in complexity and the types of missions and operations involved in those and how they varied over the different TCLs. And so in total, we came out with 3 use case packages. And if we go to the next slide, we can start looking at the first package. And the package number 1 was a little unique, a little different from the others in that it really covered both TCL 1 and 2 environments. It was just kind of a matter of timing and how we were all getting engaged at the moment. And this first use case package is really unique in the sense that it really set the stage for us. You know, there were earlier research papers that were published on kind of the overall UTM concept, and then here is where we started to get a little bit more into the details of the concept. And so for this first use case package, it really started defining some of the initial kind of key elements. You can see some of the graphics that I put in here that came out of the use case package, where we're really talking about some of the fundamental pieces of kind of the workings of the UTM, the concept, as well as some of the information exchanges. And so we can see these operation volumes and the breakdown of the different geographies that went into it. And of course, this has evolved over time now. So as where we are kind of post TCL4, we can kind of see that things have already, evolved since then. But these were some of the early kind of stakes in the sand for the UTM concept and the different elements that were part of it. So this use case package had a total of 5 use cases. TCL1 was kind of just setting the stage for a more simpler type of visual line of sight types of operations between 2 operations or 2 aircraft. And then the TCL2 use cases that were within this first package introduced a little bit greater complexity as part of that TCL2 environment and that progression from TCL1 into TCL2, and included 4 use cases where we started to touch on really the key areas that most of us are interested in terms of beyond visual line of sight operations and how those are taking place near airports. Looking at prioritization of operations within the airspace, particularly for medical types of operations, which has, that was one of the key principles that Joey touched on a little bit earlier, is the accommodation of these types of operations within UTM, as well as looking at conformance violations in controlled airspace. So that was package number 1, covering TCLs 1 and 2. That was published back in 2017. And then if we go to the next slide, we can see the successor to that use case package. This was number 2, use case package number 2 that covered the TCL3 environment, where it was starting to get much more complex, I would say. And there was a bit of a explosion in terms of the topics to be covered at this point. I think this is where we really hit our stride and we're able to start incorporating a lot of the lessons learned that we already had through TCL 1 and 2. The other working groups are really in their stride at this point, as well as industry being on board, particularly after the number of tests that we had so far. So this use case package 2 is really starting to get at some really kind of meaty topics here. And it was published in 2018. A number of use cases that were starting to touch on Continuing along with the beyond visual line of sight types of operations, but now looking at kind of separate landing and takeoff locations. This is where we also introduced the negotiation between operators and also incorporating what we were calling dynamic restrictions at the time. We're calling them UAS volume reservations now, but that same concept was starting to be included a little bit more directly here, and how operators basically can kind of negotiate in the presence of these types of dynamic restrictions. This is where we also brought out the really important area, as well as looking at the U.S. interactions with manned aircraft. So this is another important area for us to address, and has been kind of a common theme throughout. And we also introduced the high density UTM operations, which kind of set the stage for the types of TCL3 and then leading into TCL4 types of environments that we had envisioned earlier on. And then looking at rural deliveries under the Mode C veil, and small UAS operators in flight loss of performance capabilities. So this is again looking at some of the prioritizations and the messaging that can go out to the UTM system to provide operators and other stakeholders with a situation awareness to be able to kind of know when something's happening within the airspace, and being able to accommodate and plan according to those messages and that awareness. Okay, and this set the stage for the third package that was published. If you go to the next slide. This was the third and final package, which captured the TCL4 environment. And this was published in 2019. And this is kind of the, like I said, it was the final one. It really captured the key elements of what we were considering for kind of the more complex environment that was captured through the TCL4, what was laid out there. So again, beyond visual line of sight operations were kind of a key area to continue working with. And now we're starting to look at those types of operations within facility maps, so kind of near airports under the defined facility maps, and so how those operations can take place, and the interactions that need to occur to be able to safely manage those types of operations in that area. And also started to look at some other aspects of UTM that kind of weren't really part of the earlier conversation, where starting to look at now the ability and the need to be able to do kind of historic queries by authorized entities for UTM information. So if there's an incident, for example, we can do basically a query of the pertinent information to be able to build up, again, kind of what happened in that situation, to understand, what were all the important pieces in there, and what can we get for that data from the UTM system and the operators. And so looking at how that can be queried, and especially making sure that that's only by authorized entities, and continuing on with the kind of priority type of theme that's been part of the overall concept so far, looking at urgency distress conditions for small UAS, where they have to land at alternate landing, and doing that through coordination with the UTM system. So again, allowing others in the airspace to know that there's a situation taking place, and then that the operator and that vehicle able to land in a kind of unplanned area or alternate area, but that is kind of predefined and well managed through the UTM system. And again, continuing on dynamic restrictions, what we started calling UAS volume reservations at this time, kind of use cases that were covering those types of airspace structures in controlled airspace. And the final one here, kind of Jay touched on it a little bit earlier, looking at kind of accident reports or reports to the FAA due to UAS flight incidents. And so starting to put that out there in terms of being a mechanism and a capability for the UTM ecosystem to allow for these types of reports that can be build a historical picture of events that happened within the airspace. Okay, so that was the last use case package that was published, and in the intervening times there was a concepts of operations that were being worked on. Those use cases really meant to feed into and provide a lot of the background that were needed for these overarching concepts of operations. And so there were 2 that were published in total so far. It's going to continue to be a work in progress. And so these are the first 2 that were published. First one back in May of 2018. It was really the first formal publication setting out the joint vision for UTM in this type of format, which was really an important milestone, I think, to be able to have this document out there. Really shows the commitment and the drive that went into not only producing the document, but also kind of where it's leading us as a UTM community. So it was a really important milestone to be able to bear witness to, and it really established the initial framework and definitions that were kind of built upon what we had been working on throughout the RTT, but here was more formalized within the ConOps for covering like the notional architecture, the roles and responsibilities of the different actors and entities for UTM, and presenting the airspace management philosophy, and especially with respect to safety, security, and equity and fairness. And that document included 8 illustrative use cases, kind of building upon that work that was going into the use cases at the time as part of the other use case packages, but presented a little bit differently as part of this particular goal for the overarching ConOps. So that was version 1, published in 2018. And if we go to the next slide, version 2 was published not too long ago in March of 2020, and this was an update to version 1 basically, and provided this kind of updated view of the UTM concept, again kind of informed by all the work that had been going on through the RTT, as well as the engagement with industry related to that. And so this one started to look at operations of greater complexity, especially in controlled and uncontrolled airspace. And this is where we started to expand that discussion a little bit more on performance and airspace authorizations as part of the UTM operations. This is where also remote ID was introduced for UTM, and then expanded discussion on safety, security, and equity. And this one included 5 illustrated use cases as well. So that's the second one that was published last year. And like I mentioned, these are going to continue to be published in the future, and I'll touch on that in a little bit on the future work. But that's it for the overall deliverables and publications that came out of the Concepts and Use Cases Working Group. But that really wasn't the only thing that was being worked on. So if we go to the next slide here. There was also involvement in our kind of formal TCL testing that was going on, kind of more on the NASA side. But the work of CWG was kind of helping to influence some of that testing and making sure that our tests and the concept development were aligned as we were working through that process. And so, in general, flight demonstrations were really a key means for us to be able to test different aspects of the UTM concept, but more importantly, in these real world types of environments with actual operators and the service providers actually implementing the services and seeing how they all work together, and then making sure that the concept that we had been developing so far was in line and able to enable these types of operations that we were envisioning for the different TCLs. And so for TCL3, we had actual dedicated tests that were part of the concepts area, which I'll get into in a little bit. And TCL4, really the scenario foundations for what were run came from the concepts and use cases working groups. And then as the FAA was undertaking its testing as well as part of the UTM pilot program, the UPP, there were certainly concept elements that were incorporated in that testing as well. So definite relationships between this group and the testing that was carried out by both NASA and the FAA. So if we go to the next slide, we'll talk a little bit about TCL3 demonstration. Like I mentioned, there were dedicated segments or areas of TCL3 that were dedicated to kind of concept elements. And so there were a total of 5 distinct tests that were included as part of the the statement of work for TCL3, and you can see here they covered beyond visual line of sight landing, so takeoff and a landing and a beyond visual line of sight type of situation, and a return to launch. Also, contingency initiation. So this goes out to the messaging that goes out to the larger UTM network in times of a contingency management type of situation, and how that gets played out and managed by the operators and the UTM system and the architecture that allows for the information exchanges needed for that. There was another one, Con 3, that looked at the development of what we were calling a public portal, and this is the type of interface that's needed for situation awareness through kind of graphical means of the UTM airspace. And so we had a number of different teams developing these public portals that gave a good overview of the UTM operations and airspace as well. Con 4 was touching on kind of multiple long duration types of flights or multiple operations over a sustained period of time. So starting to look at kind of with a view towards TCL4 at this point of kind of what a day in the life of UTM looks like, and looking at more and more operations over time and how they interact with each other, how strategic deconfliction works when you have multiple planned and active operations at the same time, kind of in the same area. And then the last one was looking at different interactions when the vehicle heads towards controlled or unauthorized airspace. And at that time, we were looking at some types of an approach to messaging, kind of warning messages that would go out to the operators at certain distances as they got close to either a UVR or controlled airspace, and kind of looking at how that might work and some of the key considerations in that type of situation. So those 5 tests were defined, and there were 5 test sites. 5 of the 6 test sites conducted different sets of these tests. So a total of 17 of these kind of concept tests were run across the 5 different test sites for TCL3. So if we go to the next slide, you can just kind of see an overview of some of that testing that was involved, pulling from the data that we collected during that time. And this was a publication, I should have included here, publication in, I think, 2019 DASC. And so you can see here, I gave a small explanation of each of these tests, but you can kind of see in the Con 1, I'll just kind of go quickly around clockwise from Con 1, that beyond visual line of sight landing. That image on the left is out in the Alaska test site. So they were flying kind of a long distance from their launch point at the university to kind of a forested area, and doing landings out there, and then returns to base. So kind of making sure that we were understanding the processes and the different considerations involved in those types of landings. The right-hand side is a kind of longer beyond visual line of sight landing at the Virginia test site, and that one was, I think, well over a mile out there, and we were able to track it and landed successfully and returned. So really good experience kind of looking at how these operations were taking place, and these different landings were able to be successfully carried out. That Con 2, that contingency, starting to look at the messages that could be initiated from the operators in certain types of situations where other operators might need to know that this particular vehicle is having a situation, and looking at the messaging and the types of exchanges that are needed for letting others know, and the system at large know that this particular operation is having a contingency. So you can see this is a screenshot from one of our applications that we're tracking this particular UTM operation here, and you can see that we were receiving that message through the UTM systems and those message exchanges. Con 3 was the development of the public portal. There were a number of test sites developing it. We also had some usability studies on our side at NASA here. This is an image from one of those studies where we had one of the public safety members that were participating in this study to give us a good perspective on kind of what public safety needs are for these types of applications, and understanding the airspace, what are the information needs for them. But we included a number of other kind of non-public safety members as well, to get really a broad perspective from really the different stakeholders that are going to be involved in UTM, from the regular citizen to municipal types of people, and really a good cross section of people to get their input. Con 4, like I mentioned, was multiple operations over a sustained period of time. This is again from the Virginia test site, where they had a number of different operations over multiple hours of operations in a given day. So you can see here, this is kind of a plot of the volumes that were used as part of that, as one of the runs. And you can see it got pretty complex from a strategic deconfliction point of view, but it was all carried out very successfully, and it was a good insight into those types of situations and that environment for TCL3. And then Con 5 was the airspace alerting. So we were looking at the alerts here. You can see in the two images up at the top, those yellow markers were where there was kind of a warning that vehicle was getting a little bit too close to established airspace, whether through a UVR or controlled airspace. And then those red dots you see in there, those red markers, were indications of messages that were sent where the aircraft was in violation of that airspace. And then in the bottom right was kind of a unique and interesting capability that one of the service suppliers developed when in order to kind of maintain an operational volume around the vehicle as it was flying outside of, intentionally flew outside of its original operation volume. It would update the operation volume to the USS to kind of keep it within conformance, but to also keep it tracked through the system as kind of an active and nominal type of operation. So it was updating the operation volumes as it was flying outside of the original one. So unique capabilities. Really interesting to see the creativity from all the different operators and service providers that were participating in each of the TCLs, which I think Arvo will get into in a little bit here. And we can go to the next slide to touch on TCL4 real quickly. So TCL3, like I said, we had kind of dedicated tests that captured the concepts and that we had been working on in UTM, as well as within the CWG. And then TCL4 was a little bit different, where we really wanted to look at kind of this day in the life of UTM at a more kind of holistic level. And so rather than having specific tests or targeted tests like we did in TCL3, this was more of a scenario-based test. And the key contribution here, I think, from the CWG was that the scenarios that were developed were really intended to capture a lot of the concept elements that had been developed so far. And I helped write a number of the scenarios. We had a total of 5. I think I helped write 4 of them, and then we kind of just took one of the use cases from an earlier package and included that as the 5th scenario. But the key elements here that we were looking at for TCL4 were these high density types of operations that were part of a TCL4 environment, the integration of priority and public safety operations within that type of that environment, and the implementation of UAS volume reservations or UVRs in these types of dense and complex environments, as well as contingency management situations and the introduction of remote ID. So we'll go to next slide. I think I'm getting close to my time, but you can see TCL4, and Arwa will cover this a little bit more in her section on the TCL testing, but you can see that these elements were successfully incorporated into the scenarios and the testing that we did both at Nevada and Corpus Christi, Texas. And you can see here we reached high density operations both with live and simulated traffic. got pretty complex on the right-hand side there, down at Corpus Christi. Also, kind of basically within that type of operating environment that we introduced UVRs in response to like a simulated weather situation, and looked at kind of the procedures and the handling of that UVR in the respect of being able to interact with other operators and send the proper messaging and be able to follow the procedures kind of enabled through the server suppliers that were participating. And then another key aspect as well is having public safety and priority operations incorporated into the testing as well. So it was really key for us to include public safety operators in there. Okay, if we go to the next slide. I have two more here. So this is the areas of future work I mentioned before. So ConOps 2.0 was published last year. There were a number of comments that we're kind of starting to have more conversations to address some of those comments as part of that version 2 and leading into the update to that ConOps in version 3 that's in the current formulation stages. So lessons learned from version 2, and then getting input from the number of stakeholders in development of version 3, the overarching ConOps. And continue to engage between NASA and FAA through the RTT. We have a good working relationship and continuing the conversations as UTM continues to evolve and develop. And additional areas of work and testing opportunities are in discussion as well. So I'll do a quick summary slide, and then we can move on to the next person after me. So use case packages and the ConOps were published, defined the concept, really laid the foundations for the evolution of UTM, and our involvement in testing ensured that concept elements were explored, and they really helped frame the targeted testing in other working group areas. And the collaborative nature of the concepts and use cases working group really resulted in the development of strong working relationships that really are carrying us forward. So I think that is it for me. I think we're on time now as well, maybe a little over. So
Thank you, Jeff. Thank you, Jeff. That was a great concept working group summary. Now we're fortunate to have Mr. Jay Merkel, the Executive Director of the Federal Aviation Administration's Unmanned Aircraft System Integration Office. He's here to welcome the audience and talk about UTM importance. He's actually responsible for facilitating the FAA's safe integration of drones into the NAS, and he coordinates across the FAA's lines of business and staff office to ensure all UAS integration activities and efforts are aligned with the agency's overarching mission. Director Merkel, thank you for joining us. Floor is yours now.
Well, thank you. And I think that's the first time anyone's ever called me Director Merkel. Please, in the future, just call me Jay. I'm not that formal. Excuse me. So thank you for inviting me to speak here today. It's always an honor to speak with the NASA team and the larger NASA team, including industry. The work that you have done in UTM and continue to do is not only groundbreaking, but is really forging the future of aviation, not just at the low altitude, but potentially at much higher altitudes. And we at the FAA are very grateful that you continue to do this with earnest and with a very, very positive approach, and a very collaborative approach as well. And thank you especially today to Anna and Joey, who made sure that I got here on time and everything is working well. So as it was mentioned, I want to talk a little bit about the importance of UTM to the FAA. So since the publication of the remote ID rule, unfortunately, there have been some people who misinterpreted the removal of a network capability from that rule, that A, the FAA doesn't support network information sharing, or B, the FAA has abandoned UTM. Neither one of those is true. We're very, very supportive of UTM. In fact, we are working very hard trying to figure out how we can accept UTM services under our regulatory infrastructure, not just as ATC services or ATO type services. You can read the preamble to the rule and it will give you a long description of why we chose not to do network. But the bottom line is for remote ID right now, we just couldn't get to network the way that we had originally conceived it. And we need to take some time to figure that out. So we're still very, very strongly supportive of a federated UTM system. We continue to be active in organizations that promote UTM like GUTMA. We continue to promote harmonization of UTM standards across the world. It is a very, very vital technology that we will need when the scale gets to the point that the use of these aircraft scale to the point that we can no longer provide safety in the airspace through things like separation of large volumes or things like that. So where does that leave us and where are we headed? Jeff mentioned that we're working on UTM 3.0, and thank you to everyone who's supportive of that. I was with that team last week, and we will continue to support UTM 3.0, the next gen organization, and throughout the FAA, we will continue to look for opportunities to support UTM services. It looks like to us the next UTM service to come out will likely be strategic deconfliction based on a standard that ASTM is working on. And we're very much looking forward to that. So again, thank you for the opportunity to talk to you today. Keep up the good work. Know that the FAA does indeed value UTM and support UTM and plans to continue to work with you to make UTM a reality. So I think I went just a few minutes short, and I'll turn it back over to, am I turning it over to Joey, Anna? Who am I turning it to?
that would be me, Jae-woo. Thank you, Jay.
Oh, okay. Thank you, Jae-woo. Back over to you, Jae-woo.
Sure. I really appreciate your kind word and strong support for UTM construct moving forward, and looking forward to working with the FAA in continuous and harmonious manner. Now we'll move on to system architecture and data transfer, and this would be addressed by our chief engineer, Joseph Rios. Joey, floor is yours.
Great, thank you, Jae-woo. Just a quick check on the technical stuff. Do I see the screen here, Anna? Is it shared? Here? There we go, it's coming up now so I can see what I'm talking about. So welcome everybody. Thank you, Jay, for the words from the FAA side. I think it's really important for everyone to kind of understand how, you know, we really do work closely with you guys, and you know, we're all working to try and improve the NAS overall and access to the NAS. So all of your words are very much appreciated. Thank you. So I'm going to talk a little bit about the UTM system architecture and some of the data transfers that happen within the system as built and tested with partners via the UTM project. Some of this has evolved in thinking. Some of it has, changed as it goes global, so to speak. But I want to give you a sense of kind of where it came from, how that evolution started, how we got to where we are with this architecture a bit. And for folks that haven't seen these things, we'll get kind of a walkthrough on how the system actually works. So we can go to the next slide. Just a quick little outline. I'll talk a bit about our subgroup with the research transition team at the FAA. Talk about federated airspace management as a whole, as a concept. What is it? Kind of what does it mean? Look at that system architecture in a little more depth. Go through a simple use case of some of the data and protocol exchanges. and then talk about some of our research findings and the publications and where you can find them. Look towards the future of UTM and XTM systems, and then talk about the summary and impact overall of this aspect of the work. So I'm going to go to the next slide. This is a graphic from our TCL3 activity, and I think it just really is indicative of kind of the technologies involved in getting small UAS into the low altitude airspace. You know, you've got vehicle-to-vehicle communications, and you've got navigation and air-to-ground links, as well as detect and avoid, and future navigation technologies need to come into play. If we click ahead once more, where I'm going to focus is on that stuff up there in the top. And that's usually at the strategic scale, how these operations share their intent, share their operational information with each other in order to give us an initial layer of safety in the airspace and allow access in a cooperative way for all these operations. And really, this was the focus, what you see in the red box, of that of this specific subgroup in our research transition team. So working closely with our FAA counterparts to develop the concept in this regard, to figure out what technologies are going to be needed on the FAA side in the future, and then to have us have a platform to begin talking with our industry partners on these specific topics was really the focus of this working group. So if I click ahead once more, let's think about what federated airspace management actually is. And it's actually a hard definition to nail down. You see a lot of different ways federation is described online. I found this to be kind of one of the most illuminating and applicable to the UTM environment. So I'm gonna use that now with you guys. It's from MITRE, talking about systems engineering in general, not about UTM specifically, but just what federation is. So a federated architecture is a collective set of architectures with some key attributes. One is that it operates collaboratively, where kind of the governance is divided between a central authority and some other units. And it's trying to balance organizational autonomy with enterprise needs. So everyone can't just go off and do exactly what they want to do. There is some order and structure to it in order to make sure the whole system works. The central authorities architecture can really focus on the dynamics of the economies of scale, standards, and the well-being of the enterprise. And those constituent units have the flexibility to pursue autonomous strategies and independent processes. So let's click ahead once more. I highlighted some of these phrases because they really do point to what UTM is trying to do. One is to create this collaborative environment for air traffic management. With that divide between the central authority, in this case would be like the FAA, or another ANSP or regulator in another country, with the constituent units that are trying to do the work in the system. In this case, it would be those UAS service suppliers, or USSs would be those primary units with support from other systems as well. And they'd be trying to balance the organizational autonomy with the overall needs of this entire enterprise that we're talking about. So the central authority, again, the FAA side, can focus on those economies of scale, the standards, and kind of the well-being of the whole system. Whereas those USSs, they have a structure within which to work. They have a set of standards and requirements to meet. They have to perform certain functions, but they have enough flexibility to pursue autonomous strategies, right? So they can focus on their own personal business objectives, a certain value added for their customers. They can differentiate themselves in different ways while still working within this framework. So overall, this is what the federated architecture provides us here in the US with the UTM system. So we'll go ahead and click ahead one more and think about how this evolved within our project. So we talked about those TCLs originally. You know, TCL1 we executed in 2015. We finished up with TCL4 in 2019. So thinking how we evolved the system in order to support operations in those different environments that we talked about earlier. Our first cut in 2015 was this very XML-based centralized system, you know, kind of a standard kind of service-oriented architecture with kind of a central authority, though, folks sending in data to that central authority, getting responses back. Not much federation happening at that point. But through discussions with the FAA and with industry, figuring out what folks want, first of all, we found that, in order to ease the agility of development and integration and testing of these systems, we had to get off of XML, move to JSON. So that's one thing we did in TCL2 with an eye towards federation, which is where we hit in TCL3, where we begin to start to test this federated set of UAS service suppliers talking to each other to manage the airspace. Finally, in TCL4, we get more specific about where the services live and how they're provided and who's providing them. So we still have this federated architecture, but we're a little more specific now about where services and how they're decomposed in the overall system. And now the idea is that now that we've started to transfer, we've been transferring this information to the industry side as well as to the FAA side, we can start to see, excuse me, we can start to see some standardization of the key components. And as Jay just mentioned in the previous talk, looking towards standards like ASTM to help us figure out how the USSs talk together to figure out strategic deconfliction, right? And that strategic deconfliction is a concept that was born out of the NASA research with our partners and the FAA. And now to see it standardized in ASTM and considered by the FAA for future use potentially, right? Seeing all these pieces start to come together is really what we're trying to do in NASA, kind of in a nutshell. So this is kind of how things evolved. Now I'm talking about all these pieces. Let's take a look at the architecture once again, and we'll click ahead one slide here. So the classic architecture that we have here, we again have that line between the central authority, which would provide itself as FIMS in this system, this flight information management system provided by the FAA, and it would be talking to the UAS service suppliers. Note the key thing here is so that FIMS does not have to talk to every single operator directly, right? And more important than those operators don't have to have the burden of trying to integrate with an FAA system. Right, that's kind of blocked off there by those UAS service suppliers. They're the ones that will handle the necessary requirements to connect to FAA government systems and provide the right data exchanges at the right reliability and at the right consistency. So those UAS service suppliers will take on those requirements and then supply services down to those operators as needed, so that it's a little more transparent for the operators how they would actually enter the airspace and take care of their business. Those UAS service suppliers are going to talk to each other to help manage the airspace. They're going to be supported by the supplementary data service providers. Now I can talk about this, but what I want to do is kind of look at each key piece in this architecture, not every piece, but some of the key pieces, and kind of walk through and talk about some of the qualities or properties of each of them. So if we click ahead, we'll look at those USSs first. So, for these USSs, again, it was a concept born out of this project, what they are, what they should do, how they're defined. We published a specification for a USS that's available publicly as a NASA technical memo. ASTM is developing a specification that takes elements of that NASA specification and hardens them and formalizes them and agrees upon them in that standards body. And really what USSs do is they share data for operations that are under their management. And those data include things like intent or updates, requests for information, position reports, various alerts, and other kind of operational messages like that. So they share data about their operations with each other, again, with the intent of making the airspace known and understandable to all participants, right? Conceptually, it's designed to be highly automated, though, in early stages, like, now or a few years ago, there would have been a lot of humans in the loop for some of the more complex tasks. Right, but we think this system is designed such that as automation improves and the rules become more formalized and understood, and the requirements are all really well defined, that a lot of these tasks can be highly automated, and this architecture supports that. So let's go ahead and click ahead, and we'll take a look at the Flight Information Management System, or FIMS, as it would be provided by the FAA side. Is this exercise in the TCLs and the UPPs, which we'll hear more about later today. Specifically, we have a whole presentation on the technical capability level demonstrations that we performed as NASA with our partners, as well as a talk from the FAA side on UPP 2.0. So I encourage you guys to check into those later on today. So NASA actually tech transferred some initial FIMS code to the FAA. The FAA further developed that to integrate with other systems on their side, systems that we don't always have direct access to, right? So they can begin to figure out how these pieces work. So the NextGen team on their side at the Tech Center in New Jersey did a lot of great work trying to figure out where all these pieces fit. R&D here really actually helps us figure out what future requirements might exist for other non-traditional or new entrants beyond small UAS, right? So as we start to think about UAM or urban operations with passenger carrying folks or large cargo delivery or high altitude operations, trying to figure out on the FAA side what data exchanges are required and what access the FAA needs in order to get data from those systems is really important for us to figure out. So yeah, so that's FIMS. Let's click ahead once more and start to think about on this border between the operator side and the FAA side. There's some things that are shared that depending on how things get developed, you know, they may fall a little more on one side than the other, and how that's going to work. So one key one is discovery. Now, discovery is a process that we highlighted very early in the TCL process. You know, we posed an initial solution to discovery in TCL2. And really what discovery is about is how do you make sure that, you know, the FAA systems know how to find and talk to the industry systems, and the industry systems, more importantly, know how to find each other to talk to each other, right? So it's one thing to say, yeah, the USSs will work together and they will share data and everything will be great. But when you get down to the nuts and bolts of things, how do you actually make sure that USS 1 knows all the URLs for USS 2, right? And understanding that discovery process is important. So we gave an initial solution in TCL2. We said, look, if we need something, this is what we're going to use. Industry then developed an improved solution that we tested in TCL3 and 4 with them. So input from NASA testing and this industry collaboration moved this discovery to kind of an open source project driven by ASTM, but implemented by an industry group, and it's called DSS, right? Discovery and Synchronization Services for use within UTM and other new entrant domains. So that's just an illustration of how the NASA research can pose the questions, drive the work. Industry can grab that and say, we can do that better. We know how to do this. Let us do it, right? And we were happy to give the reins to them. They came up with an excellent solution. We were able to test it collaboratively with them, and now it's developing into a specification that, you know, may be something that you know, lays the groundwork for future operations in the NAS. Related to that, you know, we have all these federated systems talking to each other, exchanging data. Cybersecurity is very important. We tried to bake it in as much as we could. We weren't going to sprinkle it on at the end. So thinking about authentication and authorization was something we focused on and was important. So we published a paper on authentication and authorization for this environment. And we did that with close FAA discussion, going back and forth with them on what the requirements might be and why we would have certain controls in place. That paper summarizes kind of the authorization architecture through TCL4 and somewhat beyond. As part of UPP2, the industry participants, together with the test sites, were able to engage on further detailed security discussions with further NASA input. So we're able to have a very productive discussion about authentication and authorization within the UTM environment for the near term, as well as setting the stage further on. So again, it's an illustration of how we can work with industry, come up with initial concepts, publish some initial work to give them something to chew on in order to formalize it more towards something operational. So we were really excited to see that as part of UPP2. Let's click ahead to the next slide and talk about these SDSPs, these supplemental data service providers. And I've started actually thinking about these a little bit differently than we originally did. Instead of a supplemental data service provider, I started thinking about it as supplemental data / service provider. Because folks often think of, well, if it's not just data I'm being provided, it's actually a service. Is that different, right? There's different ways these things can be imagined. There's a lot of different SDSP types, and we've tested several different versions of them. Surveillance, for example, weather, vehicle health, static and dynamic risk assessments, conflict avoidance, communication coverage. There's a long list of what these things might be. through discussions of the concept with the FAA and industry, we think that certain SDSPs may require some regulatory scrutiny and ANSP support depending on safety criticality. For example, surveillance might be one, right? If that becomes one that industry gravitates towards using in a lot of environments, in a lot of ways, and everyone's relying on it, very likely that's going to require some more scrutiny from the regulator side to make sure that it's doing the right thing. Things that are more business oriented or value added, whether it's it could be flight plan optimization, right? That's a service that probably doesn't need any regulatory scrutiny, but could add a lot of value to operators, could be provided by a USS or an SDSP. Our major contribution is kind of this architectural context of SDSPs, where they live and how they interact with different components, and a demonstration of various proof of concept services. The idea being we wanted industry and the FAA to understand where they could fit in this ecosystem to provide their services to add value or add safety to the system overall. So that's where SDSPs sit. Let's click ahead once more and think about these little blue boxes in the middle. Every TCL that we ran touched on public safety in some form. The UPP activities, they continue to develop that further. Engaging with other government agencies from local to the national level is really vital to this part of the architecture. And just want to kind of very much emphasize that we have been in those discussions throughout the life cycle of this project. So even though it's not always the flashiest test we might do, it might not be the thing that we publicize the most. We've been in a lot of discussions with, again, local law enforcement agencies, fire protection folks at the state and local level, as well as DoD, DHS, DOI, DOJ, right? We're making sure we're gathering those use cases and incorporating them into these concept discussions. And that work continues on the FAA side as well. They want to make sure that as they make these regulatory decisions that they're taking in the context of all of these stakeholders into account. So this is something that we had been working on. So we click forward one more time. We'll just see this whole thing back in context, all the pieces together in the architecture. Can we click ahead one more time? There we go. So again, the key thing being this is a federated architecture. There's a central authority on the left side, but there's some flexibility on the right-hand side to add value and continue to innovate and provide value to folks and safety to folks on the right-hand side from the industry perspective. And in that middle line there, there's some services that are shared and important to both sides, and that may take a little more work to tease out the exact requirements there. But this is the architecture that we developed over time with our partners and with the FAA. And it's proved fairly robust, which is pretty exciting. So I'm going to go through an example here, if we click to the next slide, of a very nominal use case, right? Just for folks to get an understanding of how data flows in this system. This is not a catch-all and be-all of every single use case, right? This is a very nominal case of a single operation and how it would go in a nominal case, right? There's no off-nominal scenarios. There's no multiple operators. There's not multiple USSs really sharing a lot of data at this point. Just want to make sure folks understand a little bit about how data flows through the system. All of those other use cases are things that we did test extensively through the TCLs, and you'll find a lot of publications on them. Jeff talked about some earlier with public safety and other concepts. But again, this is just a simple one to show how the data flows within the system. So usually starts with the operator. So let's click once. So the operator plan a mission, figuring out with its small UAS how it's going to perform that mission. Right? Click ahead once more. That operator would submit that to its USS and say, hey, I want to perform this mission. This is my intent, essentially, of what I want to do. Now, this could be 5 minutes before. It could be 5 days before. There's different ConOps for how an operator would operate, but both are valid within this architecture. Now let's click ahead once more. That USS would then do some work internally, make sure, hey, is that plan, is it in restricted airspace? Is it flying too high? Is it still in the right spot? Is this a valid operation plan? And generally it would come back and say, yep, looks good, and click ahead once more. What it would do is then write that information intent in a generalized form, kind of talking about where that operation is going to occur, not so much the details of that operation, into this DSS or discovery system, right? And that discovery system would then come back and say, yep, that's good. You were able to write that. Now other USSs are going to know how to contact you for those details. Let's click ahead once more. So after you get a positive response from the DSS, your USS would come back to the operator and say, yep, your operation plan's accepted. You're good to go when as planned. So again, this is probably a highly automated process. It could take less than a second, right? These are very quick data exchanges. Assuming again the system's nominal and everything's working well, you would get this response very quickly. Let's click ahead once more. After notifying the operator and knowing that I had success in the DSS, I would be able as a USS to communicate to other USSs that I'm supposed to, as I would have discovered through the DSS. So I would write that intent to those other USSs. Now they're going to have that data in order to support their operators for their safe operation. Click ahead once more. And throughout this whole process of these data communications between the DSS and the USSs themselves, FIMS is there to provide a trust anchor. That's the place where the tokens for them to communicate with each other are actually received, right? So my USS would request a communications token, authorization token from FIMS, and I would be able to use that as my USS to talk to USS A and USS B, and then USS A and USS B would trust that I am my USS. And that's where a lot of the work on authentication and authorization went in on the NASA side, transferred to the FAA, and then further discussed with industry to move forward and formalize as a standard. So click ahead once more. We'll see this whole plan. Again, this was a nominal case. We could go through very complex cases with multiple operators, multiple USSs, off-nominal situations, public safety operations. We have all of those use cases. We've transferred and documented all of those. But this is a simple one for you to understand a little bit how data flows through the UTM system as NASA has envisioned. So let's click ahead once more. So I think I did this. So, okay. So that was how you plan the operation. So upon commencing the operation, that operator would share state data with the USS, right? So this might be position reports or off nominal that the USS receives would then be required per the specification to then be shared with the other USSs and DSS and potentially FIMS. Further defining these things has now kind of been handed off from the NASA side, and it's in the hands now of the standards makings bodies, industry, and the FAA to kind of go more into. The NASA is still trying to stay plugged in, provide input, and again, lay the groundwork for other domains in which we want to have an impact with a similar architecture. Let's click ahead. Some documentation. If you go to GitHub and you search for UTM APIs, you'll see all of our APIs we use in the TCL activities. If you search for ASTM-UTM, you'll see current ASTM drafts. They're on public GitHub sites. They're not secret. They're there for you to look at if you're interested in those kind of things. We do have some NASA technical memos that I mentioned earlier. The USS specification. It was a working document all through the life of UTM. And then we published a version in October 2019. That authentication and authorization framework we published last September, 2 Septembers ago, I guess. And then there's a strategic deconfliction final report, which again is something that folks from the industry side were able to comment on and provide input on to give us a validated set of requirements for strategic deconfliction at a high level. So those are available for folks to look at. If we click ahead once more, there's a lot of other documents available as well. This is just a sample. One as first authored by the FAA side, Praveen, which you'll hear from, whom you'll hear from later, talking about UPP2. UTM, a complementary set of services to ATM, was published at ICNS a couple years ago. It's a good paper I'd recommend taking a look at. We look at the USS performance overall in TCL4. And look at that and publish some results there in 2 papers about the USS network in TCL4. Those are public and available. Finally, for folks that like to get in the weeds a little bit and think about how we prepared our USS partners to be ready for TCL4, we go into some of the technical details on how we checked out USSs to participate in TCL4, and those are provided there in two papers. Let's go down one more. So given that we did all this work with partners and we've published all of our efforts, how do we how do we see this thing progressing? So let me see here. There we go. So the big one is standardization. I've hinted at it quite a bit. The work in NASA UTM has kind of laid out initial research questions and kind of a framework for evaluating the architecture as a whole. So we've transitioned that work. There's still a great deal of effort that has to go into standardizing that and figuring out the evolution of those things. You know, we're not necessarily planning to just roll out UTM services for the urban environment right away, right? It's kind of a rollout of things. So in terms of the standardization process, they have to find the right bite-sized chunks to standardize first, such that they can then evolve to more and more complex operations. So that process is ongoing right now. You've heard it mentioned earlier today, this XTM concept, extensible traffic management. And really this XTM term came about because we got kind of tired of saying, you know, a UTM-like environment or a UTM-like system, and it was too fuzzy. So we tried to define a little more firmly what an XTM system was, which is really a UTM-like system or environment. So what we discovered in UTM through the evolution of the process of how to manage the airspace for small UAS is really a completely undiscovered approach to managing airspace in a collaborative manner. So allowing stakeholders to actually have input into the management of airspace, complementing traditional air traffic services provided by the FAA, that's completely new. That's not something anyone ever really thought about before this project. But this approach now is being generalized by NASA and by the FAA to extract some common features to define what XTM is and how it might impact the NASA as a whole. Directly, it's influencing AAM and UAM. So these principles of collaborative airspace management and increased automation, they're critical to enabling these mobility concepts in the urban and rural environments. So you'll see a lot of that happening there. The high altitude traffic management, or ETM as we often call it, thinking about operations over 60,000 feet. They don't typically receive ANSP services once they're up that high. Usually they get the services in order to get up there, but then after they're up there, they're not really provided the same kind of services that most operations on NASA would be. And they can span international boundaries. So how do we create a collaborative environment in that space such that intent can be shared, the airspace can stay safe, folks can perform their missions. And what's interesting up there is not just obviously the increased safety concerns, but kind of the differences in performance of the vehicles that might be up there, right? From large balloons without too much maneuverability and hypersonic aircraft, right? Those would be interacting up in that airspace. So how do they share intent in a smart way? And give those operators more agency in managing the airspace themselves. And now conventional aviation, you know, some of these concepts related to provisioning services and trying to increase automation overall in the system could be applicable to conventional operators in the NAS, potentially allowing for safer and lower cost operations in the long term. So that's an ongoing research discussion within NASA and externally as well. So how can we apply some of these concepts of XTM to conventional aviation? Let's go to the next slide. Our summary and impact. So overall, the NASA UTM project, along with its partners in the FAA and industry, defined a novel, feasible, federated, stakeholder-driven approach to managing the airspace. Again, novel is key here, right? This wasn't something folks were thinking about before we got started, and it really ballooned and kind of resonated with stakeholders. The concept of federated airspace management allows for operators to take a key role in the management of the airspace in which they fly. And in a short time, NASA research spawned numerous international standardization efforts, a new industry for service suppliers, and a path for safe, efficient, scalable, and fair management of the airspace. This architecture is recognized as a key enabler to other new aviation entrants, like air taxis and high altitude operations. So the impact's been broad in terms of this architecture and the way the airspace would be managed. And we're excited to kind of keep pushing this forward in these different domains. So you'll see NASA very active in all of these domains moving forward, and really proud to have laid the groundwork via UTM for those domains. And with that, I think that's my time, and I think that's my set of slides. So appreciate your guys' time, and I think we're going to have a break, so I'll hand it back to Jay Woo, but look forward to chatting with you guys a bit more later.
Great. Thank you very much, Joey, for a great review of the architecture and the nominal use case, and also our path forward. So we will have a break, and we will meet again at 9:25 a.m. Pacific time in US. That is also 12:25 p.m. At Eastern time. And when we meet again, we will talk about sense and avoid and conflict management. So with that, let's go and take a break. All right, welcome back, everybody. We have Dr. Marcus Johnson, who has been co-coordinating in UTM RTT for Sense and Avoid Working Group, or also known as a subgroup. And he's here to talk about UTM conflict management. And before I give floor to Dr. Johnson, please think about the questions and then enter them in conferences.io so that we can respond to. And the link to that is time to time shown in the YouTube chat, and you can also take a look at that, our registration site. With that, Marcus, please go ahead.
All right, thanks, Jay-Woo, and welcome back, everyone. So for the next 30 minutes, we're going to talk about UTM conflict management and kind of some of the testing that we did, some lessons learned, more discussion on some of the internal testing that we did in some of the later sessions. So I'll touch on some of the NASA testing, I'll touch on the TCLs, and then they'll be more detailed by other folks as we move throughout the day. Go ahead and go to the next slide. So we'll start with just an overview of what the Sense and Avoid UTM RTT subgroup was focused on. Talk a little bit about where we see kind of the progression of the state of the art. Talk a little bit about the conflict management model that was kind of the big result of that particular RTT's effort, and then talk a little bit about findings and future works and consideration. Let's go ahead and go to the next slide. So from the UTM RTT Sense and Avoid subgroup, we had our kind of been tasks starting about 2017, and our main objective was looking at the solutions that were necessary to enable or to ensure that UAs would not collide with other aircraft. As we started going through discussions with industry, we started to realize that it was clear that scope was very important. But there should be other considerations as well in looking at collision risk in a more holistic fashion, which included both ground and air hazards, was the more prudent thing to look at for a conflict management model. So again, we kicked off in 2017. I think over the course of 2 years, we had about 23 different meetings, included 3 joint meetings with communication and navigation subgroup, which was led by Jay-Woo. And he'll talk about in the next session. At peak, we had about 60 different industry folks that engaged and participated in the subgroup, giving their input either verbally or written. And then kind of our purpose was to talk at kind of that concept level and help inform some of the direction of the NASA TCL evaluations, help inform some of the directions of kind of the pilot programs, help inform some of the directions of the ConOps. So a lot of the discussions that happened kind of made its way into other venues and other platforms to help set the stage for what the types of things we should be testing and what types of technology should be brought to bear and in the mechanisms in which they should be brought to bear. We did have kind of a key document. One technical document package was produced, which captures both TCL 2, 3, and 4. We had an interim distribution of that document, and then the final document was produced, and it is available on the UTM website. Go ahead and go to the next slide. So let's just start with kind of where we saw the progression going with UTM and conflict management specifically. We start with kind of the Section 333 waivers and ultimately the Part 107 type of operations. These are visual line of sight.
Marcus, I do apologize, but you have muted yourself on accident.
Oh, well, that was amazing. I don't know how I did that. And there is some sort of waivers that can support waivers to Part 107, which can support the use of either onboard or some technology-based detect and avoid type solutions. One of the challenges is that it's really kind of these small, swap type of systems, so limited size, weight, and power. And ultimately, in order for us to get scalable solutions, we need to start thinking of having capabilities that enable us to have further distances, that enable us to be not only capable of a safe flight, capable of avoiding something, but also interoperable with the airspace, interoperable with other systems, and being able to actually have higher throughput of operations. So what we saw kind of as the progression was going throughout the TCLs is many of the detect and avoid solutions were very kind of sensor specific, or they were like a point solution which addressed maybe portions of the collision hazard, but didn't really address the full kind of conflict hazard that was there. And so it wasn't really holistic approaches that were taken from a technology standpoint. Much of the integration and interoperability tended to be after the fact, and a lot of human factors considerations tended to be an afterthought in the development. And then ultimately, the technologies really were piecemeal, and it was really left to the operator to kind of piece together a system and test out its necessary components in order to address collision risk. If you go to the next slide. Where we're trying to get to ultimately with the UTM conflict management is something that is more cohesive, right? So the desired state is to treat conflict management mitigations as a continuum, right? As opposed to like these discrete technologies that are patchwork together, and have it as something that has, each component has a level of independence, but it is interoperable with the other components, right? So, and it knows when to take the lead and when to, when it's responsible for certain, for maintaining separation or maintaining a certain distance away, and when it's actually playing more of a contributing role. We really think that this tends to be something that, will be a lot more cohesive of a strategy for UTM conflict management. We tend to think of it kind of like jazz, right? This is like the jazz of UTM, right? Each system really plays a role, and it's supposed to be everyone's kind of, all the systems are working together for the same type of objective, just in different time domains and in different ways. So in order to address conflict management, one of the things that we kind of started with is this holistic approach that looks at, both air and ground hazards, both transponding and non-transponding aircraft, and both static and dynamic obstacles, and need to consider those in the context of airspace constraints and other limitations. So if you go to the next slide. So we started with this kind of, what are the contributing hazards that to look at in this problem? And we broke those down into hazards that happen on the ground risk side, hazards that happen on the kind of the air risk side or the airspace side, and then hazards that are due to other operations that are flying around. And so when we started crafting the different elements, both from the system and the operator, the US operator, to any services they may be provided, and whether those services were, like what time horizon those services were at, and at what phase are certain services being used in both nominal and off-nominal situations, right? Trying to tie those together is where we resulted at in terms of our conflict management model. And so if you go to the next slide, this gives you a highlight of kind of where we ended up in our discussions from a concept level through the RTT. It's broken down into basically strategic separation or strategic mitigations, strategic conflict management, and then tactical separation mitigations. And those even have kind of a time horizon associated with whether they're kind of associated with a separation provision, or whether they're associated with something that is very near term in conflict management. Likewise, the different rows are broken down into the different parts, the different contributors, there's different stakeholders that are contributing to the solution. And so, much of the early progression was very focused on that bottom row, which focuses on the UAS and the UAS operator playing a role, either through operation planning, through having a visual observer out there, having ground-based radar out there, doing remote identification, or having onboard capability. As we start moving away from just being able to fly safely, right, and being able to address how to enable scalable operations and interoperable operations, and being able to actually even address the flying safely with limited swap requirements. It started to necessitate the need for services to provide some provision of the separation responsibility. And conflict management responsibility. And that's where you start seeing some of these capabilities like strategic deconfliction, which Joey had mentioned prior. And there's other elements that we had talked about, how to monitor conformance, how to do dynamic rerouting. And these are tied to different hazards, specifically whether they're trying to maintain your operation within acceptable risk environments, either from an airspace or a ground risk. Trying to more actively avoid hazards on a ground risk or an airborne risk. And so this kind of was meant to try to tie together the different elements of the conflict management problem and try to tie them to the different technologies and look at an operator kind of choosing from their operational environment what technologies make sense and piecing those together to try to address the required hazards for that operational environment. So we go to the next slide. We talk a little bit about how we tested out these in the TCL demonstrations and kind of the approach we took, which ended up being more of a risk-based approach, which you've seen this slide before. But as we start applying this conflict management, our TCL environment was very much visual line of sight, notifying other operators of the intent, and potentially some information sharing at a very low level. Right, as we start extending that to beyond visual line of sight in TCL2, we're now starting to be more prescriptive about sharing our intent and where we plan to fly, doing more strategic deconfliction, talking a little bit more about making sure that we're containing our operations to that intent. Starting to get into more urban areas or suburban areas, you start factoring in more ground risk. So additional, more airborne risk associated with other aircraft that are flying in that vicinity. So talking about conflict alerting, more prescriptive onboard detect and avoid, more vehicle to vehicle to account for increased density. And then TCL4 was focused very much on the increased density in urban settings. So things like obstacle avoidance and V2V become very prevalent here, and tying to kind of safe landing capabilities became very prevalent. Go ahead and go to the next slide. So as we walk through each of the TCLs, we took a different strategy on how we were addressing conflict management. We asked I give an example. We had kind of different questions that guided how we developed the scenarios. And then these are just some highlights of lessons that we were learning along the way. Some are more observational. And again, we kind of complemented our TCLs with some testing that we did in-house at NASA. To really hit home, the implications of what we're seeing with the current state of the art. So in TCL1, we focus very heavily on, I'm going to put on the quotes, separation by structure. And I know that's probably the wrong way of saying it, but the point is I'm going to define a volume and I'm going to stay within that volume. And you're going to define a volume and those volumes wouldn't overlap. Right. So as long as you stay within your volume, I stay within my volume, we're good. Right. So this is in the conflict management model. This is kind of flight notification. I'm notifying you of my intent, and then you're making sure that you're staying out of that intent. All right. This is very early days. We were really just trying to see, how well could a UA remain within its operational volume? How feasible was this? Given the current performance of a UA. One of the things that became very evident as we started looking at kind of the operations that were going on at Crow's Landing was the types of information that was provided back to the operators. There was kind of a lack of really a clear operating picture between different operators. At this time, UTM was still kind of this centralized core system. It hadn't been expanded to a federated architecture. Some of those display elements hadn't really made their way down to the operator. We were still kind of playing around with a UTM manager type of role, right? But what became very evident is operators needed this information at their disposal and needed to understand where they were with respect to their own operational volumes, but also where they were with respect to other operational volumes. So one of our recommendations we had was UTM will need to provide some common strategic and tactical view of airspace operations and the conditions in which they're operating. And again, very, very fundamental now that we look at it, but back then, in the way that we were kind of instituted in concept, this was kind of, it was what was helping us mature where we were going. The other thing was with varying atmospheric conditions and vehicle performance, UAS occasionally left their operational volumes. You see that in the picture on the right, a couple of dots out there. That was particularly with a fixed wing aircraft that was flying there. What we realized is that the design and crafting of the operational volumes needed to be actually couldn't be arbitrary, and let me say it that way. So it needed to incorporate elements of the flight technical error, atmospheric conditions, and additional mitigations are needed for being able to maintain your containment to that geography. So if you are instituting something like a separation by structure, you need things like conformance monitoring and onboard geofencing to actually maintain the aircraft's ability to stay within that volume. Furthermore, as you start changing that volume, you may need geofencing that changes with the change of your operation plans. So just more considerations needed to be lended to operational volumes and how they were designed on an operation by operation basis. Go ahead and go to the next slide. As we moved into TCL2, we started to expand beyond just, I'm going to announce I am present in this airspace, to now starting to say, okay, operations can overlap. So we need to start considering what happens when they overlap and do some amount of strategic deconfliction. We started to take some of our lessons that we learned in TCL1 and start instituting more geographic containment. And being able to now tie in some additional information from ground radar in other systems that allowed us to have some alerting based on proximity of one operator to another, particularly when they got outside of their volume, right? And that was one of the interoperability challenges that we were looking at was, if I'm operating in my volume and another system like a detect and avoid system detects me and says that I'm too close, but I'm doing what I said I was going to do, right? That system really shouldn't be maneuvering based on that information. So one of the things that we were looking at in TCL2 was kind of some of the key considerations as you start having these operational volumes that overlap, but in particular, as you have them on top of each other, from 0 to 400 feet AGL is not a lot of airspace. So if you really want to support very high density, we needed to have some understanding of what was going to happen as you start stratifying the aircraft in the airspace. So you see there on the bottom right, that's kind of a picture of out at Reno Stead Airport. We had 5 aircraft that were operating simultaneously, and you do see some overlaps. Those aircraft were flying over each other during the operation. And we looked again at the conformance up at the top and started to break down the different elements of nonconformance and kind of how they contributed, what was the cause of them, whether it was an incorrect altitude or vehicle performance or operator errors. Some of the lessons that we found from here was looking at, and one of the key one was looking at, there were some clear discrepancies associated with how the vehicles interpreted altitude, either through the UTM system and the service providers, or on their displays, or even how they were communicating it over the radios, as an example from an operator. So altitude reporting, should be consistent and translatable across the airspace users. I'm gonna hint on that a little bit more explicitly when I talk about our TCL4 results, because that particular issue really kind of popped up in multiple TCLs, and it is one thing I want to hit home because it has implications again as you start talking about scalability and starting to increase density of operations. The other one that became very evident here was the source of weather information for our flight tests were really inadequate to support beyond visual line of sight. We had a number of weather systems out there. We were using the AWAS from the airport. We were using LiDAR, SODAR. We had weather towers. We had different handheld anemometers. There was even some sensors on board the vehicle. But it became very evident that even in this small geographic area, the microclimates that were associated with where the aircraft were flying, they were all kind of experiencing something different. So initial routine beyond visual line of sight operations should not conduct altitude stratification unless there is an accurate and timely information sharing on relative position of nearby UAS. and improvements are made in the fidelity of the weather prediction. And this was largely due to we had aircraft that were flying over each other, and we had incidents in which an updraft caused an aircraft to really increase altitude pretty rapidly. But the feedback wasn't going back to the operator quick enough in terms of their proximity to another operator, and they didn't really have any direct information that associated with the weather conditions that the aircraft were flying on. It was really kind of indirect based on the performance of the aircraft. And so this really made us feel a little uneasy as we started talking about beyond visual line of sight with altitude stratification, without having additional sets of information that give the operator and the aircraft some amount of situation awareness. Go ahead and go to the next slide. As we start moving into TCL3, again, we're starting to expand our strategy a bit, talking, again, strategic deconfliction, conflict containment, starting talking about the conflict advisory and alert, now starting to incorporate some of the DAA technologies and sensors and systems, and even looking at some initial V2V evaluations, particularly with the a dedicated short range technology that the DOT was considering for the automotive community, so called DSRC. So in this domain, some of the research question that we were asking, among others, was, do onboard sensors have suitable performance to support conflict management? All right, and so this is kind of an underlying question with these being very small swap or low swap type of systems. Can they meet the needs of being able to provide well clear against manned targets? Can they meet the needs of being able to separate even from small UAS? And can they be repurposed in some ways to be able to provide even ground risk? Being able to do some amount of obstacle avoidance and such. So one of the lessons that we saw as we started to incorporate some of these capabilities was that kind of using these airborne and ground radar systems to support separation showed that the low swap radar systems really weren't quite there to support the well clear definition as it was defined. If that was the only system that was being implemented. We also did notice that there was kind of high false alerts that were generated. There was quite a bit of clutter as you started getting lower to the ground. But it doesn't mean that these systems aren't good and shouldn't be used. It's just simply, maybe we're asking too much of them. Is really kind of the bottom line. Maybe collision avoidance is a better, kind of more within their swim lane for use, as opposed to trying to use them for everything within the DAA span or within conflict management. The other aspect was the V2V. The V2V did raise situation awareness on the using the DSRC. It did raise some reliable data to support collision avoidance under kind of slow closure rate situations. However, it still did have some limited range associated with it. So again, we didn't really test a lot of high closure situations. And we didn't really try to stress the speed of the aircraft as they were moving through the airspace in terms of closure rates. So more work would need to be done really to mature that type of capability. But there is potential of using those, particularly in high density situations where potentially vehicles aren't going as fast as in lower density situations. Ultimately, the recommendation here is as you start looking at kind of testing multiple layered mitigations, both the onboard capabilities as well as services that could support an operation. They did overall raise the situation awareness. They did overall increase the range, not on a technology by technology basis, but on a system level basis. But continued evaluation, it was both basically needed to address kind of some of the interoperability, some of the data fusion types of aspects in order to kind of track the aircraft across multiple sensors. Go ahead and go to the next slide. All right, so kind of rounding out TCL4 here, this was trying to test out as best as we can with the current technology, more of the layered conflict management. So from strategic deconfliction all the way down to technologies that would support kind of obstacle avoidance. So what we were looking at is kind of, as you start going into urban settings, what factors impact the conflict management in these urban environments? And some of the lessons that we saw, again, these should be fairly evident, but they do have broad implications when you talk about many aircraft operating in these in kind of urban settings. The UAS and the onboard mitigations really lacked the appropriate reliability. We had a lot of single point failures, motors going out and vehicles, having unplanned landings, parachutes being deployed over areas that they shouldn't. And these really kind of created some hazardous situations for people on the ground. So it was actually a situation in which an airborne mitigation caused a ground hazard. And so we have to, again, look at some of the reliability and the interplay between the risk that we're trying to mitigate for the environment in which we're in. Other things that caused us some pain during TCL4 was kind of these the different hazardous conditions. Again, that those microclimates popped up again. There was a high concentration of unlicensed bands, which caused interference with some of the command and control. There was multipathing, GPS degradation. There was a lot of kind of challenging. It was a very contested environment. The maturation of the vehicle reliability, the health monitoring, contingency management of the systems, all of these really need to improve. Having things that tie into kind of a smarter, automated, safe landing capability. All of this is needed in order to really enable these urban operations. Go ahead and go to the next slide. I just wanted to take just a minute to talk a little bit about the altitude issue because it popped up again in a variety of different places. As many of you know, there's many different types of altitudes that are used in operations for UAS. It may be that airspace you need to stay in, something like the UAS facility maps, the altitudes you need to communicate, or the altitudes that are being recorded from other airspace users, like manned aircraft. There's different types of altitudes that are measured from the UAS, whether it's height above takeoff level, height above takeoff location, above ground location, or an MSL. And then even what the USS is using. In our case, it was WGS 84. And then the buildings and obstructions, right? So those are going to have their own relative type of information as well. Go ahead and go to the next slide. So when you start mixing these different types of altitudes in the mix, what we come to is that we may not have, some of the airspace boundaries may not account for the terrain. You may have errors associated with transforming between MSL and other reference frames. You may have inconsistent reference frames and coming from the UA or the GCS. You may actually have different units as well that's being displayed to the operator. Altitudes are sometimes coming from multiple sensors on board the UAS, so it may be a fused altitude measure. USSs, fused or changing. USSs may also translate altitude from the UAS to WGS 84, and they may use different terrain models. We definitely saw that was a challenge. And then the obstacles that are mapped in AGL and are dependent on terrain models as well. So what this boils down to is we really need to get a handle over, what altitude is being used for what type of system and kind of how is it being communicated and how is it being manipulated. So standardization is really needed on the reference frame, the measure, the unit, and any sort of translation or methods that are used for the altitudes and how they're communicated and kind of the intended use of that altitude. Go ahead and go to the next slide. All right, so I'm just going to highlight here. Go ahead and go to the next slide. These are some NASA technologies. We'll get a briefing of this going forward, but some of our NASA technologies at Langley that looked at more of the complete integration from the USS down to operator displays, down to a conflict management framework called Icarus. Down to looking at ground risk assessment with the URAF framework, looking at geofencing, and looking at even a safe landing capability on safe to ditch. So looking again at more of not only the individual capability, but also the integration and interoperability between systems to form more of a complete UTM model, conflict management model. Go ahead and go to the next slide. We also looked at operations within the urban environment, and so this will be talked about with Corey Polito later in the day, and some of the testing, some of the analysis that we did. And this is focusing on basically the different challenges associated specifically with conducting more automated operations in these urban environments, and the different factors that they need to account for, like environmental, atmospheric, some of the failed and off-nominal conditions, and both the dynamic and static obstacles, as well as other aircraft and C3 type considerations. Go ahead and go to the next slide. So these are some example lessons learned. I'm going to actually let Lou Glab and Corey Ippolito talk about these as part of their talk, since I'm running a little low on time. So we'll go ahead and go to the next slide. And we'll finish off in these next two slides just talking about kind of a summary and the next steps. So ultimately, our TCL, our UTM RTT Sense and Avoid group was really focused on kind of these defining these concepts, informing the field testing that was going on, and some of the simulation analysis that we had under our project. We looked very heavily on the UTM conflict management model, and again, trying to get some of these principles in for conflict management in the ConOps and the use cases, and some of the hazard identification, and some of the requirements around urban operations, and try to make their way into some of the specifications and ICDs that we generated, as well as our software prototypes. These were tested out in our demonstrations. They were tested out. Some of these, again, the concepts and technologies were tested out in the pilot programs. This conflict management model is making its way into the UTM implementation plan, just the general strategy. And then certainly you see this in some of the industry guidance and standards that are out there, from the DAA to the UTM specification, or the surveillance STSP. And then, as was said before, some of these services are being considered under this, the UTM annex under the SORA as well, linking the safety instantiation to the performance of the service. Go ahead and go to the next slide. And I'll wrap up on this slide. So going forward, in terms of conflict management, the FAA through the Beyond program will focus on beyond visual line of sight and this DAA and UTM requirements. We do expect some of this, again, this conflict management model and conceptual strategy to be kind of used within these programs, and building out a conflict mitigation approach with each one of the operators. Conflict management topics will be continued to be developed on the UTM ConOps version 3.0. And within the implementation plan. And then ASTM and IEEE certainly have existing standards that are kind of continuing to work. Within NASA, our Advanced Air Mobility High Density Vertiport subproject is looking at conflict management near vertiport operations. We have a scalable traffic management for emergency response, and that's looking at layered conflict management and constrained disaster response scenarios. Our SWS project is also looking at kind of the integration of conflict management within health monitoring and UTM services. And as well as our ATMX project is looking at both onboard and service-based conflict management interoperability. So these is extending into further research. It is looking at different domains beyond just small UAS, but some of it is also incorporating small UAS conflict management as well. So go ahead and go to the next slide, and this is just my last slide that will point to some of the publications. The top one there is the model itself, and then there's a few that are highlighted, again, from our Langley and Ames internal work in flight test and analysis. And then down at the bottom, there's a number of other publications associated with the conflict management testing and analysis that we did. So feel free to go and look at those presentations, look at those publications. And with that, I apologize for being a little over, but I'll pass it back to you, Jay-Woo.
All right, thank you very much, Marcus, to provide us a comprehensive view of how we approached conflict management. Before I switch my head to presenter head, please know that the questions you put in the conferences.io for each session get saved and downloaded so that we can handle them in the Q&A session. Now, to present, so I've been working as NASA FAA UTM RTT Communications and Navigation Working Group Co-Coordinator. And in that context, I'd like to talk to you about the activities and what we learned about the small UAS communications and navigation. Next slide. So I'll touch briefly upon the RTT working group / subgroup, their interchangeable term, and dive into communications and navigation activities during the TCL 2, 3, and 4. And for one, RTT was informed, by the way. And throughout that description, I have references indicated in bracket, and then I'll capture them all together in a publication of research findings in 2 slides and talk about the areas of future work and summary. Next slide, please. So the CNN subgroup, the objective for us was to explore communications and navigation solutions to ensure that the unmanned aircraft are under the operational control of the remote pilot. So this is a communications issue, and then remain within a defined area. And this would be the navigations related. And we kicked off after TCL1 concluded. So as a subgroup, we worked on TCLs 2, 3, and 4. Throughout that process, we had about 26 meetings, and 3 of them with Marcus's Sense and Avoid subgroup. And at the peak, we had more than 100 UTM community members interacting within the subgroup setting. And we used a community responses to the request for information and use that as a basis of the communications and navigation guideline, and then how we should handle the contingency management requirements. And with that, let's go to next slide. So I'd like to now talk about the CNN activities during TCL2. And as you know, TCL2 has to do with operations over sparse population and multiple beyond visual line site operations, but really not really over people or property. And so let's move on to the next slide. So we sent out request for information to gain insights about small UAS communications and navigation issues. And we received 20 organizations' responses, and then we also had discussions of those responses. And through that process, we found the following insights to be relevant to us. First, that communications and navigation system performance must reflect operational setting. And operational setting really is where is the operation and what time, what kind of UAS is being used, and what is your mission type and how long that mission is. And most critically, who else is expected in that area. So that is a really important part. And the second thing was communications between UA and its operator can be disrupted, especially if one doesn't use protected aviation spectrum. And finally, given the prevalent use of GNSS receiver, such as GPS, navigation performance can be degraded due to RF interference and multipath issues that could happen more often than not in low altitude environment. Next slide. So this slide captures a notional relation among small UAS communications performance and level of small UAS operations automation and operational setting. The y-axis is a communications performance, and the higher, the better performance-wise. And then the x-axis has a level of small UAS operations automation, and low would be you're gonna have to take a look at the vehicle and then manually control that vehicle, for example. And high would be you just press a button and it does what it has to do. And the relation is that the higher the automation, you don't really need that whole lot of communications performance because it would know what to do. But there will be minimum performance requirements because there are information that UA itself may not be aware. So as an operator, if there's a restrictions coming in your way, then it will the UA will need to have the communications line so that that new constraint is known. Now the brown curve is really about that relationship, and then the overall setting, the minimum performance requirements goes higher. For example, if you were to fly over cornfield, then it's probably different than operating beyond visualized sight in a suburban area, and so on. So as the operational complexity increases, the minimum performance would go higher. Next chart, please. And this is also a hypothetical relation between small UAS navigation performance and operational setting. And this is done in terms of a required navigation performance level, or RMP. So low, actually, it's a small value, which means high performance. And then high or large value is actually lower performance. Sorry for that confusion. And then the x-axis is operational risk, and this is really derived from the operational setting. And the same inverse relation exists. So higher the operational risk, the better or higher performing RMP would be necessary, and then it'll be bounded by technological limit of RMP level. And on the top, you'll see the formula that we tested out in one of the publication. The Jung 2016 is that publication, if you'd like to take a look. Next slide. So throughout TCL2, communications and navigation evaluation took place, and two publication captures them well. And we had a data collection, but that was really done over a sparsely populated area, given this was TCL2. And they had the operations had an unobstructed view of the sky. And UA typically remained relatively close to the ground control system, somewhere between 2,300 feet to 4,200 feet. So that will be about less than a mile or 1.6 kilometers or so. So in that setting, 4 out of 47 flights experienced loss of communication command and control link, and then this we expect that unobstructed radial line of sight and relatively short distance really resulted in that low number. Next slide, please. For navigation, 2 out of 118 flights encountered loss of navigation, and we also think that this low number was achieved by really with the unobstructed view of the sky that the UA was having. And the NASA TCL2 test result analysis Marcus just went through showed that the communications and navigation performance is not only important for own operation, but overall UTM ecosystem, as weather, operational intent, and geofence information exchange would take place over communications. And then beyond vision line of sight, operation with altitude stratification not only requires a standard way of exchange at altitude, but actually the vehicle itself will have to know that altitude accurately, which is navigation performance. Next slide, please. So moving on, we are now on to TCL3. And this is now approaching a suburban environment, if you will. So let's move to next slide. So in this process, we had engaged with the community to really figure out, well, you know, communications and navigation could experience off-nominal situations. Then how should we manage those? So, and then with that interaction, 18 high-level requirements were developed. And those were reviewed by the community members, and they were all found deemed reasonable as written and is needed by UTM. And the two publication captures those the 18 requirements. And as we discussed that, it was identified that in many cases, mitigation of communications or navigation off-nominal situation results in landing of the UA. For example, if operator and UA experience prolonged loss of communications, many UA platforms are programmed to land or try to come back to the operator and then land. And then when navigation performance goes lower than it needs to be, many of the UA are programmed to actually land. Now, that may work for operations over a remotely populated area, but now we're approaching suburban area with a moderate population. Therefore, maintaining safe landing capability, where safe landing is defined as landing of UA without causing detrimental impact to people and property, is really understood as having paramount importance. Next slide, please. So we have discussed about that and then came with recommendations on how to handle communications and navigation off-nominal situations. So when off-nominal situations occur, whether the operation should enter the emergency phase, such as defined by ICAO or not, should reflect the status of safe landing capability. So uncertainty phase would be if off-nominal situation has occurred, but it's being mitigated by UA and its operator with intact safe landing capability. So this is just the information for anyone to be aware of. Alert phase is the situation is being mitigated. Now, however, the safe landing capability is compromised. So we have to do something about that phase. Otherwise, safe landing or ground risk exist. Distress phase is the situation poses an imminent danger to people and property. And I have a few examples of each phase to go through with you. And however, if we think about it, safe landing capability itself can take different shapes and forms. One would be, well, if something goes wrong, it is go to fly to a safe land location. It could be as simple as fenced off sandbox, so nobody's in there, as person-wise, and UA could land or crash into it without hurting anyone. Another capability would be it has onboard capability so that as it tries to land, it can land while avoiding people and properties. That's another. And as you have read through the operations over people and night rules, the UA could have a mechanism to transfer small kinetic energy upon impact. And combinations of those three can be safe landing capability. So if one were to understand whether UA has intact safe landing capability or not, we're recommending to monitor the following 6 areas concurrently. One has to do with navigation health. Another command and control is communications health. And external surveillance is typically the UA itself reports its position, but this is other means of knowing the location of the vehicle. And environmental detection function is related to how it knows where people and property are so that it can avoid. And ADAG is attitude determination and control, and as you know, if that goes bad, then it's going to be not so good. And resources has to do with if you're to fly safe to land location, do you have enough energy to do so? And if you were to reduce kinetic energy, do you have enough to thrust to do that? So those are the things that should be monitored. Next slide, please. So I won't go through all of this, but the top one would be a nominal, and then the emergence phase uncertainty example here is okay. UA itself is being experiencing navigational health issue. Well, this is probably information only as long as external surveillance works and there's a communications link in place to direct the aircraft. So that would be an example. Move to next slide. And what would be an alert example? Well, maybe the UA is experiencing navigation issue, and it's also environmental detection is not working properly, and external surveillance is not available. Then what would one do? Well, as long as resources there, vehicle could enter loitering pattern, and then a piloted command could reach the vehicle and use manual control with line of sight to the vehicle to mitigate this issue. So that would be an alert example. Next slide, please. And the distress, well, if I'll just call the middle one. So if the vehicle's attitude, determination, and control system is not working properly, that is really a distress situation because there is no knowing where the vehicle's gonna go or whether it's controllable. Next slide, please. So during TCL 3, we went through several evaluations as well, and that is captured in a couple of documents. And one is we evaluated effectiveness of redundant communication systems in maintaining operational control of small UA. And in that document, we clearly identify what redundancy means and then provide examples of the redundant communication system and so on. And we end that into with generating recommendations for urban operations as we are heading to TCL 4. And we also recognize the LTE or long-term evolution or 4G, I guess nowadays 5G is now, has a potential to be used for communications for small UA. So we looked at the low altitude LTE power spectrum for C2. And finally, we recognize the UA itself can generate electromagnetic interference to perhaps affecting its own communications system. So we evaluated the impact of ownership generated EMI in NASA's radio chamber. Let's go to the next slide. So TCL 4, now we're talking about operations over dense population, increased traffic density, urban application, and potentially large-scale contingency issues such as prolonged interference of the communications frequency for some reason. So this is TCL 4 setting. Next slide, please. So here, now that we approach highly complex and high dense operation setting, we are now introducing the notion of timeout. What that it is, UA and UAS could enter non-nominal situation or off-nominal situation, but there may be way for UA or its operator can fix that. So timeout is a fixed amount of time for the operator and UA to resolve off-nominal situation to return to normal operating status. Now, we can't really have that ongoing because of the density of the operation that we expect over urban area, and then other obstructions such as buildings. So we have to have that limited. And once timed out, we are recommending that UA to display predictable behavior, such as initiating safe landing procedures. And throughout TCL 4, we introduced 3 timeouts. Actually, this was starting at TCL 3. So throughout TCL 3 and 4, we introduced 3 timeouts. And one has to do with C2, and then the other, it's actually bi-directional. I mean, it actually has 2 directions. One is UA to operator C2, that's telemetry, and operator to UA C2, that's a command and control, and requirements are actually different. And then there's one timeout has to do with a navigation degradation. And as we introduced this timeout, we realized UA, operator, and USS to work together. So let's move on to next slide. And this is captured in the publication, but what I really want to say here is as UA and its operator go through mitigating communications and navigation issues, there can be different things that USS can do based on whether timeout has reached or not. So if timeout has reached, then USS should assume it's starting safe landing procedures and perhaps proactively modify the operation plan, or even use one submitted by the operator in that case, and then respond to it together, rather than not knowing what operator or UA is doing and trying to guess or trying to contact the operator via non-automated means, which did happen during TCL4 process. So integrated way in where UAS and USS handles off nominal together is recommended. Next slide. Now, during TCL4, we practiced those requirements, and then we calculated some of the MOPs, and we collected off-nominal situations report, and then those are all captured in the publications. Next slide, please. So as I mentioned, all those publications with a bracket in there, they're listed here and on the next. So you can always come back to this presentation and then kind of capture our communications and navigation work with these publications. Moving to next. So what are the areas for future research? I started a chart, but end up just showing this. So what I show on the y-axis is communications and navigations performance. And what I show on the x-axis is time and engineering effort. And then what I show in the middle is a yellow S-curve, typical one, where we see, rapid increase at some point, and then kind of tapering off at some point. And maybe this is a personal opinion, but I think it reached that plateauing of the performance, and which enables perhaps a line of sight operation, and maybe expanded beyond visual line of sight operation with the observers, which is fairly costly. So we need to have another S-curve to puncture us through to the performance necessary for beyond visual line of sight operations in urban setting. And for that, we will need to investigate how we handle safety more. And that is not alone. We should look into logistics issue as well. So how we spread out the operations and recover them as necessary, and culture. So we need to build our community so that we're thinking of operating with each other rather than only caring of the operation of one's own. So that's the areas for future research. Next slide. So in summary, this communications navigations work and other areas of UTM the working with community, whether that's FAA test sites or manufacturers or operator, it was really a key to gain insights and develop the requirements. And field tests show that use of unprotected spectrum could work, but it'll probably work where over remote location, away from population and source of RF interference. GPS also could meet the navigation need if the area has an unobstructed view of the sky. And once again, altitude reporting needs to be compatible among operators, which what Marcus has hit on. And off-nominal situations should really be mitigated by with a USS in the loop, so that UAS and USS do it in integrated manner. And we really need to do some more R&D for enabling BVLOS and urban operations. And we hope, I hope to work with you all to get that going. So that is the end of this presentation. And now we will be entering our first Q&A session. And I think that's mistaken, but the chart-wise. But I'll hand it off to Marcus to have us go through the Q&A.
Thanks, Jaewoo. And again, thanks everyone for sticking with us. You've asked some great questions throughout each of the presentations. So I'm going to be highlighting a few. I'm going to kindly ask Jeff and Joey and Jaewoo and myself will be trying to address these questions as best as we can. We may not get to all of them, so I apologize for that in advance. But let's kind of jump into it. So I'm going to start a little bit on some of the concept level discussion. So we're going to start with Jeff. And one of the questions that was asked was with respect to emergency response operations, and really, how does UTM support the emergency response? How is collaboration done? How's negotiation done? And ultimately, how did we consider support of these public safety entities and emergency responders through the UTM architecture?
Hey, Mark. Yeah, thanks for the question, and it's a great question and one that's on very topical at the moment. But it is one of, if we look back at Joey's earlier presentation, the integration of public safety operations and their needs are kind of one of the core principles of UTM that were laid out very early on, and we've spent a lot of time in the subsequent TCLs trying to understand, work with different public safety organizations to understand their needs for being able to integrate into this commercial environment that's going to be potentially highly dense and complex. And so how do we accommodate those operations in the midst of that type of environment? And so throughout the TCLs, we did build out certain elements of the data exchanges for priority operations and be able to communicate that out with the rest of the UTM system and other operators to give them the prioritization when it's needed to be able to interact, to respond to those types of situations. And then continuing to work with the different organizations that are really involved in it. So these types of response operations are they're different across organizations. There's local types of use cases between police departments and fire departments, but there's also public security or DoD types of perspectives as well. And then looking at some of the larger types of events like natural disasters, where we're looking at wildfires and earthquakes. This will come up later too, some of the work with JAXA in understanding emergency response operations and how UTM can help facilitate a more effective response. And then some of the work you touched on, Marcus, with Stereo going on now, which is looking specifically at kind of UTM applications, in part UTM applications for these types of situations. And so it is very much within our hearts and minds for UTM, and it's continuing on in some of the future work as well, and in support of developing standards around those needs as well.
And thanks, Jeff. And I think that covered very nicely kind of our our thoughts and how we kind of, again, baked in some of these considerations on priority operations and some of the mechanics on how these things could be facilitated and the follow-on work associated with continuing to explore those within NASA and even outside of NASA. Now, while I have you, Jeff, I have another question that was posed while you were talking about concepts and use cases, which corresponded to really, is there any work that's been done on the pilot user interface requirements? I think we talk a lot about USS to USS type of engagements. We even talk about USS to FIMS. But what about that other interface between the USS and the operator, or even between the operator and the information that they're seeing about the rest of the UTM ecosystem? Can you talk a little bit about that?
Sure, that's another great question where early on, I think we were not necessarily being prescriptive on these types of considerations within UTM. Some of the early, thoughts were that this is going to be a very highly automated system, and the intent was not to have a whole lot of human in the loop types of interactions. But I think it's clear at some level, and as a progression, there's going to be humans in the loop somewhere. And we did realize that fairly early on, and so we've had a number of human factors research efforts going on, starting, I would say, since the beginning, really, and then really getting more focused starting in TCL2 and beyond. There's a number of reports that have been published on some of that work, and as part of that, supporting that work for each of the TCLs, we had a number of really great researchers that were deployed out to the field to basically embed with the different operator and flight crews to understand these interactions and understand what are the key pieces that we need to account for in building out these types of eventual requirements or guidelines or recommendations that are coming out. Those reports, I think Lynn Martin is going to be presenting on this topic a little bit later. Those reports are a great resource to kind of understand the outcomes of some of that research. But the clear message very early on was that you need this situation awareness as operators and as stakeholders of the airspace. You need some way to have really good understanding of the airspace, planned and active types of operations, to have that necessary awareness for decision making, or at least just for having that common operating picture. And that changes, of course, depending on the environment and the types of missions. But that's really a key element there that I think UTM is able to enable, but we do have to make sure that we are having a kind of a standardized approach to it at some level. And this ties into some of, like your topics, Marcus, with the altitude referencing and being able to have that common, not only at the kind of message exchange level, but how that's being presented to the different people that are making decisions. That's definitely an area of need and continued work as we go forward, and I think we have a good framework that we've established within UTM through that human factors work. But it's going to be a continued need and an interesting area to keep exploring, I think.
Thanks, Jeff, and I appreciate it. And we definitely look forward to Lynn's presentation later in the day that details some of the findings from our human factors evaluations. I'm going to shift gears a little bit and start talking to some of the questions associated with the architecture. So this question was pointed for Joey Rios, and it was talking about will there be a FIMS capability, and will that capability be spread, kind of distributed to a number of different FAA data services? So maybe talk a little bit about FIMS and where you see kind of FIMS going.
Yeah, it's a good question. Thanks, Marcus. So there's two different things when we talk about FIMS. There's FIMS as it's kind of designed and deployed at the moment in terms of supporting USS to USS communications and some simple data exchanges perhaps, and a set of capabilities that would be provided by the ANSP in the future to support future operations within UTM. So it is better to think about FIMS as a collection of capabilities that may actually have a different name other than FIMS in the future, depending on what those needs might be. It's easier when we discuss it just to bundle them all under one umbrella and call it FIMS. But just think about the FIMS as we talk about it as being a collection of capabilities that may have different endpoints deployed at different systems within the FAA, but trying to make the process of connecting to those and providing the right data and getting the right data from that FIMS umbrella as transparent as possible for the operators and the USSs that have to interact with it. So I guess to lengthen this this answer a bit more, yeah, I think that FIMS is more of a set of capabilities that are provided by the ANSP to support the UTM environment, and they may look like different systems in the future, but conceptually they're a set of services provided under this umbrella that we're calling FIMS.
Thanks, Joe. I think that was an excellent answer, even if it was a little elongated. I'm going to talk a little bit. So there was a question that talked a little bit about deconfliction and kind of in a nutshell, kind of the roles associated with deconfliction. So the question is are all entities deconflicting with themselves enough? And particularly as you start moving to high density operations, is strategic deconfliction kind of the only thing you need? And things like surveillance, are these things that should be provided from local governments as opposed to from the industry? So maybe comment a little bit on kind of the strategic deconfliction and the nature of these supplemental data services.
Yeah, so there's definitely a lot in there. So I might not hit it all, but I'll try and touch on some of it. So strategic deconfliction right now, we did come out with a set of high-level requirements for what strategic deconfliction should be and should do within UTM. We published that a few years ago, and it is available. But it is very high level. It just kind of talks about the qualities of a strategic deconfliction system in the UTM ecosystem, right? It doesn't specify algorithms that must be used. So there is research that still needs to be done to figure out how strategic deconfliction needs to work in the long run. And a few folks are looking at that now. But what I would say is that what the approach that industry has taken, which makes a lot of sense, is they want to get a minimum viable product out that allows some delta on today's operations to start to occur at scale. So in order to enable more operations than there are today, we don't need a full advanced capability for strategic deconfliction. Simple intent exchange, allowing for folks to understand if and when they may be intersecting with each other, without necessarily going through all the complex, negotiations or other deconflictions that may have to happen in denser scenarios in the future and more highly automated systems. So it's going to be a progression. We don't want to wait for the perfect solution before we deploy anything. So I think industry and the ASTM standards are taking the right approach and trying to find the right bite-sized chunk to get the ball rolling and to get the FAA to buy into, so that we can start to see some of these services deployed. Now, in terms of other things like the SDSPs and surveillance, I think folks get a little nervous when you call them supplemental data service providers, because it makes it sound like, well, you're making it sound like it's not a primary function of managing the airspace to know where things are, right? Where we know it's very important to know where things are, and therefore surveillance is important in this ecosystem. It's a name or a term that is stuck. Primary in this case is, the data exchanges of the key systems within UTM being the USSs and FIMS, supplemental being the other stuff. That doesn't mean that it's less important necessarily in some environments. So we tried not to make the business case for UTM, right? We tried not to decide the right solution in terms of who deploys what, when, and for how much and for how long. We tried to show technically what the right way to do it would be. Now, it is up for industry and other stakeholders to now figure out how can we get this done collectively in a safe way, right? Is this something that the FAA has to do, or is this a solution that we can come up with in conjunction with local agencies, jurisdictions? So there's perfect answers for all of them in all environments, but I think it's important that we kind of set the table for them to have those discussions without necessarily prescribing the solution from a NASA perspective.
Yeah, and just to echo your position, I know as the architecture had evolved, originally a lot of the boxes on the right were kind of just this operator, right, at large. And we part of the discussions was actually breaking apart the USS and the supplemental data service providers so that industry could actually see themselves in their own individual business cases within the architecture. It doesn't mean that a single provider couldn't offer surveillance as part of a USS service. It allows flexibility within the industry to meet the needs of where they want to have their business and offer their different capability, and maybe not take on all requirements all over the place. I think was the general approach.
Yeah, and one other point to that, it's kind of interesting to note is when we're talking about the questions of the services that the FAA should provide to enable these operations, folks are going to have a lot of different perspectives, and kind of the balance that we want to strike is, having the FAA provide things, and from other folks' perspective, having them end up being a bottleneck because of that, right? Or not being agile enough to respond to business needs, right, in the future, versus why are you leaving industry hanging by not providing these services at all, right? So that there is a balancing act, and by providing this architecture overall, at least we allow that discussion to happen and have folks try and figure out the right way to provision these services.
All right, thank you, Joey. I think that was a great response, and in talking a little bit about strategic deconfliction, I'm going to shift gears a little bit. Part of this question was associated was strategic deconfliction enough, and that really bled very nicely over into the conflict management model. And as I had talked about in my portion, my briefing, I think we acknowledge that there's limitations on what an aircraft can do alone. And there is some interoperability considerations that are necessary. I think the opposite is true when we talk about strategic deconfliction. I think it doesn't necessarily, in and of itself, address all of the collision hazards out there. So there needs to be other systems that complement it, and it needs to be more of that continuum of conflict management that goes from the service provider down to the operator of the system, the aircraft system. So along this line, there were some follow-up questions that were associated with geofencing and kind of how that fits into the scheme of things, right? So the question is where do geofence fit within the UTM conflict management model, and should geofence limit avoidance maneuvers? And this is actually a very complicated question to some extent. It's simple in its nature, but it's actually complicated to answer. So the short answer is geofencing is in many systems are kind of these pre-programmed areas in which you stay out of, or areas in which contain your operation. The way that materializes is it works fine when you're the only one that's flying in the sky. However, as you start integrating into more of, again, the conflict management model and having to consider interoperability and the fact that you may be changing your operation during, while you're aloft, you need to consider geofencing, or what we call flight containment, and maybe a couple of different ways. And one is that it's something that maybe isn't always static. There may be kind of a static areas that you definitely cannot go in under any circumstance, right? And then there may be other areas where you can still operate and change your geofence, in which you're trying to maintain conformance to your prescribed intent. So this is, again, in many systems today, it's a little bit of a departure on what you typically think of as a geofence. Now, the second part of that question was, should geofence limit avoidance maneuvers? I wouldn't say, again, if you now start thinking of geofencing being, there's certain areas in which you want to really adhere to a geofence. Like if I put a geofence around a building, I want to make sure that I don't violate that geofence, right? And then there's other instances in which I have what would be considered more of a soft boundary, where I could violate, but it's just less preferred, right? I think when you think of that in the terms of kind of how you're instantiating your conflict, when you have an avoidance maneuver from a DAA system, it actually needs to consider the context around that geofence. So it's not a quick and dirty answer that says, yes, you can always violate geofences. I think the DAA solution, or the conflict resolution solution, needs to consider the geofences when it's deriving conflicts or deriving resolutions, right? And to that regard, I think soft boundaries may be acceptable for you to violate, and hard boundaries may not be. And so that may constrain some of your conflict resolution maneuvering to areas in which you can both achieve, resolve the conflict, and actually stay within kind of these harder geofence boundaries. To that regard, there was also another question associated with geofencing is there a plan requirement for UAS to be pre-programmed to preclude inclusion into controlled airspace? For example, placing autonomous restrictions on UAS operators, ensuring small UAS are not physically able to climb above or cross lateral confines of Class G airspace. So this is basically describing kind of the similar mechanism with geofencing. To some extent, this exists already in many systems where you can prescribe where you can fly and where you can't fly or contain your operation. It does not have the flexibility that's needed to support the scalable operations. And so there needs to be a little bit more work on kind of redefining how we look at geofencing or flight containment and how that actually interoperates with the other parts of UTM and the other parts of the conflict management model. All right. So I blabbed on for a little bit there. I'm going to switch gears again, put Jay-Woo on the hot seat for a minute. There was a question that was posed for communication and navigation that was focused on, is WAS needed, or what augmentation is needed for GPS or the GLONASS?
Oh, yes. WAS would be great because for small UAS, we are pushing to understand the navigation performance need in terms of navigation accuracy, integrity, and continuity. And by having WAS, some of the integrity and continuity issue would be helped. Having said that, though, the WAS satellites are at the location, and from US, those satellites are at relatively low elevation angle. Therefore, using them at urban setting may not be the best thing to do. So that would be my answer. And then, well, GPS and GNS, it's not only WAS, right? There are European WAS-like system up there, and then Japan has one up there as well. And I think Japan was actually situated so that it's a fairly high elevation from Japan area. So yeah, so considering all those, WAS would be very helpful.
All right, thank you, Jay-Woo. And while I have you, there was another question that was associated with how are urban aerial obstacles handled? And they gave some examples of antennas, guide wires, power lines, etc.
Very good question. So we've been advocating for so-called very low altitude chart. And the idea is to come up with a fairly rapidly updated, perhaps machine-readable version of this chart, so that operators and UA can use to avoid these things. Having said that, we were also advocating for on-board capability to detect these things. And wire detection is not a new thing. They've been working on it since days of helicopter operations. So there are technologies out there to do this. So by combining those two, perhaps this area could be addressed. At NASA, perhaps Corey will talk about this a bit. We've been also developing a SLAM capability, which can be used for this as well. But the very low altitude chart, though, the UTM project didn't really have room to elaborate, and perhaps it can be investigated further under other projects.
Sorry, trying to get off mute here. Thank you, Jay-Woo. So I want to add a little bit to that because there was a little bit of obstacle avoidance considerations associated with the conflict management technologies, and there were some technologies that were identified as being relevant. One of the, I think, the key things that that we run into is kind of the limitations of the different technologies that you really can fit on these small aircraft. So when we talk about obstacle avoidance and we talk about the need for being able to be able to detect these really small things, I think UTM and mapping can provide some solutions that can help with that. There is onboard capabilities that may be necessary as well, but it's going to be balancing essentially the other risks and hazards that it has to account for. So if it's flying in airspace that is heavily trafficked with manned aircraft, right? It has to balance the fact that it may need a DAA that sees out a little bit further. Whereas maybe this is really important for urban operations. It can back off on the DAA system that's on board, rely a little bit more heavily on services, and then provide, allow for a little bit more of your swap budget to be allocated towards obstacles where they may be more present in that urban environment. So I think it is a combination, or it can be a combination of both kind of these mapping and onboard capabilities, but it is most certainly needs to be geared towards the environment in which they're operating. All right, let me look at my list here and see if there's any follow-on questions. Okay, so here's a question for Joey Rios. So what allowances is the UTM making to assess the UAS, UAM capabilities before authorizing access to specific airspace?
Yeah, it's a good question, and one thing I'll caution is we don't want to blend too far into the UAM domain. That while we're leveraging and learning from the UTM environment to cover what's needed in the UAM environment, there will be some differences. But in this sense, there may be some similarity. In the ConOps documents published by FAA in conjunction with NASA and through information we got from our partners, there's this concept of a performance authorization that is something obtained from the regulator or the ANSP. And that performance authorization lays out the types of operations, environments, and equipage and all the things that are needed for them to perform certain operations. So conceptually, that's where we're headed, that an operator would be able to outline what it's allowed to do and with what vehicles it's allowed to do it with. And through the exchange of that performance authorization in an automated, digital, machine-readable way with the USS, USS can understand that the operator is allowed to perform the operation that it's asking to do. We think that concept does evolve into UAM. Again, there would probably be different requirements, different data elements, but conceptually the idea of a performance authorization is the means by which an operator would let a USS know what it's allowed to do and with what equipage. Hopefully that hits it, but I would recommend taking a look at the version 2.0 of the UTM ConOps or the initial NASA ConOps for UAM to get a little more perspective on what a performance authorization is supposed to be.
Perfect. Thank you, Joey. And so we'll wrap up with this last question here. This question was for Jay Wu, and it is GPS the primary means of location identification for UTM, or will alternate methods, in the example given was machine vision, be considered?
Yeah, very good question. In broad sense, location identification has two flavors. One is for UA to know where it is in relevance to surrounding. So, if I'm doing a building inspection, then perhaps all UA needs to know is how far away it is from the building. And the other is more global sense, where in the world, if you will, that UA is. So GPS would be really good at the global one, and then machine vision could be really good at the local one. But why not stop there? There are other navigation source, actually navigation and timing sources, one that can come from the satellite, and then one that can provide it from the ground. And not endorsing a company here, but companies such as NextNav provide such capability. And then UA onboard things such as machine vision and LiDAR, radar, ultra sounds. All those can be really integrated into a solution where vehicle knows where it is in global sense and local sense, and if needed, switching between them seamlessly. So that would be my ideal outcome of this direction.
And I'll add a little bit to that. I think from a surveillance standpoint, fundamentally UTM is based off of dependent position reporting from the operator, right? That's how USSs get their information or one form in which the USSs get their information on where that particular UAS is located at in order to do things like conformance monitoring and so on. But there's also, with the remote identification rule that came out, there also will be broadcast as another form of being able to identify where UAs are at, particularly if service providers decide to put up any sort of infrastructure in place to actually pull that broadcast off or solicit that broadcast more frequently. The other means in which surveillance could be provided, I think, are fall within some of the conflict management model and some of the ground surveillance. Again, these things tend to be a little bit more on the optional side of the house, based on kind of conflict management strategies that operators are taking. But they can be dual purpose in terms of location finding as well. And even to the level of when we get to the point in which we have higher densities and V2V type of interactions, that can be a means in which you can communicate with other aircraft and kind of relay information back into the UTM system in an indirect path. And we had kind of this concept, a white paper that was generated called a UREP that kind of accounted for self-reported positions that weren't coming from the operator. So there's many different flavors of a location identification. I think as you start looking at some of the more foundational elements, GPS does play a role, but it's not the only technology that can feed into the UTM ecosystem. And with that, I think we've come to the end of our question and answer session. I wanted to thank Jay Wu and Jeff and Joey for their insightful comments, and we will pass it back off to you, Jay Wu, for bringing us into the lunch break.
Yes, of course. I shall not delay us from lunch any further. So let's enter our break for 35 minutes, and we will resume 11:30 a.m. Pacific time and 2:30 p.m. Eastern time. And we hope to see you all back then. Take care now. Roughly, we're halfway through the team. So far, a great amount of activities and interactions has happening. So I welcome that. And please continue submitting your questions through conferences.io so that we can address them at the second Q&A few presentations later. Now we have Arwawi's, who has been NASA UTM flight test director for many of our tests. And here she will talk about UTM technical capability level overview. Arwa, please go ahead.
Thank you, Jae-woo. So you've heard about the TCL demonstrations mentioned throughout the presentations this morning. And right now, I'm just going to give you an overview of these presentations that we've conducted in the past 5 years. So first, I'm going to talk about the TCL test that we did at Crow's Landing and then at Reno. And then I'm going to be talking about the TCL-2 national campaign, as well as the TCL-3 and 4 flight demonstrations, give you some highlights and the objectives and a brief summary. Next slide. So you've heard in previous presentations that we took an approach of testing in a progression along 4 TCLs. And these were based on the type of operations, the density, the environment, and the procedures that were required for a UTM airspace environment. Next slide. Okay, so first let's take a look at the TCL-1, which was looking at remote areas with low traffic density and multiple visual line of sight operations. First field test was at Crow's Landing, and this was in August of 2015, and this fit the environment we were looking for at a TCL-1 level. It was a remote populated area. We had many partner organizations and flew 10 different UASs. We were able to complete simultaneous visual line of sight operations. We had several objectives that were related to the initial UTM prototype and some of the vehicle performance tests. And here, like you heard before, we didn't have the federated system during TCL1. Next. So then we had the TCL1 national campaign, and this was the first time we tested with 6 of the FAA US test sites, which were Alaska, Nevada, Texas, North Dakota, New York, and Virginia. And this happened in April of 2016. We had about 20 different organizations that flew 17 unique vehicles, and test sites flew at 7 different ranges. NASA had 4 goals and objectives, which I'm going to talk about next slide. Okay, so from NASA's perspective, we were interested in having 24 distinct vehicles that were flying and connected to our system within the same hour. Important to us was to expose these test sites to the prototype and try to figure out how these tests can continue at these test sites. We wanted to try understand the potential applicability of the system, and we wanted to load a research platform to try to look at different clients and see how things can fly in a live environment while having simulated flights. So this initial prototype was able to provide situational awareness for all of the operators. It was able to keep traffic separated, and it was able to offer messages to the different participants about the relevant operations. Next slide. So next up was TCL2, and for TCL2, we conducted testing in 2 different ways. One was in Reno, and then the other one was with conjunction with the 6 test sites again. Next slide. Okay, so for TCL2, we tested at the Reno State Airport in October of 2016. We had 14 partner organizations that flew 11 different US platforms. We were able to complete simultaneous altitude stratified operations. Our main objectives here were related to the 5 core UTM principles, which were that the US should avoid each other in other aircraft, that the operators should have the same awareness of the airspace, that public operations would have priority in this airspace, and that we should try to be flexible when it was possible in the system. Next slide. So this TCL2 testing in Reno focused on the feasibility, functionality, and the applicability and integration. So we were able to have expanded multiple operations, and feasibility was successfully demonstrated because we were able to fly multiple beyond visual line of sight operations using our air traffic management system. We demonstrated the functionality of key functions in the system that help support these operations. And we successfully integrated many partner US systems into UTM. And we were able to collect some data that would help us look at information sharing requirements. Next. Okay, so 6 months later, in the spring of 2017, we went back with the 6 test sites. Here they flew in 9 different ranges with different environments. We had about 20 different participating organizations. 32 different vehicles were flown. And for this, NASA had 6 research areas and flight objectives that I'm going to talk about next. Next slide. Okay, so for now, we instantiated the UTM architecture using the federated system. And for here, we wanted to demonstrate, evaluate, and refine the designs, the technology prototypes, and the UTM CONOP. And we were interested in testing in diverse environments using different platforms. So that's what we were able to do. And we were able to test with more than 1 USS. And a very important thing for us was to try to accelerate US stakeholder development of the UTM components, specifically the USSs. Next slide. Okay, so as I mentioned, we had 6 areas of interest, and these were related to the TCL2 technologies, as well as things related to scheduling and planning capabilities, conformance and geofencing capabilities, and even looking at human factors to try to understand the display that's necessary. And we requested that we have different types of operations. And these included things such as altitude stratified operations beyond visual line of sight. We wanted to have a dynamic replanning situation. And we also wanted to look at different responses to UTM alerts and also look at contingency implementation. Next slide. Okay, so this is just a more detailed view of the vehicles that were used, as well as the operators and USSs that participated in TCL2. We had 32 vehicles and was a very good mix of fixed wing, multi-rotor, and hybrids. We had 14 operators overall, and these included companies such as Carbon Autonomous, iSight, and Lone Star. We had 6 different USSs, and here was interesting because we were able to get more than one USS at 2 of the different test sites, and this was very useful for us because that was the chance for us to start trying to understand the interchange of data and the communications necessary between USSs. And in some cases, like for example, Amazon and Google, they were both acting as the USS and the operators in the same flight test. Next slide. Okay, so as part of our testing, the vehicles were supposed to fly profiles that emulated real-world use cases. So for example, we had package deliveries, farmland surveys, infrastructure inspection, and even some search and rescue missions. And we asked the test sites to craft these so we could test different capabilities of the system, for example, lost link procedures or responses to alerts and so on. And some of the scenarios actually included simultaneous operations that were interacting with each other. And that was very useful because we were able to test several objectives at the same time. Below here are just some examples of the scenarios that were flown at the test site. So one of them conducted 4 simultaneous altitude stratified operations. Another one tested the dynamic replanning when they had a search and rescue mission. Another one had 2 different USSs that were supporting 2 different operations. One of them was surveillance monitoring, and then the other one was a package delivery in Virginia. Next slide. Okay, so to summarize key aspects of TCL2, the partners were able to submit flight operations to 6 different USSs, including NASA's. They flew in 9 different ranges with different environments. Some of these flights were observed by both ground and airborne surveillance systems, and then the relevant data was sent to the corresponding USSs. So TCL2 basically provided us the initial validation and then the potential flexibility and scalability of this UTM CONOP of a federated system. And from NASA, it was very successful because both NASA and the partners were able to make progress in developing the components that were needed in this UTM system. Next slide. Okay, so next we moved on to TCL3, and here we tested in more moderately populated areas. We had increased traffic levels and had mixed suburban operations. Next slide. Again, this is just an overview of the flight demonstration. This happened in the spring of 2018. Again, we partnered with the 6 different test sites, and this time they flew in 7 diverse ranges, and they covered things such as high altitude, different weather, different terrains, and so on. We had 30 organizations that participated, and they flew 31 different vehicles. For TCL3, we wanted to focus on 4 test types, and these were related to the UTM RTT groups that you heard about earlier. And I'll talk about those more later on. And then for this demonstration, we also had 11 unique use cases. So we were able to show some package deliveries, infrastructure inspections, even disaster response and contingency management. Next slide. Okay, so for TCL3, we wanted to continue to demonstrate, evaluate, and refine our new UTM prototype, but under more complex regions and with more US platforms. Also important was to continue accelerating the US stakeholder development of the UTM components, which were the USSs. And as I mentioned, we tested things related to the RTT working groups. You heard about those earlier. Just as a reminder, for the concept use cases, we were interested in exploring operations that would refine the UTM CONOP at different environments and different TCLs. For the ComNav and surveillance, we wanted to evaluate solutions that would help us make sure that aircraft stay in operational control and within their defined regions. For sense and avoid, we wanted to look at different strategies to see mitigation strategies and the type of things that needed to happen between airborne versus ground surveillance. For data exchange, we wanted to look at some of the off-nominal situations, as well as try to understand what gaps we might have in the data models that we had at that point for the USS information requirements. Next slide. Okay. And you might have seen this earlier today, but this is just basically a broad overview of some of the technologies and capabilities and concepts that we were trying to demonstrate through the TCL flight tests. So for example, we looked at communication and navigation such as V2V, DSRC, and C2. We also looked at sense and avoid capabilities, things having to do with ground and airborne radars and obstacle avoidance, and also the USS and FIMS interchange. And this is something that Joey talked about in his presentation earlier today. Next slide. Okay, so next was TCL, the TCL3 operators, USS, and participants. Here we had 13 different operators, such as Intel and Drone America, Aeros, Rockwell Collins. We had different USSs, 8 of them overall, such as Amazon and ANRA and AirMap. And we even had 8 different surveillance and sensor companies, including UAvionics, AirRobot, and Echodyne. Next slide. So as I mentioned, we were focused on research areas that had to do with 4 RTT groups. So some of the things we wanted to test had to do with USS failures, negotiation, what type of negotiations were the USSs interested in having, things with the concept cases, things such as public view, what should the public see? Also, what would happen if there's a breach of controlled airspace, who needs to be notified? For CNS, we looked at things such as the radio frequency interference. For sense and avoid, things such as the air-to-air conflict mitigations, as well as system-level mitigations and off-nominal procedures. Next slide. Okay, so just to summarize some key aspects for the TCL3 flight demonstration. We focused on testing the research objectives of the 4 UTM RTT groups. And as you've heard earlier today in some of our presentations, we were able to develop and test systems that helped improve navigation, long-range communications, and sense and avoid capabilities. We were able to test existing technologies so we can determine potential improvements that were needed. And we even developed and tested new tools that would help operators and people understand more about the airspace environment. We continued to accelerate partner development of the UTM components, especially the USSs. At this point, we had 8 of them, including the NASA prototype. And something very important was that TCL3 will develop the UAS remote ID capability. So overall, TCL3 helped us identify the gaps in the data model, try to understand the interfaces between the different components in the system. It helped us refine the UTM concept for the different TCLs that we were looking at and the different testing environments. Also important was it assisted us in developing performance requirements and guidelines that were needed for future SAA and CNS operations. Next slide. Okay, so then we moved on to TCL4, which was testing in urban areas. And this was exciting because this is what everyone was waiting for, to test in actual urban areas. So just some highlights. Next slide. This time around, we partnered with 2 different test sites, Nevada and Texas, and they flew in 6 different ranges, which I'll show you later on. This happened in the summer of 2019. We had 35 different organizations. We had 8 unique vehicles that were outfitted with different equipage that we wanted to use for testing technologies. And we had 5 different scenarios that NASA developed in conjunction with the RTT groups. And we had 24 test objectives overall. Next slide. Okay, so like I said, this was very exciting because we wanted to test operations that were more complex, that involved more aircraft and dense airspace. So basically, we were testing our UTM in a true urban environment. And this test, we had 7 USSs participating. Like I mentioned, we had onboard technologies. So we tested things such as separation, collision avoidance, identification, navigation, and safe landing capabilities. Basically, what we wanted to do was to try to see what happens if we had real-world events, so responses from the system. Some things had to do with UAS to US encounters. Others had to do with obstacle avoidance. We also wanted to look at loss of comm links and things such as dynamic airspace constraints. Next slide. So I mentioned the 5 scenarios that we designed were supposed to represent a day in the life of the US operations. So things that could happen in different environments while the US were flying. So each of these scenarios had multiple required missions, defining characteristics and triggering events that I'll talk about later. And all of these were designed to help us exercise the different procedures and technologies in a TCL4 environment. So these 5 scenarios had to do with things such as weather events, airspace restrictions, mixed operations with manned aircraft, US obstacle collision, and USS failure. Next slide. Okay, so this is just examples of some of the scenario characteristics that I mentioned. We had 39 in total. We requested things having to do with high density and high tempo operations. We wanted to look at remote ID. We wanted to have rooftop operations. We wanted to look at public safety operations, just to name a few. And then for the triggering events, we had 16 overall. And like I said, these were going to help us study real-world responses to different events that could happen. So for example, we wanted to have UVRs. We wanted to test safe landing procedures. We wanted to look at large-scale loss link and things such as the USS negotiations. Next slide. This is just a more detailed view of our partners. This time around, we had 7 USSs, including Uber, Elevate, Vision Robotics, and OneSky. We had 8 different US operators, such as ABSI, the Utah State, and Lone Star. For onboard technologies, we had 8 different companies. For example, we had RTK that was providing a navigation truth source. We had Drelmatech helping with the remote ID, and we had Fruity Shoots, which provided parachutes that were equipped on the US and the Nevada aircraft. And we also had 4 different ground systems participating. For example, Fortem provided radars, ACAMP provided some weather stations, just to name a few. Next slide. Okay. So before I go on to show you more details about the demonstration, I'd like us to watch a quick video for some of our TCL4 operations. Okay. Okay, I hope that was interesting for everyone to see. So guess move on to the next slide. Okay, so as I mentioned earlier, we had the 2 test sites test in 6 different areas. Nevada chose to test in downtown Reno, as well as a nearby park. Next slide. Okay, and this is just a view of the UTM generated volumes for some of the UAS that were flown. Next slide. This is a picture of 4 of the US flying simultaneously in downtown Reno. You can even see Harrah's hotel in the background. Next. These are the 4 areas that Texas chose to test in, and it was in the city of Corpus Christi. So they tested at the port, at the art and entertainment district, downtown, and the waterfront, and even in the Corpus Christi airport. And for this, we even had the police department participate by using the remote ID functionality. And the fire department actually flew their own UAS to try to test emergency priority operations. Next. Just another look at the UTM generated volumes for the Corpus Christi flights. Next. Picture of two USSs flying in the urban canyon in Corpus Christi. Next. Okay, so even though we called these flight demonstrations, it didn't mean all we cared about was just seeing the US fly. As I mentioned throughout this presentation and from what you heard from previous presentations, the RTT leads, we also cared about collecting information that would help us try to refine the CONOP and try to understand the technology gaps and the guidelines that would be needed for future flights. So from this data, from the data for the flights, we were able to calculate measures of performance, such as these, and these had to do with the RTT working group research, the concepts, data architecture, sense and avoid, and ComNav. Next. Okay, so TCL4 was able to have complex multi-aircraft operations over buildings and near densely populated areas. We were able to have a network of 7 USSs that were provided by industry, manage these US operations. UTM was able to safely manage a large number of the US in crowded areas. The UTM provided a secure and efficient platform for the users. The remote ID was tested and it showed that it was found feasible. We had a lot of integration that needed to be done with onboard technologies. And next. So these are some of the ongoing challenges. We have to remember that there was performance, reliability, and integration of onboard capabilities that were still a challenge. There were environmental factors that remained a concern for safe operations. We had a large variation in platform maturity, and it was important for us to continue having conversations and input from municipalities because we needed them to try to have safe and secure flights. And then the last slide, next. If you're interested in learning more, you can look at some of our publications for more detailed overview of these 4 TCLs, and this is just a list of those papers. And you've seen throughout the day also, there were a lot of publications on the data and research objectives that you can look at. Thank you.
Thank you, Arwa, for a comprehensive review of the TCL tests that had happened throughout several years. Now we will transition to Dr. Corey Ippolito, who led UTM task investigating advanced airborne autonomy for urban flight operations. Corey, go ahead.
Awesome. Thank you, Jaewoo. My name is Corey, Dr. Corey Ippolito. I am the NASA UTM lead in airborne autonomy for the urban area operations. Next slide, please. Throughout the UTM project, the group that I was leading was solely focused on analyzing the urban environment for UTM and UAS operations, really from the viewpoint of airborne autonomy. We're specifically looking at high density operations scaled to the level of demands that we've been anticipating from various independent market studies, and focusing on commercial point-to-point flights that have some range to them, kilometer range or more, that traverse through the urban landscape. This captures a significant number of the commercial use cases that have been proposed by our additional partners. Urban environment is one of the most challenging environments for the UTM. I'd say it's probably the most challenging, especially when UTM is looking to allow continuous, routine, safe operations of UAS inside of these environments. On the UTM project, as Arwa just summarized, we touched upon the urban environment in the TCL4. But as Arwa mentioned, and as other presenters like Marcus Johnson described in earlier presentations on the RTTs, there are still open problems and future lines of research that need to be done to address some of the challenges that are still faced in this environment. Next slide. So briefly, I'll just touch on what are some of the challenges that make urban area operations different than other areas and why it's so difficult. One of the challenges, specifically in the point-to-point design case in the urban environment, that results in flights that are largely beyond not only visual line of sight, but beyond RF communication line of sight. From a fixed point, as soon as you go operating in the urban canyon, as soon as you turn around a building, for instance, you'll quickly lose not only visual line of sight, but you'll also lose communication linked to the vehicle. It's a very challenging RF environment. In our particular task, we were not assuming that there were going to be any significant changes to the environment. So we were assuming that we would be able to allocate specific frequency ranges that would be protected for UAV operations. We were utilizing shared common frequencies. We weren't considering significant changes to the urban environment. We weren't looking at instrumenting, for instance, each building with lots of different sensors to help navigation. Certainly that would be a viable approach to solving this problem, which might even be a little easier to solve if you're able to instrument the paths you're planning on flying with sensors to help the navigation problem, to help obstacle avoidance, for instance, and also being able to put repeaters, different types of transmitters on buildings to help the communication and navigation problem. But in our particular study, we're looking at leaving the environment unchanged and solving the problems with the onboard autonomy. So one of the biggest challenges is as you go into the urban environment, you are no longer able to keep a separation between your aircraft flights in a flight geometry which is separated from people and property. As defined by an urban environment, you're going to be flying over property and you'll be flying over people. There's no guarantee that any place inside of the urban environment will be free of people at any given time. So if you, for instance, look at the bottom left slide, you never know when there's going to be groups of pedestrians, groups of people, things in the environment that are valuable that you do not want to damage and hit. So this is kind of one of the biggest changes as you go from from a rural type of environment or an environment where you can safely segregate your flights with sufficient spatial separation into this urban environment. Also mention GPS, for instance, is also challenged. Other types of RF communications is challenged inside of this environment. Next slide, please. So in our task, we defined autonomy as anything that allows the vehicle to see, think, and act autonomously without human interaction to achieve the vehicle's objectives and constraints. So the vehicle knows its constraints, it knows its own objectives, and it automates sensing the environment. So for instance, concerns with ground risk, concerns with buildings, it's able to sense the hazards in the environment, is able to understand, build maps, and be able to act autonomously without human interaction in order to accomplish the objectives. For the UTM tests, so for instance, for the UTM TCL4 test, we found that there was little autonomy in terms of this definition of autonomy. We had a lot of vehicles that could fly with manual control, direct pilot control, and could also fly with waypoints by programming and pre-programmed GPS waypoints. But very little in the way of vehicles that by themselves could map out the environment and could autonomously behave and respond to that environment in a way to achieve its own objectives. So why aren't there more commercially available autonomy? We identified inside of this task 3 main gaps, which led into our approaches and our main technical objectives. First, there was a concept and standards gap. There are no standards out there that say these are the types of autonomy that you would need in order to fly autonomously inside of an urban environment. No standards that have been developed, no requirements. What we found inside of the literature was a lot of different literature addressing this problem, but many of the authors were coming at this from different assumptions and different point of views. So a lot of the technologies that were being presented wouldn't work together with differing concepts, with changing the assumptions. So there wasn't this common understanding about how you would be operating. So our technical objective on this task was to conduct a system-wide study of point design to investigate what it would look like for a UTM-enabled autonomous flight inside of the urban environment. Second, knowledge gap. There's compared especially to manned aircraft, there's little understanding about how these vehicles behave in terms of the modeling and simulation. We're working with other teams here on UTM who had done flights, who had done wind tunnel experiments with the vehicles, taking those and making higher fidelity simulation models. Not only that, understanding the urban environment, we're trying to bring in better understandings of the wind turbulent models, which are very unsteady, which are very complex inside of the urban environment, which is very important for these small vehicles because at the scale and the speed that you're reacting at, these become important. Then technology gap. There's been a lot of research in the area of autonomy applied to UAVs, often specifically targeted toward operation of UAVs inside of an urban environment. But very little of that technology had made it onto some of our commercial partner platforms. We identified that there is a technology gap, and one of the ways we thought we'd be able to address this is not only through the concepts and coming up with standards to help advance the maturity level of the technologies that were at, a relatively low TRL. There's some great demonstrations, some great features which have been shown inside of the research, trying to get those onto to a commercial platform, get them up to maturity level so that they can be put into a commercial platform. We felt that we can help address that by developing a validated reference design architecture for both the vehicle and for both the autonomy. So for instance, if you're designing a flight control system, you can go to a textbook and you can pull up a reference architecture and you know what the requirements are and how to build that. That's not available for urban autonomy. So that was the third outcome goal for our project. I mentioned validated here. We validated through two methods. We developed simulations to the fidelity, I'd say moderately high fidelity, to the fidelity needed for validating our system study and our architectures. And we developed hardware prototypes and we did flight testing for point design validation. Next slide, please. Requirements. So generally, these were how we kind of grouped the requirements, especially for communicating out the requirements. The UAS needs to be aware of, for on-board autonomy, the UAS, the autonomous UAS needs to be aware of different types of ground objects. We classified them in two different categories. One are static ground objects and one are dynamic. Both of those kind of have fundamentally different roles in terms of risk when it comes to the UAS. For static ground objects, power lines, for instance, are one of the most challenging things to detect. Other type of cables also, because they're very long, they're very thin, they're very hard to see until you're right up on them. This is traditionally a challenge also in manned aircraft, where a human pilot has difficulty seeing power lines until they're too close, and so it's a known problem even for manned aircraft. It's definitely a challenge for unmanned aircraft sensing. And for dynamic ground objects, there's a need to try to reestablish that safety case to say, we're flying now over an urban environment, not quite sure where the people are going to be, and we know we're flying over property, but we need to maintain a safe awareness of the risk that we're putting to the people that we're flying and make sure that we still maintain that safety. Also to other aircraft, I'll touch on maybe on the top left block as well, a little bit about the GNS and degraded positioning. We touched on all these blocks. We have a lot of research lines that went into these blocks, so please look at the references at the end of this presentation and also on the website for a full list of our references, and you can read more. Next slide, please. Reference architecture, I'll just mention that we developed the full architecture, flight control system, flight management system, all the way up to high-level planning in our NASA system. And we integrated this into some flight test vehicles for validation. We decided to tie this in at kind of the outer level, outer loop flight control. The inner loops are typically more vehicle specific, so we try to keep it vehicle agnostic to the level possible. Next slide, please. And all right, so I'll just mention also that in the previous slide we have kind of two levels of planners that were in the architecture. One planner was doing guidance level planning. One planner was doing higher level planning, running at a lower rate. We had inputs coming in from various EO, IR sensors and LiDAR sensors, which are augmenting both the INS solutions with position for full state estimation, and as well as going into environment maps for the mapping and avoidance. I've mentioned here that we did implement these on hardware and various vehicle platforms. We developed hardware prototypes and did some flight testing for point production. All right, next slide. Okay. This here is a video of some of the work that research we did in integration of GPS into the IMU. One of the challenges with with localization inside of the urban environment is the GPS denied and GPS degradation that you receive. We looked at various forms of vision-based and LiDAR-based simultaneous localization and mapping. We found that overlapping the two, LiDAR did good in certain circumstances, vision does good in certain circumstances, but if we overlapped, they were very complementary to each other. Vision, for instance, didn't do as well performance-wise as the LiDAR did, but vision often would get wiped out when the lighting conditions would change rapidly. And we did several flights both indoors and outdoors looking at the integration of that. All right, next slide, please. These are old slides, but all right. So this was so we did simulation and testing. We developed various urban models, various simulation of sensors that we evaluated, including LiDAR sensors, sonar, vision. We ended up not really relying on the sonar inside of the main solution. We processed the data in several different types of structures for fusing the data together. One of the main structures we utilized was kind of a voxel map, kind of a Minecraft view of the world that you're seeing on the right. That as the vehicle flies along, you can put the vision and the LiDAR-based information together and utilize that for the planners. All right, next slide, please. Mentioned that power lines were one of the challenges. There is a lot of research into power line detection, but a lot of the research was looking at different angles, such as flying from the top and trying to identify where power lines are located. There was less research on when you're flying kind of at the level of the power lines. So we did a little bit of our own investigation to investigate techniques that we can use from the literature and see what we would actually get when we actually flight tested these techniques. We were able to recover about 75% of the sensor range in terms of LiDAR. LiDAR did better in our test than vision. We were able to get, and that might be just specific to our implementation, our testing, but you can read more about it inside of the references and the publications that are listed at the end. But we were able to recover about 75% of the range of that sensor. And this is tied together. This is important because the longer your sensor range is, the higher you can fly and the faster you can fly, which is tied into your flight envelope. You can expand your flight envelope range. It's also tied into a few other factors. So the longer the better you can detect things out further, the better you'll be. All right, next slide. Okay, this is obstacle avoidance. So this was kind of at the guidance level, tree-based planner. Again, this is kind of old slides. So this was shows kind of one of the earlier tests where there's a tree-based planner, and this provides the guidance laws for the flight control system, provides avoidance of dynamic ground obstacles, it provides avoidance for other airborne vehicles, and it maintains its position within the volumes. Next slide. Mentioned that there's a high-level planner that was doing a tree-based planner for doing the high-level objectives. Next slide. One of the good, we still have a slide on this in the pack. That's good. We're looking at collaborative see and avoid through V2V VDX. This is probably going to be my last slide here. Here we're looking at when you have overlapping high-density operations, vehicles, the concept that we were looking at would have vehicles being able to share information back and forth in a collaborative manner to be able to navigate relative close to each other and avoid each other. These were experiments we did with several different control schemes that we found in the literature and evaluated. Some of the schemes like this one worked well. These were we did several different simulations of different encounter scenarios. Here are encounter scenario with 5 different vehicles coming together and merging together on the same path inside of the same UTM volume. As they merge together, they're utilizing their shared collaborative control technique that will not only keep them apart from each other, but also end up giving them self-separation of self-spacing. All right, next slide. And this is some of the publications that I touched upon, but please see the website for the full list of publications. All right, next slide. That's it. All right, thank you very much.
All right, thank you, Corey, for a comprehensive overview of the group's effort past several years. Now we'll move on to Lou Glab and Maria Consiglio to talk about UTM flight testings done at NASA Langley Center. Lou, go ahead.
Okay, thank you, Jay-Woo, and thank you, Corey. It was a great presentation. So yeah, my name is Lou Glab, and I'm going to be presenting the UTM flight testing that was performed at NASA Langley Research Center over the last 5 years. I worked extensively with Maria Consiglio, who is the Associate Project Manager at Langley. And just to note that we were supported by a very enthusiastic and dedicated team at Langley Research Center. Please go to the next slide. Okay, UTM flight testing was performed at NASA Langley, complemented and extended the flight testing that was accomplished as part of the UTM FAA test site TCL series, and also collaborated with the work that Corey had just presented. There was a heavy emphasis on development, integration, and testing of onboard enabling technologies required for widespread U.S. operations that is envisioned in the UTM concept. Some general objectives and presentation of the presentation here. We're going to provide some insights, lessons learned, and describe next steps and follow-on work as able. I'm going to spend some time on the next slide to talk about the characterization of the UTM flight test, really to provide like a understanding of the large area that was covered as part of our flight testing effort. I am going to review some selected flight tests as time allows. I have a summary slide and a list of team members' reports, invention, disclosures, and license patents. There's a heavy emphasis on the flight testing, on development, integration, and testing of onboard enabling technologies required for small U.S. operations. Two focus areas for our work was in autonomous contingency management, as an example of the UTM Safe to Ditch effort shown in the photo on the right, 2018. And also there was a focus on autonomous sense, autonomous detect and avoid, as was included within our Icarus work that was shown in the UTM Isaac flight testing that was performed in 2018. And we'll talk about those efforts in more detail coming up. Okay, go to the next slide, please. Okay, NASA Langley team was there at the very beginning with either the first or near first live UTM operation in 2015. Very, very proud of that. Altogether, it is estimated that more than 1,400 research and development flights were completed over 5 years in support of the UTM project. So it was a large effort. We looked at a lot of different things in support of the UTM project. We had subsequent U.S. flight tests were performed to support an array of technical areas, or this list here presents a list of flight test objectives for a series of flight tests. So as I already mentioned, a lot of work in autonomous sense and avoid and autonomous contingency management. We also did flight testing to support vehicle-to-vehicle communication links as would be needed for autonomous sense and avoid. We also performed flight tests in support of the UTM traffic management system development and integration. So in TCL 1 and 2, we supported both of those efforts. We performed flight testing in support of assured range containment as the Safeguard project. For those who are familiar with that, performed some flight tests for autonomous power line inspection, human factors for UTM operators. I'll talk more about that. We get to the Pathfinder test. Communication and control links. We did some dedicated flight testing in support of that, especially 4G communication links. Some work integrated GPS. A real-time ground risk assessment tool was also evaluated as part of our testing. We did get to some autonomous merging and spacing near the end of the UTM effort, and also did some work in failure modes, effects, and criticality analysis, where we would inject failures into vehicles to determine that we understood the effects from those failures. We closed up in 2019 with the integrated UTM TCL 4 Pathfinder test. And this test provided an integrated system evaluation. So in this test, we were able to look at autonomous contingency management, autonomous sense and avoid, vehicle-to-vehicle communication links, as well as the integration with the UTM traffic management system, and also was able to perform a human factors assessment or generate some human factors results to support the UTM concept of operations. So can I get the next slide, please? Okay, the Isaac sense and avoid testing, as Icarus sense and avoid testing or characterization testing was the Isaac flight test. The objectives for this flight test are listed here. We want to evaluate the use of a micro ADS-B receiver to provide ADS-B in to support autonomous sense and avoid. We wanted to evaluate the utility of using that ADS-B in to provide effective small UAS autonomous traffic deconfliction. So this is UAS to UAS, as well as small UAS to general aviation aircraft. We wanted to assess the performance of Icarus system to support the traffic deconfliction and the effectiveness of reduced power ADS-B for small UAS applications. So one area that was a challenge is, how are we going to basically come up with an ADS-B system for small UAS, as the potential is there for a large number of UASs to potentially overrun the FAA's ADS-B system as currently implemented. So we did look at a reduced power way of approaching that. We also wanted to look at the well-cleared definition for small UAS and acquire high-res position correlated video for small UAS unmanned aircraft. And this video data was used to develop optical-based traffic detection algorithms. So for Isaac, we had two types of intruder aircraft. One was NASA Langley's SR-22. The other one was Tempest aircraft for the small UAS intruder. And then you can see in the lower right the on-chip vehicle that was used for this test. So the results from this were the micro ADS-B unit does provide effective input. However, we did observe that we were getting ghost targets from Mode C transponder rebroadcast. So that was something that was unexpected when we went into that test, and one of the things that we observed. So this also sets the stage for potential sensor fusion that might have to occur for doing effective autonomous sense and avoid. Icarus was able to maintain well clear of 2,000 feet for the testing and performed extremely well. Low power ADS-B does appear to be feasible, and by low power ADS-B, we're talking about power levels in the 400 milliwatt range versus the nominal 40 watt range that would be more consistent with general aviation applications. And lastly, low cost high res cameras can support well clear optical detect and avoid, and by this I mean we were using just simple consumer grade Sony action cams, but with the right algorithms and processing could support well clear for small UAS. Okay, next slide, please. Okay, UTM safe to ditch testing is presented in this slide. So the objectives of the UTM safe to ditch testing was to perform efficacy testing of this autonomous contingency management concept, assess autonomous machine vision, verification of the ditch site, demonstrate autonomous rerouting based on a ditch site state, and evaluate integration of safe to ditch with autonomous contingency management with the overall system. So safe to ditch is an integration of systems that could be used to monitor the health state of the vehicle, provide a ditch site selector, nav route optimizer, a vision assisted landing element, and adaptive controls along with an intelligent hub. We initially started testing on a very simple vehicle, a Y6, that was used kind of like a worst case type vehicle to use for this. It performed extremely well for our testing. And the lower right figure shows a representative ditch site marked out on the certain range at Langley. We would simulate motion in the target with a simple RC car. So the results from this were that that the autonomous contingency management functions on a small UAS can greatly mitigate ground risk, because now the vehicle can find a safe place for it to land in the event of an emergency. COTS cameras combined with state-of-the-art microcomputers and algorithms enables autonomous ditch site verification. So we were able to get very good verification at a ditch site with a fairly simple system. And the geolocation of the ground targets is adequate. However, improved geolocation could support smaller ditch site usage. And we were using the sensors and systems on the vehicle to support that geolocation. Through the UTM project, integration of Safe to Ditch and Icarus was tested. In this construct, the ditch site top of descent was provided by Safe to Ditch, and then Icarus provided a route to get there. And this did include some geofencing around other vehicles' airspace as one example of how to approach autonomous contingency management. Okay, next slide. Okay, UTM Raven. This test was performed as a collaborative effort with the Mid-Atlantic Aviation Partnership. It's worked out extremely well for us. The objectives of the flight test were to characterize performance of a prototype commercially available small UAS airborne radar to detect and track UASs as well as general aviation aircraft. And then the second objective was to integrate that radar output into Icarus and evaluate non-cooperative autonomous sense and avoid scenarios. So you can see the Winship BFD that was supplied by MAP, also equipped with the radar system and the rest of the research system. In the top photo, we had 2 intruder aircraft. One was a Tempest and one was a Cessna 172 that was we got from Liberty University. And then we used the MAPS Kentland Farm test site to perform the testing, and NASA provided the Icarus software and the Tempest UAS. Well, you can see in the lower image there, you can see the yellow line on the right was the BFD. The lines on the left, the green lines, were the Tempest aircraft with the actual track and the radar track. So it worked very well. It was able to track the vehicles most of the time. However, there was some background clutter issues that we think are resolvable. And this was a great test to kind of set the foundation for work in this area. Okay, next slide, please. V2V was performed in 2017, and the objective of this flight test was to develop and assess technologies critical for UTM type of UAS operation. So we were looking at DSRC as a vehicle-to-vehicle communication link. We also evaluated 4G cellular to provide command and control. Again, we were able to require as like a ride-along some more high-res position correlated video for optical sense and avoid. And we also performed the fixed-wing evaluation of Safeguard, which is the autonomous range containment system. See some pictures of some of the different technologies there, the BotLink and the Safeguard box. The lower image shows how we performed the testing. So we had race tracks where the vehicles would be set up to be like a head-on approach course. They would turn out at the boundary and just do continuous loops to evaluate these technologies. DSRC, as Marcus was pointing out, effective range is limited. Partly due to the high frequency and also partly due to the low power that we're able to use. 4G Cellcom is effective with some short duration dropouts, and the dropouts that we would see typically were at lower altitude, and we tested this in a very rural environment where cell is not particularly available, and we'd like to extend those results to a more suburban environment going forward. Again, the Sony action cams were effective for optical detect and avoid, and Safeguard worked very well for the fixed wing application. Okay, go to the next slide, please. Okay, Pathfinder. Okay, this test was performed in 2019 and represented in many ways the culmination of a lot of efforts in the UTM project. The objectives of Pathfinder were to integrate Icarus and Safe to Ditch and then assess those effects on the UTM system. So we wanted to evaluate how the ground control station operator, situational awareness and workload and reactions or affected by the different types of autonomous sense and avoid that were available for this test. We wanted to look at the effect of airspace constrained contingency management. This is Icarus routing and rerouting, potentially around a geofence of the other vehicle was one of the test conditions. And then we want to do this with high density operations. So we were using simulated aircraft to boost that density. Another objective was to evaluate flight alarm. So flight alarm is like an ADS-B system that's designed to operate in open ISM band. I understand it's not a regulated band, but it is able to work fairly well for the application that we tested. Another objective of Pathfinder was to look at long-range cross-center operations and to acquire more 4G characteristic data in a suburban environment. So you can see on the top right there is a couple of flight paths. I know the lines are a little thin. I apologize for that. But the flight plan on the upper left was the intruder aircraft. The flight plan on the lower right was OwnChip. At a certain time, the intruder aircraft would enter a simulated emergency situation that would require it to cut across the airspace of OwnChip. And the curved color line is Icarus's response to this emergency situation. What makes this particularly significant was that the intruder flight path was not a continuously translating flight path. The vehicle flew to the top of descent, did an abrupt stop, and then transitioned into a slow descent. So it was a three-dimensional time-varying trajectory for Icarus to maneuver around. And it was able to do that very well using flight alarm as the vehicle-to-vehicle communication link. Another part of Pathfinder was the human factors testing. So we set up in our air traffic operations lab a test subject test area where we brought in people to serve the role of UTM operators, and we presented them with the data from the flight line. And asked them to monitor the traffic and to provide separation. One result from that was that human separation of UAS traffic was considered to be a monotonous task as we tested it. So that could pose some concerns for future efforts that could rely on humans to become engaged in a task when it was previously somewhat monotonous to follow. And human factors results indicate the vehicle intent is highly desirable, if not required. So the test subjects indicated they really wanted to know where the vehicle was trying to go to maneuver around the other vehicle. So that type of intent information that Joey was talking about earlier, something that needs to be carried forward. Okay, next slide. Okay, summary slide. There are many challenges exist towards ubiquitous small U.S. operations, has been touched on today, both for on ground in terms of the traffic management aspects, as well as airborne aspects. What's happening on the vehicle. I strongly believe the UTM project achieved progress in both areas through the course of the project. And just my statement here, fully operational small UAS transportation system, I think is considered required before we can see a human carrying system, but maybe that's just more prognostication on my part. Lessons learned, separate technology development and testing is effective. So a lot of the testing we did at Langley, we were looking at individual technologies and developing them. Integration and testing of those technologies is more of a challenge as we experienced in Pathfinder. However, the integrated testing has extremely high value to look at the overall system and test. Some next steps that are underway. One is the Stereo project that is applying UTM technologies for disaster response facilitation. So that's currently a project that's underway, and that's wrapping up this year. Another follow-on project is the AAM High Density Vertiplex project that I'm working on with Marcus Johnson, where we're looking at prototyping a UAM system development and then testing that system using small UASs. We'll be leveraging technologies from several projects such as UTM, System-Wide Safety, ATMX, and TCube. we're looking to enable effective management of off-nominal scenarios in a vertiport environment, and then that coordination of dynamic reroutes throughout the UAM system is one of the technical challenges that we're looking at in HDB. We're looking to provide operational credit for NASA or other technologies and support Part 135 beyond visual line of sight advancement. You see a few images on the right. We have a image there of the NASA Langley Research Center campus with some vertiports placed there. We'll be doing our prototype testing. We'll be developing a UAS operations center at NASA Langley in our air traffic operations lab. And then we have plans for some potential work with folks at Fort Monroe. They're standing up a UAS test site down there, potentially enabling long-range flights from NASA Langley around and then down to the south to Fort Monroe. It's indicated by that yellow line there. Okay, next slide, please. Okay, this is a list of personnel. As I mentioned at the opening, a very, very dedicated, very enthusiastic team. I believe I caught everybody who contributed that. So nearly 40 people on the Langley team, and just a shout out to them for all the work that was accomplished. Next slide. Okay, we have a list of additional reports that have not shown up in the UTM database yet. They're provided here. They cover a range of flight tests that have been performed in the last couple of years. So recommend folks who are interested to look at these reports. And there are several others there too that we saw were not on that UTM server that we have listed in this presentation. So that's all I have right now. So I see we're a few minutes early, but I don't think there's any problem with that. And thank you for your time.
Thank you, Lou. That was great to really hear about the amount of the flights, 1,700. I had no idea that took place. And just amazing achievement that was performed. Now we'll switch gear a little bit, and Lynn Martin is going to talk about studying human system integration within the UTM system, which was the work performed by the Airspace Operations Lab Human Factors team. Lynn, please go ahead.
Tim. Hi, Lynn. We're having trouble hearing you. It looks like you're still on mute. We can definitely hear something. It's a little garbled.
Can you hear me now?
That's better.
The sent out by Jeff this morning.
Lynn, you are starting to break up again.
Okay.
And I'm going to drop the call number into the chat box for you to call in via phone, and that may be able to help. We can use that for audio.
I can't get on the chat because I'm not on VPN like you advised. Because so to put something in the chat isn't going to help me.
Okay, we're able to hear you much better now. Can you try speaking one more time?
Hello?
Okay, that is better.
Hello?
We're hearing you clearly now, Lynn. No, okay, Lynn, we just lost you again. Jeff Homela, are you online perchance?
Hey, Anna, yes, I am online. Should I fill in?
Yes, would you be willing to jump in?
All right, I take my best shot at it. Hopefully I can do it justice. Let me turn my camera on. And yeah, Lynn, yep, sorry if you get back on, then please feel free to chime in or text me if I'm going off script somewhere. So yes, I'll present this on behalf of Lynn. Lynn was really kind of the ringleader of a lot of the human factors work that we did coming out of the lab. So a pretty big team, and I kind of touched on it a little bit earlier in the concept discussion and the Q&A session about pilot displays and just general interactions. And so a lot of that work was performed here throughout the different TCLs. And we'll kind of go over the risk association that was encompassed as part of the TCLs, and some of the human systems integration considerations, the different parameters of the demonstrations, and look at the human factors data collection and the processes and what was collected throughout the project, and kind of summarize our flight test demonstration involvement, and then some of the general findings regarding information quantity, information usefulness, or using it, increased complexity and standardization, and really looking at UTM as a human automation system. So if we go to the next slide, please. Okay, so we've kind of touched on this a little bit in different presentations so far, but as part of the UTM project, we defined different technical capability levels that really increased in the levels of complexity, but also the risks of the increased levels of risk as we transited from TCL1 into 4. So each of those environments kind of increased in the level of capabilities, complexity, and inherent with all of that is increased risk as well. So going from TCL1, where you might be in more rural types of operating environments where, if you're looking at safety, maybe the biggest concern is dropping into a cornfield. And then TCL4 is when you're downtown in an urban environment where there's definitely much more risk involved in those types of operations. And so this was sort of like the going in point for being able to frame our approach to looking at the human factors considerations for UTM. And if we go to the next slide. This is we started from TCL1 and really starting to look at the types of questions that we could start posing, starting in TCL1 with the more simplified types of operations, and really building upon those questions and our approaches to be able to observe the humans that were interacting with the system as it was developing and evolving, and then adapting those types of questions as we moved throughout the TCLs, such that by the time we got into TCL4, we had very detailed questions, and we were able to start applying those to the types of operating paradigms that we were incorporating into the tests at that point, where there were more complex interfaces, a lot more functions, different crew members that had different kind of operating procedures and interfaces themselves, coming from different companies and being connected to different USSs and other services, and all of them trying to do kind of the strategic deconfliction and doing the pre-flight planning using some of the services in this more urban, higher complexity type of environment. So we were trying to adapt as we were going through the different TCLs. And if we go to the next slide. Okay, and so this is kind of an overview of the flight demonstration details. Arwa kind of touched on some of these in her demonstration, her presentation. But as we got through the different TCL demonstrations, there were a total of 5 that we were kind of embedded in as a human factors crews. TCL2 had 2 instances where we were out in the field. One was for the national campaign that was kicked off at the multiple test sites, and then the more formal TCL2 testing that was done at Reno Stead up in the high desert there. So you can see kind of the dates that were involved, and you can see as we moved from TCL1 up to TCL4, you know, the number of flying organizations and vehicles were increasing. Number of days kind of increased, except for TCL4, where we were much more targeted in the locations and the testing, as opposed to being at the other FA test sites. But you can see it basically as we kind of moved through the testing, all the different organizations were kind of moving along with us and kind of expanding as we were expanding our test scopes as well. And so the human factors team were very closely involved in each of these tests, going out to the different sites and working very closely with all the different operators that were out there, as well as in the lab, kind of observing things from kind of an information perspective, information gathering and viewing perspective. So if we go to the next slide. Yeah, so you can see these were sort of like the focus areas for the teams in terms of how they were embedding with and interfacing with the different stakeholders and actors within our flight demonstrations. And if we go to the next slide. Okay, so you can see here, this is sort of like an overview of the data that was collected throughout the UTM project. And we had a lot of initial kind of observational periods. So during that testing, we had our researchers kind of with those crews, like I mentioned before, kind of observing the runs as they were being carried out from the kind of planning pre-flight stages, as well as into the actual flights themselves and carrying out the operations from beginning to end. And then afterwards being able to conduct debriefs and have the participants fill out surveys, kind of qualitative reports on different aspects of the run and the UTM systems and interactions with it, kind of through those surveys and questionnaires. And then generally having kind of larger debriefs afterwards in the day, where we get multiple people in the room and really go through a number of targeted questions that we had developed as part of our human factors focus. And so you can see here just sort of like the overview of how that data was collected, and we really ramped up starting from TCL2, getting into TCL3 in particular, where you know, we had a lot of tests across all the different test sites, and so a lot of that data sort of ballooned in TCL3, and it's really stayed strong as well. If you kind of consider that basically all of that was collapsed into 2 test sites for TCL4, but we still got quite a lot of survey responses and opportunities for debriefs with a number of the folks, and a lot of hours of debrief. So by TCL4, it was 9 hours, and a lot of transcribing and reviewing and collecting and collating that, relating it to the other data that we were seeing from the questionnaires and other debriefs, and the number of flight sessions observed. So all of the observations during those flight sessions made their way into kind of the larger body of data that was collected in support of the human factors work. Go next slide. Okay, so overall for the flight test demonstrations from a human factors perspective, we were able to really successfully demonstrate that UTM's a viable method or approach for communication and coordination between small U.S. operations from kind of multiple perspectives, from service providers to the actual vehicle operators and other stakeholders as well. We're able to demonstrate that the data exchange as part of the UTM system and the architecture that we had developed, and as it evolved, was able to bring that information, provide that information to each of the parties to provide that level of situation awareness that's needed to be able to operate within this sort of UTM paradigm that we pioneered here. And as we moved through the TCLs, especially into 3 and into 4, We were really focusing on capabilities that allowed for contingency management, contingency maneuvers, and the alerting that kind of went with those types of situations, and being able to share that alerting via message exchanges, data exchanges to the affected parties, and being able to really look at the information that's needed for real-time decision making. So how do we get that message and data exchanges to the right people in a timely manner, and in a way that allows them to make the right decisions in a timely manner. And then especially as we ramped up into the TCLs, the operations became much more complex. So multiple vehicles at a time, altitude stratified operations that were all strategically deconflicted through the USSs. And it really gave us a good window into the types of procedures that the crews need to have in place for that type of planning to be able to operate in that type of environment. And it also kind of raised some of the interesting issues about kind of like we mentioned before, altitude referencing and obstacles and structures that are in the airspace as well. But at least as part of the testing, we were able to kind of work through these different aspects throughout the tests, and kind of observe how that looks within kind of the UTM construct. So we go ahead, one more slide. Okay, so now we're kind of looking at some of the information findings with respect to how humans are going to be interacting within this system. And so looking at the situation awareness responses, so for the operators that were flying the vehicles, trying to assess, given the information that was available, what was the situation awareness and kind of what was missing. So in some of the earlier tests, you could kind of see this chart on the right here as this situation awareness ratings. And in test 2, back in TCL2, we could see that the situation awareness ratings were fairly low, or at least lower compared to how we started building that out through the TCLs. And so earlier on, you could see that details were missing in the UTM information, and it made it a little bit more difficult for crews to establish the necessary situation awareness. And so it was really clear early on that, this type of information and that level of situation awareness and complex or common operating picture is really needed to be able to operate in a scalable system. And so as the concept and the services and technologies kind of improved as we moved through the different TCLs, we could see that the interfaces for the operators with their service providers matured, and a lot more information was provided to each of the operators for kind of this broader type of situation awareness that's really needed to be able to meet the type of operating approaches that we're considering for the later stages and evolutions of UTM as it gets closer to implementation. Next slide, please. Okay, so looking at the efficiency of USS interaction, and this is sort of a comparison of the efficiency in responses. And so in the earlier tests, this is just comparing test 3 and 5. That's I think TCL 2 versus 4. We found that less information and more external planning made crew decision making more straightforward, which might be counterintuitive to some, but it's really having a more simplified problem and decision making process makes it a little bit smoother. But as more information was needed and the types of operations and encounters between operations were getting more complex, it was clear that more detailed information was needed. So it was available as the systems matured and started including much more information that was available to the operators. It was needed much more quickly as we got into these types of operating situations where you had higher levels of density and you were in more kind of constrained environments with structures nearby and airspace structures as well, looking at UVRs in the airspace as well. So it just sort of follows that the more complex the environment comes, the more information is needed, but that information needs to be presented in such a way that those that are responding need to be able to act to that quickly. So how do you provide that type of information, and in what way to kind of streamline the response? Okay, next slide, please. Okay, so facing complexity. So we're looking at kind of the amount of information that was displayed to the operators and how they were displayed. And so, like I mentioned earlier, we didn't prescribe, especially within the testing, how information needed to be displayed or presented, or when. It was really more performance based. And so, as long as the operators could react to the proper messages and data exchanges, that was where our kind of more objective measures were focused on. But on the human factors side, we were much more interested in, looking at how the different operators and crews were interacting with their service providers and the ground control station to really get an understanding of what are the different approaches to it, and then in the future be able to provide guidelines based on those observations. But as we saw in the earlier slides, as the testing complexity increased, the amount of information available also increased, and the amount of information that was needed increased. But as we saw with some of the flight crews, the amount of information started to clutter some of the displays. And so, having information that's available is great, but if you throw it all in front of an operator, or just throw it all on the screen, it is not super helpful if your screen is being cluttered. So that was kind of a fairly obvious finding, but it's one that that you'll find as kind of engineering processes progress. Sometimes these types of human factors considerations aren't included in the development. So these are the types of things that have to be considered as we move forward to either some level of standardization or guidelines that are needed to be able to address sort of how information is presented in a more streamlined way that operators can really find more usable and more timely for them. Okay, so yeah, so like I kind of said, more complex environments required more information to be presented. Too many messages it was kind of another one of the findings. So that kind of, there's display clutter, and there's also kind of information clutter as well. So looking to kind of streamline what is the right amount, what's the right balance for crews to be receiving messages that need to be acted on. What are different ways to present it in terms of, like, this is just for awareness and notification, and this is the message that needs to be acted upon. And then some of the message labels that we had instantiated as part of the messages that were flowing through the UTM system. Some of them were not very informative for the crew, so that kind of adds to the clutter as well, because the crews sometimes don't know which messages, like I just mentioned, need to be actionable and what others are just for notification, and some, if the labels really aren't very targeted for that type of message, they're not going to be very helpful, and that could lead to operators starting to ignore messages, which is not a good thing either. So again, you want to strike that balance in terms of information display, accessibility, and actionability. All right, next slide. Okay, so this is kind of like looking at standardization for the procedures, the different types of units being used, and the terminology as well. So there was a lot of times where some partners or flight crews were not familiar with some of the information that was being exchanged, and this was part of a, I guess, education process for those that were inexperienced from before coming in and not really being able to latch on to some of the common terminologies that were being used as part of the messaging, and that were on their displays as a result as well. Measurement consistency. So we kind of still were finding, even in TCL4, that there were different units of measure kind of across the board sometimes, even though we had established data formats that kind of specified some of these units. They were still popping up in the wrong units, and it was hard to catch sometimes. So this is like another vote for kind of requiring some level of, or a forcing function for kind of common standard of units to be used. But it's a tricky topic, especially in terms of altitude referencing, which kind of Marcus was talking about a little bit earlier, and it continued to kind of show up in multiple testing areas as a challenge. And so I think that's a broader challenge for industry as a whole to start targeting and addressing these types of issues, which seem pretty obvious, but they're not necessarily super simple from a technical perspective. And the last one here is the undefined procedures, which were a little bit difficult for crews to kind of deal with, as far as kind of the interaction of the crew with their interface and the UTM system as a whole. And so there weren't really defined standards or procedures for how that interaction looks, and that was, I wouldn't say it's by design, but we sort of, like I mentioned in a previous presentation, we didn't do early prescription on any of it. We wanted to learn a little bit more of how different industry players were approaching that interface, and then from there be able to provide some sort of information or input to some more definition on these types of procedures. And then given the current state of the interaction, or the displays and the interfaces that the crews had, and combined with the type of messaging and the clutter that we were mentioning from before, it ultimately, especially in TCL4, when we were looking at kind of situations that had shorter time horizons for action, a lot of the users are finding that they had too little time to make complex contingency decisions based off of what they were receiving on the display and through the system. All right, next slide, please. An automation system. So while the end state of the systems is, we're kind of envisioning it to be, I guess at some level, kind of fully automated. The interim near-term states will require some level of interaction. So there's going to be humans involved somewhere. Even in a fully automated state, you're still going to have stakeholders that are human and kind of in the loop somewhere, at least monitoring, if not stepping in at some level in certain situations. But that's part of a progression. So we're going to start from not fully automated paradigm and then kind of build our way up to it. And so challenges for the nearer term usage is that we need to design displays that are easily usable in these kind of complex high density types of environments, even though we probably won't start out that way as we move into the implementation of UTM. Kind of need to be able to account for how, from a design and interaction perspective, how that can scale and how that approach is designed to be able to be scalable, so that we start from a kind of more or less complex environment, but it's we're set up to be able to scale to the types of environments that we envision for the future. So looking at the messaging and the ability to filter by criticality and presenting operators with the right level of information that's needed. Having UTM training for users. I know there's some UAS pilot training, but this is really more kind of focused on UTM as an operating approach, and having some sort of level of standardization that's disseminated through these types of trainings. I think is going to really help in sort of the standardization and formalization of the procedures that we may want to get to at some point in the future. And challenges as we progress from kind of near term to the midterm usage is more automation and autonomy gets incorporated into the types of operations that would be in the midterm, having functions automated in a way that keeps the manual tasks as kind of coherent activities for the humans. Really having a very well-defined allocation of functions between the human that's still involved, as well as the automation and autonomy that is going to be on board the vehicle, as well as through some of the services that would be available as well. Next slide, please. All right, summary and future work. So successful demonstration of UTM as a viable coordination method between operations. We were able to kind of see that through the TCL demonstrations, but we also saw that the information was key for building up the awareness that was needed and to be able to coordinate the operating functions. And future work is going to spotlight the human automation system interactions, as well as the display requirements that are needed for the operators as we get closer to implementation and some of the future areas that we think UTM will evolve into. And I think that's it.
Great. Lynn, I'm sorry for the network trouble, and Jeff, really appreciate it for a seamless handoff. With that, we're entering a break session, and then the home stretch. We have a lot of interesting talk to come our way, including the global impact of UTM panel. So I hope to see you all after 1:25 p.m. at 1:25 p.m. on Pacific time and 4:25 p.m. on Eastern time. See you then. All right, welcome back, everyone. To start the home stretch, we have Minju, who led UTM fast time simulations effort, and we have him to talk to us about the effort that has been taking place past several years. So Min, please go ahead.
Thank you, Joe. Thank you, everyone, for listening to this talk. So I was a UTM task lead for the fast time simulation. The focus of this task is really on the UTM traffic management modeling and simulation. So the focus is really, it's like not for several aircraft, it's actually for tens or hundreds or even thousands of aircraft. Next slide, please. So as we have heard from previous talks, we have layered kind of a conflict management models from strategic conflict detection, conflict management to tactical conflict management, including separation provision and collision avoidance. Although we have done a lot of work by laying out the foundation and the testing, build and testing, but we have to say there's a lot of work for us to do in order to enable high density operations such as drone package deliveries. So in current strategic deconfliction, we hope that, whenever there's a conflict or intent conflict, we hope we can resolve that through negotiation. If they have to proceed with that kind of conflict, which might happen in the future for package deliveries, because they share the paths might cross each other. So in both NASA and FAA document, they say you can proceed, but you may be required to have some DA technologies. But there's no, it's not clear about the requirements regarding in terms of safety and efficiency. Next slide, please. So there's a need to evaluate, what if given a conflict management models, how do we assess the safety and efficiency? So we know these layers often interplay with each other. So strategic deconfliction can take some stress away from tactical separation, and the different performance of separation, different performance of a tactical separation can also, affect the strategic deconfliction. So anyway, so we need some kind of a Monte Carlo simulation capability such that we can assess, airborne risk, study the airspace capacity, and also develop a subsystem requirements. And eventually we can give us a kind of a better idea what the performance look like for conflict management models. Next slide, please. So in this talk, we're going to go through, first of all, some, the simulation hierarchy in our mind, and then we talk about the models we developed to build up such kind of platform, and we will talk about some, some past studies using this simulator, and finally we'll conclude some summary. Next slide, please. As we said, the focus here is really air traffic systems. It's not a vehicle-centric kind of simulator. So there are many ways to describe simulations for air traffic systems. Here I just plotted 2 dimensions. One is model fidelity. Oh, sorry, can I go back? So the other side, the other axis is a competition performance. We know we like to flight tests. They provide the highest fidelity. But the things like they're prohibitive in terms of cost and time. So we can only run limited scenarios. Same thing for live virtual, hardware in the loop, human in the loop. On the other end of the spectrum, people develop a lot of simple simulators just to focus on one thing, like a lot of MATLAB code developed by students, by researchers, but the lack of fidelity. So the purpose of really want to push the envelope, make sure we have enough fidelity, but still maintain a very high competition performance, so we can do millions of kind of runs, do all kinds of uncertainty studies. So next slide, please. So the idea is really, by doing Monte Carlo simulations with certain, good enough fidelity, we can down select, we can run millions of scenarios with uncertainty included, and then we can down select scenarios, given only limited scenarios. Go back to the next slide. Maybe there is timing over there. So yeah, so then we can down select scenarios and then feed it to the live virtual simulations to do a more thorough high fidelity simulations. Next slide, please. So based on that motivation, we start to develop this simulator called FE-Cube simulator. It's actually, the full name is a flexible engine for fast time evaluation of flight environments. So the key features are really just, first of all, we want to maintain a mid to high fidelity to capture the key characteristics in a traffic management system, such as a 6-off trajectory model. If you know traffic management simulation, in conventional ATC, we use a BARDA type kind of model, but we found that might not be accurate enough given the environment, these drones or UAM flying, because we are not talking nautical miles accuracy, we're talking about a meter or feet level kind of accuracy. We want to capture the perturbation caused by the wind, etc. So the 6-off model, that's what we end up use. And also we want to capture, want to include the communication, navigation, surveillance, because there are a lot of uncertainties over there. So if you want to mimic the reality, you have to include that kind of uncertainty. And the most important, we want to have a core airspace management function, such as conflict management. We talk about strategic, all these layers of conflict management, we want to include it. So, and we want to do uncertainty study, of course, because nothing is perfect. We have to make sure, when you develop an algorithm, you run through scenarios, you find out some kind of assumption was hidden. You may not even notice that. Overall, we want to run Monte Carlo simulation, so we can get a stochastic kind of analysis. So to achieve that kind of so fidelity and efficiency. To achieve that, of course, we're going to leverage the cutting-edge hardware such as GPU, but that's not far from enough. We have to think about the modeling from the modeling side. So next slide, please. So one typical example is a conflict management model. So we all know first of all, we know there are layers, right? Strategic deconflict before departure, dynamic rerouting, detect avoid, collision avoidance. That's for different phases. And also, there are also a lot of software package has been developed by all these, conflict management developers. But every time, if you want, it's not easy to, have a platform to evaluate all of them, because they all developing different packages, has different performance. So actually, if you look into this kind of these kind of models, you find out they share a lot of a common structure. First of all, the data flow, the input typically are position, speed, intent, flight plan, etc. And the actions are typically heading change, speed change, altitude change, or some combination of those kind of actions. And even you look at the decision making, the middle part, they share really common structure, a lot of common structure. It typically has a decision logics to decide when, who, do what. So they have a very common trajectory prediction algorithm. So they have a lot of set of rules. The rules can be, at what condition you do what, so that kind of thing. The rule can be, majority of them are rule based. So like a decision tree based kind of conflict management algorithms. And even for collision avoidance, something like some algorithm like ACAS-X, XU, they are table based kind of decision making. So you can also incorporate that. In recent years, so there are a lot of there's a trend to develop a neural network or AI-based kind of conflict management model. You can just put a neural network in for the decision making. So by generalizing this conflict management model, you can literally just say, okay, can we take the JSON rule-based input instead of taking a software package? So then you don't need to worry about the efficiency of the code part. So that's kind of the reason why we want to have this kind of generalized conflict management model, which we can increase the computation efficiency while we're not losing the fidelity of the algorithm itself. So next slide, please. So this one I just show one part of that is a strategic deconfliction. So we know we set up we can set up priorities, who goes first, etc. That's a little simple one. Typically in UTM, we're using that for pre-departure. Next slide, please. So next one, sorry, go back. So yeah, thank you. So yeah, next one is to just show how this kind of text JSON input can handle very sophisticated kind of rules. So typically you can have rules like say, okay, if you meet this condition, you take this action, meet this condition, take that action. Etc. We can just translate to a JSON format as a sample format at the bottom. So if you meet this action, meet this condition, for the next half second, you're going to do heading change, etc. That kind of action. So by using this one, can go to the next slide. So we can deal with a very sophisticated kind of models. Here are just two examples. I just need to change the JSON text input by changing the rules. Then we can evaluate the algorithm. So the first one is multi and we go crossing each other. I just change the rules. I don't touch the code. I just do the change the input. It's similar for the next one. So next slide, please. So, and now we're talking about the model for communication, navigation, surveillance. Next slide, please. So, speaking of a communication model, there are many ways to do that. So we can talk, folks already talk about V2V communication, or you can send, send the information through the ground. There are many options. Here, instead of using hardware or software in the loop kind of simulation, we try to abstract those models. So we just literally just, based on their reception probability, latency, etc., just have those kind of simple characteristics, and then we can generate a kind of distribution based on that. So one example is using DSRC. It's actually the reception probability is a function of distance and a function of density. So of course, if you know DSRC, the default distance is actually 300 meters. Here I just kind of extend to 1,000 meters, 1,000 meters, just in case you're curious why the range is so large. So anyway, so yeah, it follows certain distribution, and then we can generalize input without really worry about what's behind this kind of communication mechanism. So next slide, please. Same thing for the sensor model. You can click to the end, one more click to the end of this. So yeah, so for radar, whatever you're using, you can use radar, LiDAR, etc. But there are common features for those kind of sensors. So here's an example for the radar, right? So you have detection range, azimuth range, elevation angle, etc. And then you have, we can assume they follow Gaussian or certain distribution. And then you just put it into the input template. So then you can play around with that. So next slide, please. Yeah, so, and the next component is the weather. Sorry about that, Raj. So yeah, so weather is a big uncertainty source, right? So can you go to the next slide, please? Yeah, you can do that. And so yeah, we can either take weather wind measurement, which might be a little bit sparse, and or sometimes if you want to using some certain wind modeling to fill the gap, but that's fine. So all this can be fed into our 4-dimensional grid-based kind of a wind structure. So you can see it's X, Y, Z, and time. We have these 4-dimensional grids. For each grid, we have 3 components: U, V, W for 3 direct the wind vector. We're assuming they follow certain statistical distribution. So by taking that, we can actually take in account a very sophisticated wind model. Can you go to the next slide, please? So this is a wind model generated by our CFD team at AIMS. So this is a horizontal resolution is 10 by 10 meters, and the vertical resolution is every 10 meters you have 1 layer for wind display. We use particle wind to display that. So altitude range from 0 to 200. The reason I show it here is using that 4-dimensional grids. You can have very sophisticated wind field like this. So next slide, please. Yeah. So the last step is putting everything together after we model this. We try to generalize models. Sometimes we want to abstract the model, but try to keep the key features for this traffic management system. So next slide, please. So we use cloud-based GPU instances to speed up the process. So GPU, that's a typical way to because they're fast and we can parallelize all the computation, etc. So while cloud-based just allow us, we can do auto scaling to use, and we can call as many as GPU instances if it's needed. And we have this web portal interface, so make things easier. You don't need to carry the software around. So next slide, please. So this one just show you, how do we auto scale. It's not necessarily used every time, but that's kind of a thing. We do this kind of calculation. Next slide, please. So here is a roughly performance check. So we do in terms of real-time factor, which is how much time faster in terms of actual flight time. So we are actually looking at it anywhere from 1000x to 10,000x, etc. Of course, if you know the simulator, there are a lot of factors affect the performance, such as how smooth the trajectory is, the interaction between flights, conflict resolution algorithm, etc. Next slide, please. So now we just go through some studies we did using FUCube. Next slide, please. Yeah, can click through the slide. So the first thing is about the complexity, right? So one more click. And so in ATM, ATC, maybe one more. We have asked ATC air traffic controller to handle that. So they give them certain scenarios. They're gonna write down the workload, and then we measure what kind of metric is actually has the highest correlation to that. For UTM, we're not expecting ATC in the loop, ATC controller in the loop, but how do we measure the complexity? Many times we're using density, but density might not be the best measurement. So we use measurement from the simulation, such as a resolution maneuver. Use that as a ground truth, and then we try to identify some simple metrics that can measure the complexity. As a first paper, we used the weighted number of conflict. We found that the correlation to the ground truth is actually 0.9. Compared to give it as a comparison, the density is air traffic density is only 0.7. So that's quite an improvement. And later on, we also developed another metric called impedance. We have even higher kind of correlation. So recently, another project in NASA, they are using similar kind of a mechanism to study UM. Next slide, please. Yeah, thank you. So yeah, the other one, sample studies, define CNS requirement. So let's say here, just showing an example for some preliminary kind of studies. Say intruder, we have intruder position error. So the left side shows the safety. I want a safety, want to have 0% of chance of loss of separation. Then you can see when you have high errors, your aircraft count is less, should be less. If you have a less error, then you can have more aircraft flying the same area. Same thing for efficiency. If you have a large error, then your efficiency gonna be. So if you want to maintain the 5% of extra distance, you have to have a better kind of position, less position error. Otherwise, you might end up to have less efficient. So next slide, please. So we can click through. So yeah, this is a recent study did for work using the simulator. So you can animate that. Sorry. And so the literally is like two streams of flights fly cross each other, departing from their vertiport. Of course, they're going to cross at a certain point. So here, just do some interactions between. Okay, thank you. So there are certain you can interact between these two scheduling and the conflict resolution to achieve the best performance. We did some study on that. That's actually pretty interesting. So if you're interested, you can look into that. So next slide, please. So yeah, as a summary, so we did spend an effort try to from modeling and implementation point of view perspective, implement incorporate core traffic management functions while ensuring efficiency in computation time. Mainly, we try to do some uncertainty studies, such that we can assess the airspace airborne risk, etc., and evaluate conflict management models. So the studies using FEQ helped us mature new concepts through statistical evaluations. Next slide, please. So because of the using the simulation, we can potentially generate a large amount of data. So actually, we're thinking about it. That can be used for future AI ML related work to help to train some kind of a neural network based kind of conflict management tools. And using that, we can also explore approaches for certifying autonomous algorithms. So I'll end the next slide, which is next slide, please. So this is about software usage. I know some folks may raise a question, how can we use that? We have this patent application filed. And so if you're interested, you can talk to us and NASA Technology Transfer Office for potential software usage. Thank you. Thank you, Praveen.
Oh, all right, man. You just had on time. Thank you, Min, for providing us with a thorough review of the really novel GPU-based feature that you developed, which is not only used by UTM, but UAM, and also upper class E traffic management to come. With that, we'll move to Praveen Raju, who is from the FAA, to talk to us about UTM pilot program phase number 2. Praveen, please go ahead.
Hi, good afternoon, everybody. Happy to be with you all here today. So we'll talk a little bit about the UTM pilot program, or the UPP phase 2 activities here today, and how we've collaborated with industry and NASA to move UTM forward within the FAA. Next slide, please. So just a quick overview. We're developing new ways to safely and efficiently integrate a small UAS into the national airspace, or the NAS, while promoting a scalable, cost-effective way for these things to happen. The UTM system for us is a manner in which the FAA will support small UAS and other UAS potentially in the future in a low altitude airspace, and we will leverage and utilize industry's ability to supply various services in order to support the FAA's overarching UTM ecosystem. UTM is a community-based and cooperative traffic management system where the operators and USSs provide services and work together in order to meet regulatory requirements set forth by the FAA. For us, the UTM pilot program was a way that we could partner with industry to test and evaluate various technologies, validate and address some standards and various procedures. And that gives us information to develop systems internally, as well as provide feedback to the different standards bodies that are looking to address the challenges within UTM. Next slide, please. So this is a general overview of the UTM ecosystem as it plays a role today. On the left, you can see some of the FAA and potentially industry capabilities in terms of qualified services that a third party within the industry could provide on behalf of the FAA once qualified. Things like the UAS registration, airspace authorizations, potentially in the future, somewhere along the lines of remote ID correlation services play an important role on the back end of the FAA. We have various authoritative data sources in terms of different registration and waiver information that are held within the FAA cloud services and databases, as well as our Flight Information Management System, or FIMS, as many of you are aware of. And on the right, there are the commercial UAS service suppliers, both sort of overview of traditional USS and supplementary service data service providers, or SDSPs, as we call them, which can provide services like flight planning, strategic deconfliction services, weather, and potentially in the future, qualified USS can provide things like UAS volume reservations. And we also have the operators working hand in hand with the USS to adhere to different requirements. Next slide, please. So why UPP? This is generally outlining the need for areas like the UTM pilot program, and why we have gone out and done some of these capabilities. To date, the FAA has enabled more routine commercial and recreation operations in terms of visual line of sight. However, we fully understand that the future is looking to beyond visual line of sight operations, or BIVLOS operations, and we wanted to explore different use cases and capabilities that will be required to enable the expanding need for BIVLOS operations. In today's environment, BIVLOS and UTM operations, UAS operations are really done at a case-by-case COA or waiver level. So they are evaluated on sort of a one-off basis, and we move into more, as we move into more nominal environments, we want to use and explore technologies that will make BIVLOS more routine and not and lessen the burden on the one-off sort of environment. We understand there's stakeholders at the doorstep of the FAA asking, what is next for UTM? Where are we going? How are a lot of these R&D capabilities that NASA has tested, how are they moving into more of an implementation type of system within the FAA? As we address and work through some of these use cases and concepts, we needed a test bed or test activity to validate some of the rules and standards that have been developed externally. So in our UPP Phase 2 efforts, we focused a lot on the ASTM standards that have been taking place from USS to USS standard, as well as some of the remote ID standards that were in work as we began this activity. In addition, the remote ID rule has currently been published, and it was sort of an enabler to the beyond visual line of sight rule. So using activities like this to explore different capabilities, including remote ID, and how that may fit into the beyond visual line of sight environment played a pretty key role for our use cases that were tested as part of this activity. And we used the information gathered as part of this activity and a few others in order to inform decision making on how we move forward with UTM implementation in the future. Next slide, please. So where did we derive some of these objectives and requirements? UPP Phase 2 objectives and requirements really stemmed out of the FAA 2018 reauthorization. It directed us to work closely with our colleagues at NASA and industry to test prototypes that were designed for increasing density of operations. So increasing operations or high dense operations in a particular area. In order to satisfy that requirement, we actually heavily work closely with our colleagues here at NASA to define what high density meant. And we'll get into some of those details a little bit later in the briefing. We were also told we needed to test the UTM system at selected test sites and ranges over test sites. And this go around, we needed to include folks from the integration pilot program to be able to work with those. And our partners from the test sites proposed a team of USS, industry manufacturers, industry technology providers, and participants within the IPP as a team package in order to pull in order to test these various capabilities. So in the end, we selected 2 test sites. That was the test site in Virginia, as well as the New York UAS test site. And lastly, one of the major components that the reauthorization added that we needed to test were RID technologies. We heavily relied on some of the activities that were being done in ASTM and some of the recommendations that came out of the Aviation Rulemaking Committee. Next slide, please. So UPP Phase 2 awardees, as I mentioned just before, we worked with the New York UAS test site as well as the Virginia Tech Mid-Atlantic Aviation Partnership. And throughout this entire process, we were in close contact with our colleagues here at NASA in order to take lessons learned and make sure we had information sharing as we address the new technologies that have come into play. Next slide, please. A little bit about our partners. So as I mentioned earlier, both test sites brought to us a diverse group of partners to execute the UPP Phase 2 activities. Between New York and Virginia, we had several USS, including AirMap, Arrows, AX Enterprise, Wing, One Sky, and ONRA. As for the technology providers, you can see many different folks within the UAS and industry participated with us at different levels, as well as there were several operators, including a pretty major shift in that we had operators from public safety entities, so local police departments and sheriffs actually participated as both operators and those that gave us feedback on some of the services that were being tested. Initially in our Phase 1 activities, the operators were many of them were from industry and commercial perspective. This time we had an added layer of public safety entities participating with us hand in hand as we evaluated the various capabilities within Phase 2. Next slide, please. So what were the specific capabilities that we demonstrated? So over in fall 2020 and into winter, we completed the final demonstrations and received final reports from both our test site partners. And as part of that, we highlighted 5 major technological capabilities that were tested and validated. First is the access to information between the FAA and industry, and that was done through the Flight Information Management System, or FIMS prototype, that was initially tech transferred from NASA and now resides in our lab infrastructure in our Atlantic City evaluation, next-gen integrated evaluation capability. And we essentially decomposed a lot of those activities and started to derive immediate needs for FAA purposes. And we put that prototype into place to test with our industry partners. We wanted to test various standards, and one of those included RID and USS standards. So that's where artifacts for RID, both broadcast and network, were tested as part of UPV2 capabilities. Another standard as part of the USS to USS standard is the in-flight conflict management, or the deconfliction capability that was also tested. And both of these things were done, actually all of these things were done in a high-dense environment. What we ended up doing for the high-dense environment was using the guidelines from NASA, which were 0.2 square miles with around 12 UAS operations occurring in that area. And additionally, we did the UAS volume reservation capability. And this is a capability to notify operators of emergency and priority operations that are occurring within the area. And what we're using that lessons learned from that capability is to feed back into some of our policymaking groups for lessons learned and how they could develop business rules based off of some of the technological challenges that we had addressed. Lastly, a key player that added additional complexity throughout all of our use cases really was secured information exchange between the FAA, industry, and authorized users to ensure data integrity and message security. Cybersecurity plays a pretty vital role to the FAA as we move forward. And this was one of the forays into investigating different capabilities for that cybersecurity aspect of the work. Next slide, please. So, a little bit about the deconfliction and shared intent testing that we did throughout the UTM pilot program was we did a lot of automated and highly scalable activities. It used 40 operating volumes to communicate. We had supported strategic deconflictions amongst all UTM participants. And we know that it has been tested from TCL 1 to 4 and in both UPP phases 1 and 2. So it showed continuity, and we addressed challenges as we learned from the previous testing activities. And we've given a lot of feedback to the ASTM communities, and I believe it is a key part in enabling UTM in the near future, and it is one of the priorities that that group is looking to tackle. Lastly, the FAA test infrastructure supported the UTM network connectivity in order for the FAA to monitor things with US service suppliers purely for the test environment. In the future, that may not be a need from an FAA perspective. Next slide, please. The UAS volume reservation capability. So this is a technology allowing for people like the public safety partners to quickly disseminate information to UAS operators about activities occurring in an airspace. We believe it is an automated process in the future. It can be activated for short periods of time, encompassing small airspaces. It would provide warnings currently to a UAS operator about that specified volume. And we believe it can be enabled through a government qualified USS in the future. The qualification of that USS is some of the additional work that needs to be done on the back end for us. This prototype was initially instantiated as part of UPP Phase 1, and we continued the progress within UPP Phase 2 to tackle interoperability between these different capabilities. Next slide, please. The FAA UTM data correlation capability. So this is a pretty significant capability that was developed within the FAA to support some activities for authorized entities to have access to data from the FAA, dependent on the broadcast or attaining a remote identification of an aircraft. We started working on just the correlation portion of the capabilities back in the 2018-19 timeframe in terms of concept development and putting together a general architecture around it. And as part of UPP Phase 2, we actually conducted testing with external stakeholders, including USS and public safety entities, to test the feasibility of the technology. And this is a significant addition to the UTM FIM system and is now integrated within our FAA test infrastructure at the NIAC lab. In order for us to test this capability, we made a few different assumptions. The FAA has authorized public safety and security entities to do this data request for correlation services. The FAA has provided access to authorized users to submit those requests, and that these services support queries to internal FAA databases, not necessarily external ones. Next slide, please. In order to do this all in a very secure manner, one of the principles we use for this cybersecurity effort is the International Aviation Trust Framework. This was sort of the first program to leverage this capability and to achieve some of the preliminary IATF compliance. So what this allows us to do is, we know there's transformation occurring in the aviation industry, especially in terms of digital transformation. We know there's new technologies being added, and there are many new entrants that are starting to integrate within the airspace. What this allows us to do is an interoperable approach for secure information exchange with the proper authentication and identity management possible in the future, and allows us to have a certain set of data integrity, so we know the data we are exchanging is what we say is being exchanged. And this includes traditional aviation stakeholders as well as these new entrants. So this has become one of the things that we are starting to highlight in terms of cybersecurity as we move forward. Next slide, please. So as part of our program, we had distilled it down to different layers of the cybersecurity approach we wanted to do. For in-transit type of message security, we use the SSL and TLS certificates between USS, and we required that connection for all message exchanges. And then as we got into authentication, non-repudiation, data integrity, and encryption, we wanted to achieve that through the UTM certificates for each different USS that partnered with us, as well as a public key infrastructure, or the PKI, throughout our program. As part of our program, we did have the ability for many of the partners to do these secure message exchanges, but we also left it a little open for those that had production systems to be able to accept non-signed messages purely for testing purposes. And lastly, the authorization piece was achieved through the OAuth 2.0 framework. Next slide, please. And so how does all of this work play in with the larger picture over in the activities like the UPP are key in exploring these technological challenges. Now, as we gather our lessons learned and do analysis on the data that we've gathered through this activity, they're disseminated to different lines of business, and those are represented as stakeholders within the FAA here. We had participation from our flight standards, our security folks within the FAA, our information technology folks, the Air Traffic Organization, as well as the integration UAS integration office throughout the entire program. So all of the key findings and the results are being disseminated amongst different folks within the FAA, and that will be reflected in the UTM implementation plan in the future as well. So we've done our initial research, we've done some requirements refinement, we've done some level of validation here. Now it's transfer of that technology to lead us towards an implementation in the future in a very methodical approach. Next slide, please. In addition to all of this, we are actively engaged with different standards bodies. In fact, as part of the UPP Phase 2 work, we aligned several of our APIs to the ASTM standards bodies and data models. As we move forward in the future, we are actively engaged in the USS to USS standard. We are transmitting some of the outputs from the cybersecurity work in terms of a industry-led threat assessment as part of this activity back to ASTM. And I believe our colleagues at NASA are going to post that white paper on their website today. We are monitoring the different USS negotiation areas, as well as the remote ID standard development, as now the rule is in place. Next slide, please. If you are interested in learning more about the different use cases that were tested and the specifics in each of the use cases and how they were achieved at both of our test sites, we have started to showcase and put those videos out for public consumption on the FAA YouTube channel. So use case 1 and 2, both test sites are available now. Within the next week, we believe the use case 3 will be available for consumption, as well as use case 4 and 5 will be available in the very, very near future after use case 3 is published. That being said, I think I am 5 minutes ahead of schedule. I hope that's a good thing and not a bad thing. So I will turn it over to our colleagues at NASA.
Great. Praveen, thank you for providing a very comprehensive overview of UPP, not only the activity details, but where it's coming from and potentially where it is going. And it is good to hear about our work together is really bearing fruits. Now we are going to move to the afternoon Q&A session, moderated by our own Ron Johnson, who has been managing this project till his retirement last year, and we brought him back just for this occasion. Ron, please go ahead.
Great. Thanks, Jay-Woo, for the introduction. Yeah, it's it's great to come back to talk about one of my favorite subjects, UTM. So thank you, everybody in the audience that are contributing questions into the conference IO. We're selecting some to address now, and if during this Q&A you have more questions, please feel free to submit them through conference IO. So why don't we start with Arwa? Recall back, Arwa gave an overview of the TCL testing, and she has some additional information on some of the statistics from that testing and participants and such. So, Arwa, why don't you listen?
Thanks, Ron. So yeah, I just want to give you some more statistics on the flight tests that took place in the urban areas, so you could try to see the density requirements that we had. So Nevada actually had 5 UAS flying simultaneously at one point, and they flew over 150 missions in downtown Reno and the park, and over 500 simulated flights that we had in there, so we could try to create a high density environment. In Texas, they had as many as 7 live flights, along with almost 419 simulated flights flying simultaneously again, so we could try to simulate high density operations. And overall, they had about 419 flights in the 15 days that they were testing.
Okay, Arwa, thank you. That's the additional information you wanted to convey?
Yeah.
Okay, great. Okay, so next after Arwa's presentation was Corey talking about automation requirements on vehicles flying in urban environments. And this question came in about what would be the best solution to track the UAS in urban areas during takeoff and landing. It's obvious that the GNSS does not provide much help in this scenario. And yeah, we did actually see some GPS issues when we were flying in Reno in particular. So Corey, can you address this question?
Sure, absolutely. That's a great question. I think it probably is going to be site specific. Based on our research, we found that different solutions for alternative position, navigation, and timing perform differently depending on the specific conditions that you're using. Certain airborne type of systems were better in different altitudes and different lighting conditions. Different types of ground-based systems that we've been investigating are also better for different types of conditions. So we didn't have one type of solution that would be kind of that magic bullet. So I think it would be very site specific, but definitely look at the literature that what we've published, check the website for our publications, and that should start to answer some of the questions.
Mm-hmm.
Yeah, Ron, if I may. Mm-hmm. So Corey actually worked on a system that from the ground, there's a visual system. And then since aircraft is approaching, the visual system can pick it up. And then using the communications so that the vehicle's information, such as where it is, how fast it's going, and so on, picked up by visual system, fed back into the vehicle so that it can actually manage itself without GPS. So that type of innovation can certainly be used to help approach and perhaps take off as well.
Mm-hmm. Okay, great, thank you. Also, Corey, another question for you. The question was, what simulator you used in your research, and how did it complement the actual flight testing?
Excellent question. We used a lot of different types of simulations depending on what we were testing. Most of the simulations we're using on my task were custom-built software. We tied most of the components together with C, C++. We had components built in various types of platforms like MATLAB. We used a lot of MATLAB scripts. We did a lot of the control modeling in MATLAB and MATLAB Simulink. So we kind of tie that all together. Again, if you look at the references, you'll get an idea about the different types of simulations we created. They're all NASA software, so if you contact me either directly or through this panel session, we can probably provide you more information and see if there's any way of getting you a copy of the software.
Okay, great, thanks. I got a message that I may be bandwidth limited, so I'm going to turn off my camera, and maybe that will help the situation. So let's see. So there's a couple of questions that came in about communication and the onboard systems used in our testing. And so this question is for Lou. And the question is, for V2X, did you look at the industry recommended update rate of 10 hertz being too slow, or the limited 30 megahertz bandwidth? Lou, you got that question?
Yeah, I could try to address it. I don't think we were aware of the industry specification that's being cited there. I can't talk about the test we did perform. The DSRC boxes were set to broadcast at 2 hertz, so as not to oversaturate the system. But that really wasn't the challenge. It was mostly range, given the 5.9 gig frequency and the power we were working with. The systems we worked with, the FLARM system, flight alarm, that's in the 900 megahertz band. and that was at I think it was about 500 watts it was working at. So we had very good results from that over a range of conditions. So yeah, I'm not familiar with the 30 megahertz specification either, unfortunately.
Okay, let's see. There's another question here for you. So the flight testing involved DSRC at 75 megahertz. Maybe you should confirm that first. The FCC is now limited bandwidth to 30 megahertz and put its weight behind the CV2X. How does that change things, if at all?
Okay. Well, again, I'm sorry for not being familiar with the industry specification being cited there. From CV2X, I can assume that's some type of cell communication, and that could be one way of doing, vehicle to vehicle or vehicle to ground infrastructure. We did some testing. I know others have been doing testing. Look at cell strength, cell link strengths, and that has worked really well, even in very rural areas. Once we get the vehicle up off the ground, we had great, cell strength. The problem we did see was in the cell quality. So as you get up in altitude, you start talking to a series of cell towers, and they start interfering with each other. It's just the nature of the beast, and so the cell quality could tend to degrade. So I think at first cut though, cell communication looks very promising. With some perhaps some additional testing or a different type of approach could work out really well for CV2X. So I'm not sure if I really answered that question, but I did give it insight to what we've learned from our testing.
Okay, great. This question came in, and let me kind of open it up to Lou, Corey, and Arwa, since all three of you have moved on to other projects and are looking at UTM or how UTM will adapt to other regimes such as advanced air mobility or urban air mobility. Are there any lessons learned, key lessons learned, high level, from your flight testing that may be applicable to these projects and field testing that's going to be coming in the future? So Arwa, did you have a comment about that?
Yeah, I guess it was more in terms of the locations of testing. We found out it was very important for us to involve test sites and try to test in different locations as opposed to just one general area. So I think that's something that would be important to do eventually. Also, I think it was useful for us to test with having interaction with a manned aircraft. Also, I think testing different technologies, prototypes on the aircraft was very useful. And I think that's going to be important for UAM aircraft as well.
Mm-hmm. And to kind of add a little bit to that, that I mentioned in my presentation, the integrated testing part of it, where you get these different separate pieces of technology to talk together and play well, and then integrate that all the way into the UTM system. Took some additional effort to accomplish, but provided some excellent results. So as we move forward into AAM high density vertiplex, that integration is front and center as we look to do the UAM prototype testing and vertiport automation assessments.
Great, thanks, Luke. Corey, do you need anything to add from your standpoint?
No, those are great answers. Good question too. Just to follow on what Ron said, that's something we found too, was that the technology, there was excellent technology available that we could utilize, but the integration was a non-trivial effort. And sometimes there's some foundational research that's needed to get that technology to the state of readiness for those particular applications.
Yeah, and I guess let me interject one lesson that we learned from particularly our TCL4 testing, where we're testing in new test ranges in Reno and downtown Corpus Christi. And certainly getting the approvals over and above what COAs already existed between the test sites and the FAA. For this particular testing that we were doing in urban areas, we had to go present more safety case and take more safety precautions because we're flying in inhabited areas. And so these other projects, AAM and such, they're looking at advanced flight tests on maybe traditional flight ranges, but also in urban areas. So the lesson here is work very closely with the FAA, keep them informed on what the plans are, what new aspects of testing will be done, because there's oftentimes there's multiple groups within the FAA that have to give these approvals, and they need to understand what the extent and the novelty is of the test, and they have to, to kind of figure out how best they can assess the safety and operational risks, and then grant approvals. So it was almost a full-time job from our point, because we were doing something new. We didn't understand it totally ourselves, and so how did we explain it well to our FAA counterparts? So that's just something that we experienced, and really, I'm sure it will be a major element in the future when doing these new types of flight testing with these experimental aircraft. Okay.
Something quickly. It wasn't just either that you require coordination with. I think it was very important for the municipalities actually had to have meetings with the public to tell them about what these tests are about, so they're aware, and to make sure that they're okay with this type of testing. And I think that was a good thing.
Oh yeah, that's excellent, Arwa. Yeah, in our case, both the Nevada test site and the Texas test site did a lot of work with community engagement and with the local officials, not only fire departments and police departments, but also city councils, and to get people on board. And really, I think the result of a lot of that engagement was both communities were enthusiastic about having NASA and our partners come and test in their communities. So yeah, that's an excellent point to bring up, Arwa. Okay, let's see, another question came in, and this one is in the area of the human factors. And let's see, the first one, in the human factors topic discussed, undefined procedures and operators had too little time to make complex contingency decisions. What were your mitigation strategies? Design playbooks, ? So that's, toss that out to Lynn if she's online, or Jeff.
Hi. So we were never in a position where we could specify what we were doing, and so we didn't have an opportunity to put procedures in place. But if we had, it would have been a combination of those things that Jeff mentioned, which is a training program so people knew a bit more about UTM and how it works, which would give them some awareness of what was going to happen in the system if a certain set of events happened. And then giving people a set of consistent actions they could take when some event happens, so that they have some way of, a checklist is a good example, but I don't mean that the procedures should be a checklist. But if you have a checklist, then you can work through it, and then you're only having to run on your own. You're only having to use other contingency procedures if that checklist doesn't work for you. So you can follow through a number of simple steps to try to get you back on track. So I think if we had been able to put some training in place and have some procedures in place, then people would have been able to handle contingency events more easily.
Okay. And also another question here, have you identified what information operators need to make better decisions faster? Or is there a gap in operators' operational knowledge in this complex environment?
There is a gap in operational knowledge in a complex environment, and that was one of the things we were trying to look at. But you can go back to some basic principles for decision making, which is people need clear information. the information they need if they have to make a fast decision shouldn't be buried under other information or down a menu. So you would want the information that people need to make a good decision to be rising to the top on your interface, and ideally in some kind of order, like the order that you would need to consider different variables to make a good decision. So I think you can apply some basic decision-making principles to an interface that you would use in a complex situation like UTM in an urban area.
Okay, great. Thank you. Let's see. Here's a question for Min. Starts with, thanks for the great summary of the FE Cube simulator. I'm curious how wind information is handled in terms of treating temporarily variation conditions, i.e. response to the wind field to diurnal heating, as well as how uncertainties in the wind field are treated in the Monte Carlo simulations.
Sure. So, yeah, so I think, as I mentioned, we try to formulate in a 4D kind of grids. So the 4D actually has a temporal component over there. I guess if you have a varied kind of wind condition, it can be taken into account. And that's for the first part. For the second part, yeah, so the main impact of the wind is actually on the trajectory generation. So we have 6-stop trajectory model, which can respond to different wind conditions. And sometimes the temperature, the density can affect the thrust, etc. Eventually can affect the energy consumed. So, which is kind of one of the key findings in our TCLs. When you fly at a different altitude, you're gonna see different energy consumption. So, for uncertainty of wind field, we actually, because we're running Monte Carlo simulation, so and each simulation takes some perturbation based on the wind field distribution. So every time step, you're gonna pick some random number based on the which follows the normal distribution. So that will essentially literally just mimicking what happened based on the certain assumption of the wind field. So that's how we take that into account in our Monte Carlo simulations.
Okay, thank you. So how is the FE3 Cube simulator being used by the system-wide safety project for urban air mobility applications? And I guess more broadly, are there other entities out there, academia or such, that you know of that are using the simulator and its performance?
Sure. So system-wide safety, they are focusing on the airborne risk. That kind of I described in on 1 hour slide about the past task. So they try to identify, given a scenario, what kind of risk it can be, or the chance they're gonna loss of separation, etc. So kind of similar, but for UM type of scenarios when you have corridor or different kind of operations. So speaking of collaboration with external partners, we try to push the software usage agreement, but still on the way. So we haven't have external users for that.
Okay,
we're working on that. So
stay tuned about that. Okay.
yeah.
Okay. Speaking of pathways, so I think Jawo, you think you can answer this one about in urban concentrated areas, would prescribed pathways be a better approach for optimizing strategic deconfliction?
Yes, indeed. We actually had a scholar from Korea, KAIST, named Dae-sung Jang, look into this back in 2017. Working with Dr. Corey Polito and the group he's leading. And in that setting, the main findings were two. One was it is really challenging to mix fixed wing and high-speed vehicle with the quadcopters or octocopters, if you will, because they tend to fly slow. So separation of those two may be advantageous in structured approach. And after that, the way this would go about is a fixed wing would really need fly above skyline, if you will, and for below skyline, then there can be a structured way to handle multiple layers of the drones, depending on, or UASs, depending on their performance capability. So yes, it can be a good way to handle this. And to look that up, we have a nasa.gov/UTM website up and running. And there you can go to the technical documentation area, and under 2017, you should be able to find this paper.
Okay, great. Let's see. So there's a few questions, Praveen, came in for you regarding UPP and ultimate UTM implementation. So the first one is one that actually came up this morning. I thought it would be appropriate to bring it up now. What is the implementation timeline for UTM here in the United States? And when can we expect UTM being real and operational?
Yeah, I think it's going to be a very phased approach for UTM, right? We're going to work through, I believe Jay always talks about, the crawl, walk, run approach. And we probably will apply something similar in the implementation sort of framework as well. And I think the first step to that is the UTM implementation plan. We know we are on the hook for that implementation plan 1 year after completion of the UPP activities. We are currently in development based off of a lot of the lessons learned of all these activities we've participated in over the past few years to develop that implementation plan. And so our first step would be to release that document in the very near future. At the latest will be 1 year after completion of phase 2, which phase 2 is just looking to wrap up here in the spring time frame with the release of a final report.
Okay. Well, since so UPP 2.0 was successful, it kind of begs the question, what comes after 2.0?
Yeah, so it's a very interesting question, Ron. I think there's a lot of activities going into realizing what we did as part of the test and validation activity and going into more of an implementation-centric activity. We've taken a lot of these interesting inputs from various areas, from industry, from other government agencies, and now we are starting to take a look at what it means to implement different levels of these services. In addition, I think we are also working with different areas within ASTM to, in the near future, accept some of these standards as well, so that we can push UTM forward. In terms of demos and activities, I think we are now in a time where we have to prioritize some of the next high-level capabilities that are going to be integral to having UTM be placed, and hopefully we can talk about some of those activities in the near future as well.
Okay, great. Let's see, Praveen, there was one additional question that came in, and maybe, I don't know if you can tackle this one. It says, will the UTM provide for the granularity of administering which operator can traverse a specific airspace? Question, state, city, administration, question.
I'm trying to understand the full scope of the question here. I think things like LANCE and facility maps sort of are our first instantiation into airspace authorizations. If I'm reading the question correctly here, as well as things like UVRs start to address some of those airspace access type of questions.
Okay, so I guess you think that it's still being worked, or it's in initial stages about how to kind of cope with this?
Yeah, I think we're in the initial stages of these airspace access question. But Ron, one thing I can do is if you do send over that question post this event, we're happy to take a look at it.
Yeah, okay, great. Well, that is the list of questions that have come in so far on Conference IO. Let me ask Chris or Anna, is the spreadsheet updated? Any more questions came in? Yep. Okay, if there's no additional questions.
No, you got them all.
Okay, yep. All right. Well, if PK is on, I know he had offered earlier to provide some kind of perspective on UTM and maybe reflect on where it started in your mind, PK, and some of the initial challenges with building momentum on UTM, and then given where we are now, kind of your thoughts on how it goes forward and its impact.
Yeah, no, thank you. I think this has been a great day today for sharing all the work that we have done collectively with FAA and industry members, with the rest of the world. And it's been a tremendous journey with UTM. And I have several lessons learned on UTM, really. And it's really power of the collaborative innovation that we see UTM basically embody. We started this idea in 2012, later part of 2012, almost 2013, February-ish, when I started to cultivate it. And a couple of times it was kind of rejected because it was too early and it was focused too much on the feasibility aspects of, and not so much on the reality of what likely to happen. But one of the lessons I learned, for whatever reasons, I felt so deeply about it in my heart that I kept on going. And we did a workshop about this, So that workshop, happened in 2014 February, and 2013. After the idea was rejected a couple of times in sort of internal seedling or kind of efforts, what changed the perspective of many people towards UTM is the Amazon's announcement right after the Thanksgiving of 2013. And basically people said, oh my God, this is real. This, drones are going to happen and we need to have a way to accommodate them. And then fortunately, I was still kind of pushing that idea. And then we got pretty good support from NASA's advisory committee to say, hey, what are we going to do about it? And then folks started to say, hey, we have a tentative solution and a path forward. It's called UTM. And then it kept on getting kind of more and more visibility. We did the workshop in 2014, February, with about 180 some people. And we got pretty good support as to this construct makes sense. Industry supported it. So that's when it started. I must have got like airspace systems program offered about $300K to kind of dive into the details of feasibility and concept details as part of the end of the year money. That was 2014. And then 2015 is when it became a project in itself, And one of the key that happened was not just the innovation on the technical side, but what I felt was the remaining supporting organizations. So for particularly the lawyers, the public affairs, and procurement, they all work together to help this cause. So the early stages, right around 2014, during that first workshop, we felt that we need to collaborate with industry, and I had identified already a number of key industry members. We went to the legal folks, and they started to make 2-3 agreements. Some of the companies don't exist anymore, others are still very prominent and going very nicely, making developments in UTM. And so once we set up 2 agreements, it took about 6 months, and then I literally went to the chief counsel's office and literally crying about like, this is taking too long, and we got so many industry members interested in participating. And so he developed this idea that, look, we should do this template agreement. So collectively, him and I and another attorney, 3 of us, basically we developed this template agreement that allowed us to fast kind of create these relations and partnerships with the industry. And that was changed the process. Then the public affairs people also started to get engaged and understand what we're trying to do and help the broadcast the message. We got a lot of excitement through TV and radio interviews and newspaper articles and things like that, magazines. Then came the next wave to collaborate with FIA to make sure that we were kind of not getting too much sideways with them. At the time, I used to say NASA was too fast for FIA and too slow for industry to enable these drone operations. And so we worked very closely with FIA to build relations, make sure that we are in sync with them, and the construct of UTM is palatable to their long-term vision and perspectives. And we found really great partners in the form of Steve Bradford, Jay Merkel, and many others like Praveen that you saw. And it sort of changed that dynamics, and we started to make progress through research transition team. Then in 2015, we built a big convention to kind of roll out this idea and have industry actively participate and influence the thinking. Because one of the things we said is we know certain things, but we don't know everything, and we need to take advantage of ideas and technologies that are out there. That's where the service-oriented architecture and pushing out third-party services and things like that started to evolve much more aggressively. So that's kind of how we started to get a lot of momentum by collaborative innovation and working with FIA as well as a lot of industry members. And one of the main lessons I have is basically collaboration, finding the right allies, making sure that the entire mission support organizations have a way to influence and support the cause, because they do have some creativity and they can help you reduce friction in getting things done. And then it became also international because that was one of the themes, to make sure that there is a harmonization of these ideas. And a lot of internal people at NASA really have worked hard, and you saw all of them that works so hard, much harder than I did, to make this reality. And it's just a really powerful lesson in sort of how the collaboration and best ideas bringing together and kind of open-spirited thinking makes you get faster. So that was just awesome. So I think one of the biggest lessons, cultivate that collaborative spirits for future to any big complex problems that we take on, which NASA tends to. So it's very rewarding to be part of this activity and collaborate with you all. So thank you for everybody's inputs and interests from industry and guiding. A lot of critics also help me get better at thinking and ideas. And so I'm very much appreciative of everybody's participation, and look forward to continue to collaborate on next big things.
Well, great. Thanks, PK, for that perspective and some key lessons that you acknowledge and will be carrying forward. And I think that does have applicability to other projects going forward too. So, okay, well, that concludes this second Q&A session. And let me turn it back over to Jae-woo for the...
Yeah, PK, really appreciate you starting this whole thing, and then Ron, really appreciating you guiding us through the conclusion of this particular project, and also handling the questions and answer session. Now, I'm happy to introduce a panel. We will be discussing global impact of UTM. And let me introduce our moderator, Joey Rios. And Joey, please go ahead.
All right, thanks, Jay-Woo. Yeah, no, that was great to hear from PK, and glad Ron was also here to run the Q&A, and Jay-Woo introducing this. I was just 3 of the 4 project managers that I've had on this on this project lined right up. So thank you guys. Again, hearing PK's perspective on this is really valuable and really kind of sets the context for everything we're talking about. So appreciate that very much, PK. So yeah, this panel, we are looking at the global impact of UTM. And just, 7 years ago, UTM was a simple idea, summarized by a white paper at NASA Ames, as PK was describing. And then NASA ended up developing a coalition of partners, including the FAA and industry, to begin discussing and developing and testing the concept to prove it out and to produce a path towards operationalization of it. And over that time, this revolutionary idea of collaborative airspace management was brought to life. And it took hold not only in the US, but it spread from NASA to the US to the global aviation community. So in this panel, we hope to discuss kind of that process and the current state of the UTM in the US and abroad, as well as some future steps. So I do have an excellent panel here with me, and they're going to carry the day, and you'll hear less and less of me, I hope. We have Jeff Homola from NASA, Amit Ganju from ANRA, Phil Cannell from ASTM, John Coggin from the Virginia test site, Sebastian Babiars from GUTMA, and Ronaldo Negron from Wing. So what I'm going to do is just kind of go around the horn with you guys and have you introduce yourselves, and then we'll get the discussion started. So let's go ahead and start with the list that I have here, no particular order. Jeff, you might turn on your camera and saying hello.
Hey, thanks, Joey, and hello to everyone. Jeff Homola from NASA Ames. Been with the UTM project from early on. Served as the integration and testing lead throughout that time, as well as the concepts and use cases working group co-lead during that time as well. And as part of the project, was involved in some of the international collaborations that we had going on, which was really exciting and interesting. I'll hope to get into some of those topics during the panel questions, as well as some other collaborations that were going on now and into the future. So that's it for me.
Great, thanks, Jeff. Amit, please say hello.
Hey, Joey. Good afternoon, good evening, good morning, everyone, depending on where you guys are. First of all, thanks for giving me the opportunity and inviting us to join to join the panel. I'm with ANRA. I'm founder and CEO of ANRA Technologies. For those who are not familiar, we are an airspace management and mission management company. We are headquartered here in North America in the DC area, and we have operations in Europe as well as in Asia. We work with enterprises and air navigation service providers. NASA is this is a very near and dear day to me because we have had the opportunity to work with PK. I remember my first conversation with PK in 2015 when this whole program was getting off the ground. So we have had the privilege of being associated with NASA since in all the TCLs and have scars to prove that. So really exciting to see the culmination of the whole project. Outside of that, we've been engaged in different programs, whether it's US or internationally, like UPPs, again, working with NASA on the Advanced Air Mobility Program, and then in Europe with programs such as like CESAR, in UK, Open Access, UTM, etc. I am also on the board for GUTMA, which is the Global UTM Association. It was alluded to in a bunch of discussions earlier today, focused on global harmonization. I realize we have a couple other members on the call, and Seb is going to represent GUTMA, so I'm not going to touch much on that. Outside of that, we as a company believe heavily on standards. So I also co-chair the ASTM F38 standards working group, which is working on the UTM standards. And those are some of the standards that have been, as Joey mentioned in one of his earlier talks, moving from research to more industry and operationalization and standardization. So these are some of the standards that have come out of that. We actually exercise these standards as part of UPP, the UTM pilot project, use these standards And so have other projects in Europe, like in Open Access UTM project, and in Switzerland, the Swiss FOCA projects, they're using that. So very excited about that and continuing the collaboration as we move forward towards urban air mobility and so on. So thank you.
Great, thanks, Amit. And yeah, and mentioning ASTM, why don't we have Phil say hello?
Well, thanks a lot. And following Amit, that's going to be a tough one to follow. So, but anyway, Phil Kennel, I'm the chair of the ASTM F38 Committee on UAS. And as most of you know, we work on UAS standards. What I'm happy to say is everybody on this panel has been associated with ASTM and supporting the work we're doing specifically with UTM, topics like UTM, and additionally remote ID as well. So I'm very pleased to be here. And this topic about standardizing and globalizing, so I think is near and dear to me. We've been working at ASTM to ensure that we are coordinating this effort with other SDOs as well, so we don't duplicate effort or we don't produce a standard that is in contrast to somebody else's. So it's very important to us and to industry as a whole that we have one architecture for UTM in the future. And with that, I'll turn it back to you, Joey.
All right, thanks a lot, Phil. And on my screen, at least, right next to you is John. John, please introduce yourself.
Yeah, thanks, Joey. Really appreciate the invitation to join the talented group here on this panel. And yeah, John Coggin, I'm Chief Engineer with the Virginia Tech Mid-Atlantic Aviation Partnership. And and in my role here, I lead all of our UTM and detect and avoid research. So I've had the pleasure of working with a number of the folks that we've heard from today and have gotten a real opportunity to kind of get my hands dirty and get a real practical exposure to, providing UTM services to a variety of stakeholders and evaluating, how well it serves the needs of those various stakeholders. So pleasure to be here.
Great. Thanks, John. And Sebastian.
Yeah, thank you, Joey. Thank you for having me here. It's really a pleasure to be in this conference where I started my experience with UTM in 2015 when the first NASA convention happened. So glad to be in this loop. My name is Sebastian Babiš. I'm representing GUTMA, Global UTM Association. So maybe some of you already hear about us. It's an association which was founded in 2016, and we are focusing on harmonizing the initiatives around the world for enabling the scalable and interconnected UTM services in the different regions. So in this session, I will explain what we are doing here and how we can help on that. So thank you.
Excellent, thanks. And finally, last but not least, Reynaldo. Gotcha.
All right, yeah, taking a minute to get off of mute there. It's been really great to follow today and kind of relive, I think, a journey that you've mentioned that's taken a while. But a quick introduction of myself, Ronaldo Negron, head of UTM at Wing. Wing is a drone delivery company that does delivery on 3 different continents today, in Australia, Finland, and the US, flying over people, delivering goods to where they live. And we build that on our UTM services and a lot of the work that we've done through kind of the TCLs and UPPs and use those services again on that daily basis. And we also are engaged globally in UTM projects as well. Amit mentioned a lot that are going on around the world, but we're seeing work in Switzerland and France and the UK, Finland, and a range elsewhere in the Europe space. There's a lot going on in Australia and the work there, and engaging kind of an ecosystem set of providers. And so we're really excited to see the things that have started as part of this research and started in the US start being adopted around the world and being tailored for the regions and meeting those needs. And a key piece that's making that successful is the standards work that we've talked about and seeing that be a consistent piece across all of those activities. And so we're very excited to participate in the standards work. Mike Glasgow from my team co-chairs the UTM standard with Amit, but we're seeing that as a consistent way of being able to make these services reproducible, keeping them low cost for operators and keeping them global, and seeing them demonstrated, beyond just the U.S. We've seen them now also be used on 3 different continents, and that's a pretty exciting spot to see these standards maturing. And as an example, I think of the global impact that we've seen from this work.
Great. Yeah. Thank you guys all for taking the time to join today. I really appreciate it. And I think that, this is a discussion on kind of the overall global impact of UTM. But I think before we get into the global impact, let's kind of just let's start kind of domestically here first and think about, your work on UTM systems and UTM research and testing, and think about what the impact of UTM has been, I guess, domestically, first of all, from a U.S. perspective. I'll just toss it to Amit first, if you don't mind starting.
There you go. All right. Thanks, Joey. So it all started here, like we back in 2015. So we've come a long way. So in terms of what has happened, like I always talk about innovation, experimentation, and operationalization. That's how I talk about the phases. So I think we are at this point where we are transitioning from that experimentation phase more towards operationalization. So LANS was the first aspect of it, right? So the LANS was, even though it didn't have tracking, conformance monitoring, but at least it was the authorization and the approval services and controlled airspace. So that was a great first step. And as there's a lot more work, so what I see is the research from the small UAS world kind of dwindling down as we saw with the culmination of all these TCL4. But now you see the parallel effort, which is staggered, the AAM project, Advanced Air Mobility, kicking off, which is going to build on top of what is happening, what happened where UTM project, TCLs laid the foundation. And from a research point of view, the AAM starts taking off, and then you see these pilots and trials happening. And then in terms of an operational, you have these exemptions by operations by exemption, like BVLOS, the kind of operations Wing is doing or others are doing, and that now you hopefully, as with the new rulemaking coming out, ops over people, nighttime ops, and all these things, we'll see a more significant transition towards operationalization of the small US operations, and in parallel, start more researchy efforts on the X3, X4's advanced air mobility concepts. And hopefully transitioning, starting with cargo and then towards humans. That's the way I see it.
Great. And yeah, you mentioned Wing. So Ronaldo, in your perspective, just domestically, kind of the impact of UTM.
Yeah, I think, look, UTM and the understanding of strategic deconfliction and kind of knowing that we can have, specific safety layers that enable one pilot to manage many aircraft, to be able to move to a manage by exception over, a fully positive control environment. That's really shaped the way for us to have a scalable delivery business, in addition to many of the highly automated features of our aircraft. And so we've seen those UTM technologies be a key enabler there. I think we're excited for the moment where industry starts sharing data, operationally. When we have services that are overlapping and when that interoperability occurs. And I think that's kind of the next magic stage for UTM in the US, is being able to see that capability come through and enabling kind of broader and more scalable operations. But again, one-to-many ops is a key example of something that the strategic deconfliction and other technologies can help enable and support.
Thanks. And I think I'll just bring John in here really quick. John, if you don't mind, seeing some of these technologies tested at your site and your sister sites across the country, just kind of where UTM is from where it was and where it might be in the next couple of years.
Yeah, as a lot have said, it's been quite a journey since 2015 for me anyway, but some earlier, even as PK was saying, 2013 or so, as these ideas started to bubble up. And as Amit says, we've certainly been in the research phases here over the years. It's been tremendous progress from my first participation there in TCL1 and then more recently in the FAA pilot programs. I think it's important that folks don't think of UTM as just, an air traffic control for drones. It really is the ecosystem that all the important hooks attached to, for surveillance and weather and UVRs and public safety aspects. It's not just about deconflicting drones. It's about providing that entire ecosystem. And so, I've seen a ton of progress. I think, the back end and the software and the message exchanges are very mature at this point. So it's great to see the standards bodies, kind of putting that in writing and getting everybody on the same page to take all the lessons learned from the research and develop these standards. I think, what we'll see over the coming years is to prepare ourselves for what Ronaldo mentions, which is, true interoperability across disparate organizations and providing interfaces for, the average pilot, not the large organization like an Amazon or a Wing that has a fully integrated system, but, the interfaces that are going to be utilized by our VLOS pilots and other, kind of one-off operations and making those interfaces much more streamlined and providing those safety critical functions in a way that the human factors folks would be happy with. So, it's been great progress, and it seems like, just a few more little blocks to put in place on the path to implementation. So.
Awesome. Thanks, John. And we've hinted at it enough here. I think it makes sense to bring Phil in to kind of just kind of talk about this standardization. Everyone's talking about ASTM. Kind of just fill us in and the audience in on the state of that and the importance of that bridging us to kind of international interoperability for things.
Yeah, I think both John and Ronaldo hit on it a lot actually. And as far as standards development's going here, we always keep an eye out for what's going on internationally. And whether it's, John mentioned weather as well, we're not only are we doing the architecture for the UTM standards, but we're doing the supplemented data SDSP standards as well. One particular one we're working on, for instance, is weather. I mean, and my past from NOAA, weather is very near and dear to my heart. But we need to take a look at what's going on internationally as well, not only what's going on domestically, because industry doesn't want multiple sets of standards that are not interoperable. And that was, I think, key to what John said. In a federated system, you definitely need this interoperability. And what we're working on diligently is to have that. And to that end, we have MOUs with other SDOs to ensure that we manage this interoperability well. So we signed an MOU with ISO, who's working on standards for UTM as well. They're working on really, safety and quality standards, not getting into the technical details that ASTM is. We're also developing an MOU with EuroK. There's work that they've done in geofencing and geocaging that we think is going to be important to us in our standards development as well. So we need to work with these other SDOs internationally and be sure that nobody gets stuck in that not invented here syndrome. UTM is a very challenging topic, and it's not going to be solved by one SDO or one organization alone. There's going to be multiple standards, and they all have to be interoperable. And that's what's good about GUTMA. GUTMA as an industry organization is really bringing all these groups together and supporting that. And that's a good lead in for Sebastian.
That is correct. It is a great lead in for Sebastian. So, Sebastian, let us know a little bit about what GUTMA is, what it does, and kind of your perspective on what we're talking about so far.
Thank you for this great intro. Correct. So the GUTMA objective is to harmonize activities which are happening around the world and connect with the stakeholders and the members of GUTMA who are participating in this domain and providing the various services. So GUTMA focuses to find out which standards will be required for enabling the UTM. GUTMA is looking at new technologies like the connectivity. So everybody was talking about the mobile networks. So we are working with GSMA and other folks on the idea how the mobile networks should support the drones and the UTM, what kind of parameters might be applying there. GUTMA also works on the regulatory aspects. So we are collaborating a lot with FAA, but also we are working closely with the European Commission and EASA to understand what the upcoming regulation will mean for our members and for the ecosystem. So we can really support it from that perspective. GUTMA also working on we call it the global UTM map, where we are presenting where the UTM deployments happening, and we try to somehow deliver the information to the members and also the rest of the world, how the UTM is developing around the world. So that's that's the various aspects. We are pretty proud about the members and the work what they are doing. And we're really happy to have more members who will contribute to these activities and help us to build up the sustainable and harmonized UTM ecosystem.
Excellent, thanks. Let's kind of shift into that international stage and kind of the things that are happening internationally. And I'll bring Jeff in here really quick just to give a NASA take on how NASA's collaborated with folks to look at international operations.
Sure, thanks, Joey. We certainly had a lot of kind of international interest, but we did have one really dedicated source of collaboration over the years with JAXA, the Japanese Aerospace Exploration Agency, working very closely with us dating back to 2016, working under a formal agreement to look at the integration of UTM into disaster relief, disaster response types of operations. So in previous to that, JAXA had a system in place called DNET, Disaster Relief Aircraft Information Sharing Network, which they've been using to manage disaster relief or response operations for kind of optimizing, managing aircraft assets during disaster response. But there was a clear need or a gap that was identified for being able to incorporate UAS into their response operations, which DNET was not capable of at the time. And so that's really where that kind of tripped off our collaboration, and we started looking at how UTM, we can take what we had developed so far within the UTM project and integrate that with their DNET system over in Japan and look at how that information exchange works and how we can establish the right protocols and message exchanges to be able to manage small UAS in conjunction with their DNET system. And it was a really kind of fun time, worked really closely with Marcus Johnson on that collaboration, and then a small team over at JAXA, and that involved eventually live flight demonstrations in Japan as part of a larger disaster response drill that we were able to go over there for. And there were some firsts that we had wins over there in terms of the first manned helicopter that was operating within the UTM system. So we were able to track that operation as part of a disaster response effort through UTM and be able to see that operation over in Japan and over in our lab at NASA Ames as well. And that was really the first kind of international connection between our systems and other operators as well at the time. And it really, I think, set a good stage for further work in that area. You know, disaster response has come up multiple times so far. It's really a key area where I think UTM can contribute. That's another really impactful area that really speaks to the work that we were able to do internationally with JAXA throughout these years. And they did another flight test back in 2019, kind of looking at some of the more pilot-focused views of being able to operate within the UTM system as well as kind of a manned operator in this type of environment. And so really fruitful collaboration there, a number of publications coming out of there to keep an eye out for. So that's been kind of the primary one, Joey, and I think we get into some of the more extensible aspects of UTM in later in this panel.
Yeah, thanks, Jeff. And you know that collaboration with Japan, it was really fruitful for both sides, and I think for UTM as a whole. It's a heavy lift for NASA to actually work with international organizations, right? There's a lot of stuff that has to fall into place to make that happen. So actually, I don't know if Ronaldo and Amit know this, but we kind of consider you guys our UTM ambassadors, right? Or you know, UTM graduates out of the NASA program, right? And we really want you guys to take that internationally and kind of, you know, figure out how that's going to work. So from your perspective, I guess operational, I'll come back around to Amit and Ronaldo. So Amit, you first, just kind of the reception of UTM and how it's been going kind of from a service provider's perspective internationally.
That's actually a great question, and thanks for the kind words. So we try our best to live up to your expectations. It's a tough bar, high bar, but what we are seeing, I can talk to personally, and Ronaldo probably has different experiences. I can talk, we are in a few markets, like ranging from Asia and India, Switzerland, UK, and in Europe. So the places where we are engaging early, when we started this process early on, like 3-4 years back, it's not made here, like what Phil mentioned. It's not great. we want to create their own. And there were a lot of efforts early on to create parallel or competing architectures. But with our, and not just us, many of the industry stakeholders, their engagement in different, whether it's different initiatives in different countries, such as in UK or in Switzerland, or even with EASA in Europe, we have been able to, as a group, influence, and because the way we look at it as it's logical functions. In a UTM system, there are logical functions that need to happen. At the end of the day, everyone needs those similar logical functions. There are some regulatory overlays that tweak things a little bit. You may do it this way versus that way, but the key functions are the same. So we have been, to a very large extent, have success. There's still some pushback in some markets because a lot of times, if you look at a pure federated market, it impacts some business models, right? So the business model picture comes in, but leaving that aside, there has been acceptance. So for example, open access UTM framework, we've been engaged in that since 2018. And there we started with somewhere, but now as of yesterday, there were live flight trials happening. They wrapped up the live flight tests yesterday, and that's all building on top of the ASTM standards. In Switzerland, we did the demonstration, last fall or I forget. So it was all in line with the ASTM standards. And we are going to be doing some CESAR projects in Europe for UAM-like stuff. So similarly, like what we did for X3 using the ASTM draft standards, those are going to get used there. And so a lot of the concepts are there, but that doesn't mean it's the end all be all. We also understand it needs to be adapted to the localized environment. So it's not just a one-way street. So I want to be clear about that. It's not just, we are just saying this is the mandate and you use it. We are saying here's some of the building blocks. Now let's see what the gaps are and what can we bring back to modify it instead of starting from scratch to make it more globally acceptable standard. So we are seeing a lot of stuff like that. And there are some one-offs like in Asian countries, like where we are engaged, for example, in India. So they're also, there's their flavor, but they are leaning towards taking components from ASTM and standard and the work NASA has done.
Excellent, thanks. And Ronaldo, your perspective from kind of becoming operational in other countries, kind of just the reception and kind of either the hurdles or successes that you've seen.
Yeah, I think you can somewhat judge your success by how much other people present your topics. And I really think if I could be paid $1 for every time I saw the NASA UTM architecture, could have probably made more money than most of the drone industry, depending on how you look at it at this point. I think it's been quite a popular and well-adopted model, and I think something that's become increasingly well understood. And what I think as people look at it from a service provider perspective, there's many countries that are excited about that model because that means that their local markets, the people who are investing in their country for their services, can export it to other countries and be able to have a chance for broader investment. We saw DSNA on one panel, the French ANSP, talk about that, hey, is their market big enough for investment alone, or does having a globally harmonized approach with standards and kind of this model enable their market to take off even more and have better level of investment? And so I think we're seeing people around the world recognize that this model and this kind of openness and the standards-based enables investment at different levels and enables even their local markets to export and expand. And I think we're seeing that as a quite amazing trend and an enabler for large parts of the world. Specifically in Switzerland, I'll talk not about us, but there was a startup company that participated in the trial that Amit talked about a year ago, and it took them a month to implement the ASTM remote ID standard and demonstrate it, get it checked out, and be included. And that was a startup able to do that on their capital, and I think they were a 2-person company. And so from that perspective, really trying to make sure that this industry is accessible and able to be as broad as possible to support a very diverse number of operators is quite incredible. And so I think we're seeing beyond just kind of the graduates, but people around the world kind of seeing the value in that and how that enables their industries and enables them to participate in a lower barrier to entry across all of that work. And that's, again, I think part of the traction that we're seeing around the world.
Great. Yeah, let's just kind of continue that train, Sebastian, if you don't mind. Any other context in terms of the interacting with the ANSPs or the CAAs in terms of how they're adopting it or how they're thinking about it or anything of that sort?
Yeah, that's good. That's a good question. So as I'm located in Europe and my daily work is a BD for another USSP, so I noticed that many ANSPs and CAs maybe like year or 2 years ago didn't really know what the UTM means for them. And I think that the work which we are doing here in this group is also educate them how the UTM can enhance their businesses and how the UTM can enable some scalable operation in the country which they're representing. And I think this is also an important aspect of the whole discussion which we have here, and how to translate the technology to the services. And moving also forward here is the topic about the regulation. So the Europe is a bit more complex scenario here in terms of regulation. We have 28 countries. Each country has different flavors. We have one European Commission and EASA, which are managing the regulation for aviation for those countries. And the point is that the concept is coming into the point that countries want to equip the ANSPs with some, let's say, regulatory framework where the ANSPs will play the role in the UTM, which is pretty obvious, and I think it's very correct. So ANSPs are targeting to deliver some core services. In Europe, they are called like central information services, which are part of the use-based architecture. And the rest will be left for the market and for the USSPs, so use-based service providers. And that's pretty interesting because a Commission envisioned that most of the services has to be in the competitive environment, where these USSPs will have equal access to the core services which ANSPs will deliver, and this will enable the scalable and really operational services for the drones. So in this sense, the use-based UTM in Europe is targeted to really enable the full blow of services, very scalable and harmonized services, and for that we need the standardization. For that, we need the associations like GUTMA, which will bring all stakeholders together and all of them will talk in the one voice. So the regulators and countries can understand it as a really solid and mature services and systems which can be deployed there.
Thanks, Sebastian. We've kind of danced around it a little bit. I think we're all kind of steeped in UTM and kind of how everything's going forward. But Phil, would you mind giving us a quick little breakdown of some of those key standards that are being developed, not just by ASTM, but the other SDOs that are going to kind of enable all of this? I know we've mentioned them all tangentially, but maybe more specifically.
Sure. And I think you can't just pigeonhole a specific group of standards as being, UTM oriented. So, additionally, what level of certification of the aircrafts do you want to have in operating in a UTM environment in congested areas over cities? So there's a lot of work being done on that. I think you may be familiar with the durability and reliability means of compliance that the FAA put together and ASTM put together the test methods to validate that. I think that's one standard that's being worked on that people won't really think of as a UTM standard specifically, but that was really put in place so that package delivery platforms can operate in a congested environment or even in a UTM environment. Additionally, the remote ID standard, which everybody has heard quite a bit about, we've been working with our European counterparts at ASD STAN to satisfy their remote identification requirements. And even though the FAA took out the network portion of remote ID, which we looked at as a fundamental building block for UTM, I was very happy to hear, which I knew Jay would say this morning, that even though we took it out, network is still going to be critical to a UTM architecture. And ASTM is actually leaving the network portion of the remote ID standard in the standard because we think it's a value and it could be used at a later time. But specifically with EUROCAE, we're looking at an MOU to collaborate on geofencing, geocaging, et cetera, so forth. With ISO's developing several UTM standards, none of which we think conflict with the overarching architecture that we're putting together. They're really looking at some fundamentals or functional requirements Our standards are being a little bit more technical oriented as well to support a UTM architecture. So I don't know if I went around in circles or answered your question, but there's a lot going on in that environment, and I don't want to pigeonhole just somebody who's calling we're developing several UTM standards at ASTM, but there's a whole lot that goes into that. The detect and avoid standards, for example, beyond visual line of sight standards that we're working on as well. We just established a working group to look at precision navigation and timing that we think will be a supporting element to UTM in the future as well.
That's great, Phil. And I'd like to go back over to John really quick. Given, we'll take a quick technical detour, right? Given all those standards being developed and some of the testing that you've been able to see out in the field, what are some of those major technical gaps that you think are still there before we actually can realize a lot of this? Or maybe there are no technical gaps. What are you kind of seeing in field testing this stuff?
Yeah, well, I mean, it was a natural progression of the research to kind of move the ball forward a good distance and then take a little step back to address the standards and implement those standards. And so in some of the recent iterations that we've tested, some of the technical capabilities weren't as mature as they were at NASA TCL 4 levels. So, but again, that was a natural progression to take a step back and begin with a standard that could be implemented quickly and have the robustness to carry it forward. So, there are still some gaps. I mean, in the current V1 standard, the strategic deconfliction and negotiation, the whole access to airspace and doing something more sophisticated than first come, first serve is still a gap, in my opinion. There's a number of gaps that might not really be addressed by standards, but are still gaps nonetheless that industry needs to look at. And you'll hear me talk about this a lot, is the back end versus the front end. The back end software and the information exchanges are being well dictated and well prescribed by the standards. But the front end interfaces, what the pilots actually interface with, is something that we've got a lot of really great hands-on experience with and generated a lot of good user feedback. And so there's not a one-size-fits-all solution. There's enterprise groups that are building their aircraft and implementing their delivery services end-to-end, and they have complete control over their software and can implement that in a very prescribed and focused means for their business objectives. But there's certainly going to be, the need for other softwares that address, other users that the inspections and the non-routine events that are handled by individual operators that don't have kind of a full enterprise solution. And so, there's a number of improvements on the interfaces that those operators are going to utilize, that need to happen. And I'm mainly pointing to the safety critical functions. And I think something that Lynn pointed to earlier in the human factors discussion, making sure that the alerts truly serve their intent and that they don't, get buried in other information. So, really looking at the human factors of the displays and how they address the true intent of, the mitigations they're there to provide. So.
Awesome. Thanks, John. Let's continue this discussion about gaps, I think. I'll go to Jeff first and then maybe go up to the operational side with Ronaldo and Amit, if you don't mind. But any other either technical or non-technical gaps, Jeff, that you see kind of as barriers to, further adoption or progression? Anything that stands out to you?
I think actually just John really highlighted some of the gaps that we identified through our research within the kind of formal UTM project. And it's great that, well, it would have been great if it was all incorporated very early on and, human factors was part of the overall kind of development at scale. But that was really part of the research that we needed to incorporate on our end at NASA as we kind of developed the concept and the implementations. But it's nice to kind of see now that we've kind of progressed to a point where a lot of the kind of earlier engineering and technical issues where we've moved on beyond that and evolved to the point where we're really able to look at some of these more operator-focused types of considerations. And so I think that continues to be a gap, kind of what John and I had presented on behalf of Lynn, to really look at the operator interfaces, especially as we start looking at these more complex control paradigms, this like M to N idea of, one or many operators operating many vehicles all at the same time. How does the UTM system accommodate that? What are some of the key considerations that can enable that sort of like safe implementation of an approach to being able to control? So I think those are some of the kind of main gaps that are on the horizon, in addition to some of the other areas that we're finding some of the UTM concepts kind of moving into right now, but at least sticking within the kind of UTM umbrella. I think those are sort of the main immediate gaps, but there's probably others that I'm sure I'm not capturing that others may be able to expand upon here.
Well, I'm sure Ronaldo can expand upon that. Any technical or non-technical gaps or barriers, Ronaldo, kind of from your perspective, domestically, internationally for UTM adoption?
Yeah, I think one of the things that we've seen through all these activities, and it's part of research and development, is the validation and time to make sure the systems are interoperable is very manual, right, in the way that we do it today. And I think Switzerland found this a bit in their rollout of kind of a soft launch of a national remote ID. They did a very manual checkout process. And I think what we see as kind of a huge investment this year, and we're seeing some work in the open source space around intra-USS supporting this, is automated testing for interoperability and approvals of saying that you're meeting the ASTM standards. I think that ability for people to roll out software on a weekly basis as a service provider and to be able to check out and make sure it's working across the ecosystem is quite critical for that next step of evolution in that interoperability and that set of scale. And so for us, automatic testing around that interoperability is quite critical. And I think we can see in this kind of new age of air traffic, open source tools that enable us to go and support that. So I think that's kind of a key piece of what we see going forward, and is probably the other lesson learned John could talk about in terms of the process, for moving forward. The other piece, just as someone who's kind of seen a range of operator interfaces from Lance all the way to kind of our operations, it's actually really quite hard to make sure that the operator interface is contextual to the type of operation and meets that ConOps and what that need is, and the how automated the aircraft is as well. So I think we know that UTM provides the ability for diverse operator interfaces to be built to meet those needs, and I think we're going to see as UTM becomes more regulatory certain. Right now, there's not a clear regulatory path to it. As we see that become more certain, I think you'll see a diversity of interfaces that will come and achieve that, but can also match the operational risk and intent and the automation of vehicles that will come as well.
Excellent. Thanks, Ronaldo. It's great to hear you talk about the interoperability and the automated checkout process. And hopefully folks are referencing our papers from the TCL4 checkout process that are because going through that, we're trying to get eight different implementers of a spec to make sure that they all talk to each other appropriately. It's a very detailed thing you have to go through to make it happen. Anyway, Amit, any other gaps or barriers that you might want to point out?
Yeah, a couple of things I wanted to touch on is I think we have to go at this in an iterative fashion. Let's be candid. We know that we don't have the density of U.S. operations. You don't have 10,000 aircraft in the sky at the same time. So if we wait for that ideal, perfect solution to get airborne, we'll probably never do that. And not trying to one of the things you take the path of least resistance. The first come, first serve is what we believe works in the near to midterm. Now, is first come, first serve going to stay there forever? Not necessarily. So, but I think as we iterate, as we keep moving forward and we get more data, we get more metrics, we will evolve there. And the concepts there are some things that still, especially when you move at a global level from a harmonization point of view, so your deconfliction, strategic deconfliction, are you going to strategically deconflict only the small UAS operation below 400 feet? Are you going to consider it as a non-segregated airspace where you have maybe UAM traffic, man traffic, and where does that deconfliction happen? Does that still happen out there at the USS level, or do you need to have an additional node sitting in the or do you need to define an interface to pull the data from ATC in a two-way where you do that? So there, as we move into a higher density operations mixed with controlled man traffic, how do you handle this strategic deconfliction? In segregated airspace, it's pretty easy. That's not hard to do. So that is one of the areas I feel needs to be worked on. And UI UX, I know what John is saying. We've had these discussions. I second him on that. The challenge has been, we've always said the operator interface is, even during the research aspects, I know with NASA TCLs, we said, hey, operator interfaces, we are not dictating the guidelines, right? We are not saying it needs to be a red circle versus a green circle versus an amber circle. So we never did that. And unfortunately, fortunately or unfortunately, on the standard side, that's the kind of approach we have taken too, saying, hey, we are staying away from the operator interface. That is between the GCS provider and the operator that they decide. Now, is that the right approach? Don't know. Based on the feedback, I know John has an opinion, and I kind of see what he's saying, and I agree. I think we need to that is an item where we need to kind of come to an agreement as an industry, as a regulator. Is there a minimum set that needs to be complied to? I don't think all interfaces will ever look identical, but are there these minimum attributes that need to be factored in? That's my thought process.
Awesome. That was all great stuff, guys. I'm going to kind of keep staying on the technical train a little bit, maybe go to Seb and ask about the different approaches to the UTM architecture. All day today, we've seen everyone presenting kind of the UTM architecture from the NASA perspective, with multiple USSs talking to each other with one kind of portal to the FIMS. This architecture is actually more flexible than just the way the US wants to implement it, right? It's amenable to other implementations. Can you kind of talk about the other options that might be there in terms of this architecture implementation by other folks?
Yeah, sure. So that's a good question. So I think it's referring to this standardization and some kind of common understanding how the UTM should work. So this other architecture I already mentioned here is that we are talking in Europe about it. So it's called U-Space environment, and we have inside this CIS, which is partly like a FIMS, more or less, but with the focus really on the aviation or traditional aviation data, which is coming from the ATM systems. And here we call it like a centralized information services, and those services should be distributed to the other stakeholders like the U-Space service or UTM service providers. And this architecture also indicating that there will be the competitive environment around. So that's the one architecture which we are working on in Europe, and we are promoting it and discussing with the regulators. So I think that this is also the aspect of the standardization here, that the regulators are setting up the regulation about this. And whenever I talk with the countries and the CAs or ANSPs, they are always trying to understand how they should implement it. And which roles the different stakeholders in the country will play here. So I think this also reflecting to this a bit more commercial model, how the business will run around that, and where the players will monetize that. So I think that in this sense, architecture looks pretty similar, I would say, to the US model, with some caveat which are more representing the local environment and which has to be adapted here.
Great, thanks, Seb. So we've got about 10 more minutes here. It was touched on a little bit by Amit a few minutes ago. This concept of a kind of a collaborative airspace that wasn't something that really existed, 5 or 6 years ago, in terms of how the airspace is managed, right? The traditional way was always kind of a central authority providing all the control and management of that airspace, everyone talking to that authority and getting their information back out, and moving towards what we're seeing in UTM of this collaborative environment of intent sharing and information sharing in order to take some of that burden and the bottleneck off of that ANSP. Are there, looking forward a little bit, I'm just wondering if there's any lessons learned or caveats or excitement about the application of this to other domains like UAM or AAM or these XTM environments, as we've started to call them, either from a standards perspective or a technology perspective, whatever it might be. or from a testing perspective for that matter, right? How do we learn from how we tested UTM to get to UAM? And I guess I'll start with Jeff. We haven't heard from you a little bit. I guess some of the things we can learn from our UTM experience that would bridge us to these other new domains.
Yeah, I think one thing that's important to keep in mind that I think sometimes gets lost when we start talking about these other environments like AAM and the XTM environment is that nobody's really proposing a straight swap of UTM into those types of environments. I think it's understood and recognized that there's elements to take from what we've done within UTM, but there's going to have to be additional changes that are really unique to each of those environments. And so that needs to be kind of understood and captured as we kind of move forward into those different types of operating areas. And what's most exciting to me right now is kind of seeing how it is really applicable in these other areas as we kind of move into AAM. It's been talked about so far, and then some of the other areas like PK's foreseen in the past, like the application of UTM concepts to the high altitude stratosphere, so ETM, upper class E, traffic management, and how these types of service-based approaches can apply to kind of not burden the traditional air traffic control system, but be able to have a more service-based cooperative approach to being able to manage traffic where we're not necessarily planning on provisioning services up there. And so I think there's going to be plenty of lessons learned as we kind of embark on those different research paths that are going on now for ETM. There's space traffic management, which has been in the discussion as well, and then more near term right now, which a lot of us are involved in, is this advanced air mobility in terms of how can the service-based concept apply to the management of that those aircraft and the traffic. But what really gets interesting now is the interaction between kind of these services and that system that's going to be in place for managing that traffic and how it interacts with the traditional ANSPs. And so we didn't quite get as far, I think, within our kind of UTM project and understanding that interaction between ANSPs and UTM. And I think that is really sort of like a huge area for us to really explore in AAM and ETM as well. So I think those are some of the, not necessarily lessons learned, but sort of like research areas for us to really, I think, be excited about. And I think a lot of us, as we move into these different areas, we can bring that experience that we've developed together as part of bearing out what UTM is and help add that insight into those different operating concepts.
Great, thanks, Jeff. And Phil, how about from a SDO perspective, right? What can we learn from how we're doing and have been doing UTM that can be applicable to these other new entrants?
Well, I'm glad you brought that up, and we actually started looking at it, and we agree completely that it's not a one-to-one translation to AAM and upper air as well. So we're looking at the lessons learned from what we've learned in the UTM standard development, and we've actually revised the terms of reference for our working group to include traffic management for AAM, UTM, and upper air as well. Now, we haven't started that work yet because we want to finish the work on the UTM standard, but that is the next phase that Ahmed wanted to tackle, because he does believe that there are lessons learned, especially from the DSS system that we put in place. And when you're looking at a digital type traffic management system, it's a big leap, and without biting off more than we can chew right now, we just think it's a worthwhile effort. And I'm gonna let Amit take a little bit more of the discussion on that one, but because he is going to be the lead.
No, just Phil captured it, and Joey, as you know. So what we have realized is there are obviously gaps in what we know from a UTM airspace management point of view as we start transitioning towards AAM or UAM. Maybe not necessarily from the DSS interaction, but the PSU or PSU, the provider of services for UAM, PSU to PSU interaction, and other concepts, how we are managing these. I'll use an analogy like slot management as you do vertiport approaches and departures. So there are a lot of the new concept nuances that get introduced. So hopefully, and call out to the folks that are interested. So we are going to be spinning up the UAM focus group next month. which is just a few days away. So encourage anyone who wants to roll up the sleeve and has an interest, not just an interest, wants to actually do the work, to reach out to us, and we'll be happy to pull you into the conversations.
Awesome. Thank you, guys. So yeah, we're in our last few minutes here. There's 6 of you, so you got less than a minute each. I guess just we'll get a sense of how optimistic, pessimistic, realistic you might be. If you can give us just a couple sentences on, you know, the next steps for UTM, whether it's 1 year, 5 years, 10 years, major barriers, major hopes, whatever it might be. Go ahead and send us out with something here. We'll start with Ronaldo up there.
Sure, I'll say I'm optimistic because I think the world recognizes we need a digital environment where, as Steve Bradford said, it's information instead of eyes, providing that level of safety and that level of cooperation, and that with the level of autonomy that's coming, that we're not going to have positive control but managed by exception. I think those principles that UTM has been built upon have been widely accepted. I think the path that becomes a bit more challenging is the regulatory side and the oversight and the getting regulatory certainty that is necessary to drive investment models going forward. And I think we're seeing big steps in Europe with the upcoming new space regulation that provides some of that certainty. I think we're excited to hear Jay talk earlier today about, you know, a path forward and the engagement and the FAA's implementation plan. But I think we're seeing that as kind of a key step to make sure that the industry can happen and to help make sure operations are happening at scale and providing that value of service. But overall optimistic. I think everyone agrees, and UTM in some form is honestly an inevitability to support the range of aviation that exists and will exist in the future.
Awesome. Amit, hit us.
I think Ronaldo captured most of it. The only other couple of items I'll add is I think I'm optimistic, definitely. And what we see in the crawl walk thing, I think the UTM by itself, UTM is, like you mentioned, it's a glue that holds things together. It's a framework. It's not a thing by itself, right? So using UTM as an enabler to where it lets us use it as UTM as safety credits for your operation to enterprise operation. So it may not be a nationwide deployment of UTM, but for a specific area, specific type of operation, whether it's delivery, linear inspection, UTM providing you those safety credits to enable those operations. I see that happening near to midterm.
All right, Phil. You're muted, Phil. Oh, you're muted again.
Damn.
There you go. You're perfect. Oh, nope, you're muted.
Okay. Yes. Sorry. The future looks bright, but I don't think it's going to be an easy road ahead. I think there's going to be several challenges, but I think we've got the right people at the table, you know, the brightest minds working on this problem. And I think as Amit and everybody has already agreed, it's a necessary part to make this, to commercialize UAS operations, not just in the United States, but worldwide.
Awesome. John, from your perspective.
There we go. There's a lot of lag on my mute button there, but yeah, I'm very optimistic, and I'd like to ask myself the question as we've talked about UAM and AAM and how maybe these concepts translate to that ecosystem. But why are we even talking about flying cars today? And I think the answer to that is because of all the doors that the drone industry has beat down. From the advances in electric propulsion, but more importantly, the regulatory and public perception barriers to accepting autonomy and autonomous systems. And we've seen great progress. And I think that the progress we've seen in the UAS industry is what's really stimulating all the interest in AAM at this point. Hasn't become that much more feasible in the last year than it was 5 years ago. It's in my opinion due to the work of the small UAS industry that's really enabled that. So I'm optimistic that the push will continue, and that the great economic potential that can be enabled by scaling operations will continue to drive that. And I certainly support what Amit and others have said here. There's no need to wait for a perfect solution if indeed it does address the safety issues and can move the ball forward. So incremental steps, and don't wait for the all-encompassing solution. So,
thanks, Jeff. Quick take from you.
Yeah, I'm very optimistic from my vantage point, for just evidenced by the fact that we're all here, and I don't know how many hundreds of people registered for this, but we hit a nerve, and the work that we've all done together is, I think, for fear of being hyperbolic, I think we were ushering in really a new age of aviation, as we see here, from what we started with the small UAS, but seeing how applicable it is elsewhere. It's really a dawn of a new age, and very exciting to kind of be in a front row seat for it all. So very, very optimistic and excited for where this is all going.
All right, Seb, top that and take us home here.
Yeah, so I'm too optimistic. So I think that we passed 5 years when we spent a lot of R&D effort to understand what the UTM is and how to blend it with the different services. And now, as in Europe, I see that regulation are almost covering that, and there is already several UTM deployment in Europe, and these deployments are connected with the UAS services. So the future is very bright, and it's just a matter of time when the money will start flowing and the services will really be utilized by the people around. So I'm looking for that.
Awesome. Thank you guys. It was an awesome hour. Really appreciate your time. A great panel. Thank you guys. And I'll pass it off to you, Jay Woo.
All right, what an awesome panel. I was really looking forward to listening, and then surely it was a great 1 hour. Now, we are about to conclude the team, and to do that, I'd like to invite Cheryl Quinn, who is the Deputy Director, Aerospace Operations and Safety Program, followed by Ron Johnson. Cheryl, would you have a few words for us?
Sure. Jiwoo, thank you so much for inviting me to attend, and it's been a great pleasure. I want to thank all of our attendees for either rising early in the morning to join us or staying late, as many of you are. The response is phenomenal. I'm really glad that we were able to do this. I'd like to thank the speakers and panelists. Great bunch of presentations with an overview of the UTM project, architecture, key technologies, human factors, modeling and simulations. Very comprehensive summary of the technical work and the progress we've made to date. And the TCL flight test story illustrates the how this project came about with the partnerships and engagement with the test sites and FAA to make this a reality. I think the that was supported by Jay and Praveen's presentations that really highlight the coordination with the FAA through every step of the project, and enabled key technology transfers that are helping the FAA initialize follow-on work to further develop that UTM ecosystem, and work toward enabling that widespread low-altitude small UAS operations. I'd really like to thank PK for jumping in and giving us that impromptu lessons learned and kind of history lesson. That was enjoyable to hear how we got this thing started, because it really was kind of an uphill climb in its nascent phase. And then our final panel, wow, that was really great. I just really spoke to the impact of UTM, the UTM project and the UTM construct on US and now global UTM initiatives. A lot of progress being made on the standards, and really that's going to facilitate the operationalization. Also appreciated those insights into some of the highlights of what's yet to come in terms of expanding that UTM construct to additional types of operations. I'd like to thank the team, Anna, Chris, Kanate, and for making this event possible. It's often difficult to manage these sort of things, and I think we were able to get through it with only a few technical difficulties. And mostly I'd like to thank Jay-Woo and Ron and the rest of the UTM team for making this project such a success. I mean, this is really a shining star example of, putting smart people together and thinking of a good project and really breaking it apart into the steps you need to really tackle those barriers for really understanding what needs to take place in order to make this work. So I will turn it back to you guys, but thanks a lot for having me, and thanks to everyone for participating.
Thank you, Cheryl. Ron, would you like to say a few words to wrap us up?
Okay, sure. Yeah, well, I'd echo what Cheryl was saying about thanks to the UTM team, the panelists, and the NARI team for planning, preparing, and presenting this technical interchange meeting. It's a big effort to pull this off, and really appreciate everybody doing their part in preparing and having it, technically execute very well with a few glitches. So, and also just to the audience out there who we can't really see, but we hope there's still many of you out there. We had about 900 people register for the event today from all over the world. So that's really a testament to the importance of a traffic management system for drones and a safe integration with other airspace users and traffic management systems. So we really wanted to highlight what was achieved over the course of the project and point you to kind of the lasting legacy, which are our publications that further explain the results and identify remaining areas of work. So, the NARI group will make these charts available, this information available at a later date, so everybody can get their hands on it. So we couldn't have accomplished what we did without the enthusiastic participation of the UAS community at large, and particularly our partners on the project. They stepped up and made valuable contributions in all areas. In most cases, these were collaborative partnerships that really relied on good faith efforts, very little money exchanged. So we really appreciate what everyone brought to the table. With a very fast pace of expanding UAS operations, we definitely felt the community's pressure to move as quickly as possible to flesh out the concept and get the results into your hands and the FAA's. And I would like to acknowledge our close relationship with the FAA. NASA and the FAA have been collaborating on advanced air traffic management concepts and technologies for decades now, and this collaboration has resulted in a rich suite of solutions to vexing problems and more efficient ways to manage air traffic. But implementing a air traffic management system for large numbers of UAS is a very challenging problem and required a new way of thinking about it and required creative solutions, which is not so easy to do for big, large organizations like us and the FAA. So we tried to find new ways to be agile to meet your demands. So just in closing, while we're proud of what we accomplished, we're also very excited about not only the future of UTM for small UASs in low altitude, but also the new applications of the service-based architecture and how it will extend to managing traffic in high altitude for advanced air mobility vehicles, autonomous cargo, perhaps even space transportation systems. So just say thank you all for attending and contributing this valuable information exchange. Thank you.
All right. I just wanted to say also thank you to Melinda and Nicola for helping the presenters go through review process in timely manner, and also PK for having NARI host this event. With that, UTM Tim is concluded, and until we see each other again, please stay safe and healthy. Take care now.
Take care.